Welcome to APEC. It's January 20th, and I am your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. In today's session, Kurt Zeller presents on SpaceTime Engineering. Curtis Horn discusses the Sachs-Dirac Matter Field Equations. Christopher Maylor describes his research into a quantum-based warp core, and we are expecting John Brandenburg to present his revised model of the nuclear holocaust on Mars. He may or may not be able to attend, so we're not sure about John, but we are hoping that he will be able to be here with us. Also, we're going to be hearing updates from our lab partners and finishing off the event with an open discussion by conference attendees. I am really excited. 2024 is starting out amazing. We have research going on, especially with our lab teams. Everything is moving forward. There is so much work being done. So many results are being produced. It is just incredibly exciting and gratifying to see. So let me congratulate everybody in our community. A couple of quick updates before we begin. Today's event uses StreamYard. We're broadcasting through the Alt Propulsion YouTube channel. We're also rebroadcasting on the Alien Science channel. Check us out. You can visit altpropulsion.com to see our channel. Visit alienscientist.com to visit that one. You can ask questions using the live chat feature on the right-hand side of the page, and we will try and ask them to our presenters, depending on time constraints. You can always view replays of this, details, and speaker info on our website at altpropulsion.com. So I want to get into our first presenter. I am pleased and honored to introduce you to Kurt Zeller, who's going to be talking about space-time engineering. Essentially, the gravitational electromagnetic analogy postulates that our gravitational field is composed of two components, a gravito-electric field and a gravito-magnetic field. And so he is going to be discussing those as well as the potential astronomical implications of them. So without any further ado, I'm going to bring Kurt on. There we go. Welcome, sir.
Thank you, Tim.
Welcome to APEC. Yeah, well, thank you. It is a pleasure and an honor to have you with me. Let me put up your slide deck if I can. There we go. Right. And you should be able to navigate that yourself. So what I'm going to do is mute myself out. I will be here if you have any questions or anything like that. And I would say take it away, sir.
All right. Thank you. Yeah, excited to be here. Excited to talk. I've got not that many slides, so we'll see. I'll try to slow down, take it slow. Some of the objectives here. I really just want to provide a top level view of this gravitomagnetism. Frame dragging is another name for it. We'll talk about some of the experimental anomalies surrounding that might be related to this effect, propose potentially some next steps for an experiment. And my idea here is really to stimulate discussion, figure out, is this idea worth pursuing? I'm looking for honest feedback. And so I don't think this is going to take the full hour. I'm hoping maybe 30 minutes, maybe 40 minutes, and maybe we'll save the rest for some open discussion and you guys can give me some honest feedback. An outline of the talk, I'll start with an about me and just kind of how I got into this topic and what my career is in, sort of the perspective that I'm coming to the table with. I'll talk about motivation, which I think is probably the same for many people that are in this community, UFOs. We'll talk about obviously gravitomagnetism, the evidence, potential implications, and then sort of the fundamental theory that I'm getting at, which is not new. Most of this stuff is not new, but perhaps I'm putting a new perspective on it, coming from a microwave engineering background, and some of the relevant experimental anomalies that might be hinting at the fundamental phenomenon, and then we'll have some discussion. All right, so about me, EM Drive at Cal Poly. So I studied aerospace engineering at Cal Poly SLO from 2012 to 2016. And I was studying rocket science and I got pretty fed up with it, because you're not going to get to other star systems with rockets. I think that's pretty obvious. So NASA at the time, NASA EagleWorks was testing this asymmetric resonant cavity. And if you're not familiar, it's this frustum-shaped, I don't know if you can see my cursor, but you've got this frustum-shaped or conical shaped copper cavity where you're putting microwaves in, they're resonating. And the idea was that you're pushing off the fabric of space-time, or perhaps emitting some sort of quantum vacuum plasma. Harold White and a couple others where Paul March were working on this. And, they're getting results and they couldn't explain them. And so as an undergrad, I got really interested in the topic. I participated a lot in the NASA Space Forum, which I know a lot of the people in this community also were around there at that time and maybe still are today. So I taught myself how to do, electromagnetic simulations using EM Pro, sort of a free software for students. I took apart a lot of microwave oven magnetrons, and I took out one of the antennas, basically made a homemade magnetron antenna. We brazed a little SMA port to a magnetron antenna, and we're able to hook that up to a VNA, to a vector network analyzer, to basically measure the resonance of this tunable cylindrical cavity. So you see in the middle here, we've got this cylindrical resonant cavity. We made it asymmetric by using like a dielectric loading. So instead of having the shape be a conical shape, which is really hard to tune, we made a cylindrical shape, and we're able to tune that using a plunger, basically. And this is funded by the university. We got a small grant to do this, me and another student, a friend of mine, and able to borrow a lot of equipment from the university. And we used a laser position sensing detector to basically reflect off of a mirror. And all in all, it came out to a thrust stand that could detect about 2 millinewtons reliably. You can see on the oscilloscope here, we've got that green kind of oscillation is actually just noise on the order of, I think, less than a millinewton or so. And so we could reliably detect about 2 millinewtons. And but I spoiled the surprise here. The experimental outcome, thermal expansion of the leads was the problem. We don't have an onboard power supply. We're plugging this in externally. We thought this pendulum, maybe we could orient the wires so that we don't have that issue. But basically, every time we fired it up, whether it was on resonance, whether it was off resonance, didn't actually have the effect that we were going for. We couldn't isolate the effect that we wanted to see. So could not see the anomalous thrust, but that turned me from a microwave engineer or an aerospace engineer into a microwave engineer. So that led to my first career move, which was doing microwave plasma reactors. So this is kind of just a new technology to basically convert natural gas, methane, into carbon and hydrogen, which has a lot of applications. You can make different types of carbons. You can make the carbon more graphitic. You can make the carbon more like graphene. Right now, we actually have a pilot that's deployed in Pittsburgh, Pennsylvania, and we're working to scale the technology and deploy it in other applications. And so that's all of this to say is, this is my kind of real career. This is where I'm coming from when I present this gravitomagnetism stuff. I also had a few years working at General Atomics doing nuclear fusion. Got to visit ITER in 2022, which was pretty amazing. The scale of that place is mind-boggling. But at General Atomics, I got very experienced with COMSOL multiphysics, which I'll talk about a little bit more later, and designed a lot of new electron cyclotron heating equipment, which is basically really high power microwaves at really high frequency. And while I was at General Atomics, they had an open pitch fest. So they invited anybody to come out with their wild ideas, and they said that they would fund somebody. And so I worked really hard to put together a pitch for what I thought would be the best theory for anti-gravity, or space-time engineering. And so that's kind of where this presentation sort of was born. And I've done a little bit of refinement to present to you today. But I got runner-up in the competition, did not win, unfortunately. I think they thought it was a little bit too out there, even though that's what they wanted. But that's how it goes. So motivation, unidentified aerial phenomenon. I think that we're all on the same page here. This is straight from the DIA report, Director of National or DNI report, that basically says, these things have appeared to demonstrate advanced technology. They move at considerable speed without discernible means of propulsion. No thermal signature on these IR videos. These things are moving. We've got pilot witnesses talking about craft moving at 90-degree angles, pulling massive amounts of G's, accelerating instantaneously. All of these are consistent, excuse me, with space-time engineering. i.e. gravity field modification. So some sort of space-time warping is going on. I think there's ample evidence that this is a real thing. The question is, how do you do it? And so that's been my real, I don't know, hobby, passion for a long time. And yeah, so let's talk about sort of the theory about how that could work. So it kind of comes back to frame dragging, which is the same thing as gravitomagnetism. So this goes back to Einstein's time. Lenz and Thirring derived frame dragging from general relativity. And it took us until about 2004 to actually measure this with a high degree of certainty. And so, I think it was Gravity Probe B and a couple other satellites, as well as now we've got quasar measurements that are measuring this effect. And basically what this says is that the curvature of space-time depends on mass and velocity components. So it's not just your static rest mass, it's also the movement of that mass relative to other mass. So the angular momentum vector creates a warping of space-time that is similar to the magnetic field created when an electric charge moves through space. Some of the differences is you get a negative sign. So instead of like charges attracting each other, instead of like charges repelling each other like you do in, when you have two electrons, you've got like charges attracting each other, and that charge is now mass. And obviously we've got this gravitomagnetic field, which is orders of magnitude smaller than G. And so that's the big challenge here is, okay, so we've measured this effect. The problem is it's tiny. That's why it took us so long to actually reliably measure it. And if that's the case, how could we possibly use this to do anything useful? Oh, wow, some things got blown out of proportion here. All right, so on the left here, we've got electromagnetism, which everybody should be familiar with, Maxwell's equations. You've got your Lorentz force. So when you've got current moving through a wire, it creates a magnetic field according to the right-hand rule. And you've got an electromagnetic impedance of free space. So when you design an antenna, it needs to be able to radiate properly to its environment. And so the analogy suggests that gravitation acts in the same way. You've got gravito-electromagnetism is basically saying that your gravito-electric field is just like your Newtonian gravity, and your gravitomagnetic field is your weak component of gravity. And it's not the same force as a magnetic field. It is just an analogous analogy. So within the analogy, you should have a gravitomagnetic Lorentz force. You should have a gravitomagnetic pointing vector. You should have gravitomagnetic impedance of free space. And I'll come back to that in a bit. But basically, this gravitomagnetic field comes from angular momentum. So, at every scale, if anything has angular momentum, it is going to create a gravitomagnetic field. And this is actually according to the left-hand rule, which I find kind of intuitively satisfying that this would be the relationship between, mass, sort of interpreting it as a charge and looking at it with respect to electromagnetism. But of course, I'm going to say that as the microwave engineer. It seems very, it seems like a nice way to formulate everything. Okay, so I talked in the intro. I did mention that I wanted to look at astronomical implications or cosmological implications, but in doing some more research in preparation for this talk, I was actually a little bit stumped. There are a few papers out there that suggest, like this one from Ludwig, who says that, hey, if we include gravitomagnetic equations in our galactic rotation calculations, we can potentially explain some of these dark matter observations. So instead of this anomalous galactic rotation being responsible or being caused by dark matter, this invisible stuff that we can't measure that's distributed very specifically throughout most galaxies, but not all, maybe that is actually the movement of the galaxy itself that is pulling the galaxy together. And we don't need any dark matter, sort of correction factor to include. But then I dug into a little bit further and I found examples that refute this idea, like NGC 1277 is a relic galaxy in the Perseus cluster. It's dark matter deficient, much less than you would expect, and compared to most galaxies, but it's also a very fast rotator. So that kind of threw a wrench into this idea. And I'd say maybe there's something there. And I'm not a cosmologist, I'm not an astrophysicist. So, this is just me reading a bunch of scientific papers trying to figure out what's going on. And my conclusion here is there is no conclusion to be made yet. So gravitomagnetic interpretation might be a partial explanation for dark matter, or it probably does affect galactic rotation. It probably does affect the movement of stars, but I think that saying that dark matter is fully explained by this is probably a bit presumptuous. So I think there's interesting research to be done here, and I hope that more people look into this because I think that there's probably something there that we're missing. So then it comes down to what about at the quantum level? So if we say that the gravitational field can be affected by gravitomagnetic induction, so if we can change an angular momentum, then we can create a gravitational field. Well, why don't we look at the quantum level? A material, if you think about it, has intrinsic angular momentum in the form of quantum spin. Every atom in any given material has a quantum spin number, unless that spin number is zero. Or not. I feel like it could be wrong here. That might not actually be zero. But anyway, it's different atoms and different isotopes have different spin numbers that are sort of ground state. And so really the idea is that not all vectors within a material are aligned. And if they are, they're not changing in time. And so if you could align all of the atomic angular momentum vectors within a lattice across an entire material, and you could drive a time rate of spin or time rate of change of that atomic spin number, and then you could also consider the macroscopic emission of gravitons or gravitational waves from that material that is matched to the ambient impedance of free space, then potentially you could leverage this effect to produce an appreciable field. And I think that last point, that we need some sort of gravitational antenna, is perhaps the interpretation that a lot of people that I haven't seen out there, except for only a few papers. So I've only found a couple of examples where people even attempted to simulate a gravitomagnetic field, and it's never, at a smaller scale, it's always like a black hole or something like that. So you can see the example here. But what would a structure look like that could interface with the, we're basically living in a capacitor, if you think about it from the electromagnetic analogy perspective, where the, Earth is like a capacitor. And how do you create a gravitomagnetic oscillation that will interface with that capacitor to cancel off the fields that you're subject to? So that's kind of the essence of the theory. One of the big questions is does the order of magnitude kind of math check out? So you could look at the gravitomagnetic field at the center of a spinning disk, a macroscopic spinning disk. Let's say a 1 kilogram mass, is orbiting at a 0.1 millimeter radius at 1 megahertz, so ridiculously fast speed. The gravitomagnetic field you could create is 10 to the minus 18th, so like tiny. Very, nothing you could do with that. And then you need to be able to change that angular momentum with time. And so obviously you've got G's that your material is going to experience. And so that's just not really a viable idea. The macroscopic angular momentum of a spinning disk is just not enough. But if we assume, as the big assumption here, that quantum spin and classical angular momentum are equivalent, then okay, maybe we're onto something. So let's think about bismuth 209. And I don't pick bismuth 209 out of the blue. I've done a lot of reading in the UFO lore, and bismuth seems to come up a lot. I'm not sure if there's anything really there, but it seems like a great candidate for this theory because it has a very high ground state spin. And so you could think of a 1 kilogram mass has an intrinsic angular momentum on the order of 10 to the minus 10th joule seconds. You could calculate its moment of inertia. You could think about each atom having some radius spinning around some center axis, and then you could figure out what that orbital frequency is, which is ridiculously high. So you could think of, hey, each atom actually has an associated gravitomagnetic field associated with it. So if you had every atom within a 1 kilogram material aligned, you would have actually a reasonable sized gravitomagnetic field. And if you could change that with time, that suggests that you could create a gravito-electric, aka gravitational field. And over here we've got, the cartoon illustration of bismuth 209 sort of wobbling around some center axis. And this idea that you could use quantum angular momentum to affect the gravitational field is not new. This isn't something I came up with on my own. This is, a lot of people have suggested a link between superconductivity and gravitation. I think one of the most prominent in there is Ning Li. Douglas Torr had a series of experiments papers back in the 90s. I took this quote directly out of that because it's really the essence of the theory. Coherent alignment of lattice ions, spins, will generate a detectable gravitomagnetic field, and in the presence of a time-dependent applied magnetic vector potential, a detectable gravito-electric field. And they've got this really big derivation that basically says, when you align all of the angular momentum vectors of these lattice ions, or you can think of the nuclei, nucleons of a material have the same alignment of angular momentum vectors. You could think of it as changing the gravitomagnetic permeability of that material. Whereas, when you have a magnetic material, you've got alignment of electron spin. A magnetic material has all these electrons that are oriented in the same direction with their spin. But a gravitomagnetic material has all of the nucleons with their alignment of spin. And so, this derivation is not without criticism. There are a lot of assumptions that go into it. This paper, is one criticism. I wouldn't claim to really have the mathematics or physics background to stand on either one of these, but it seems like this might be an area worth further investigation. At the same time, Lee had an experiment in 1997 that was inconclusive. And so that didn't really lend much credence to the theory, but then I know the story goes on. Lee was given some grant from, I think, DARPA, and kind of went dark. And so we don't really know what happened to her research. We don't really know if there was actually anything there. You could go on and talk about the Podkletnov experiments, which is a bit of a rabbit hole, so I'm not going to really dive into that. But basically spinning superconductors, emitting gravitational fields, or causing a gravitational anomaly. I actually had a professor in college that tried to replicate that experiment like many years ago when Podkletnov first introduced this idea, and he was not very keen on. He was actually the same professor that helped me with the EM drive, and he was not very keen on Podkletnov because of his reluctance to help them replicate the actual aspects of the superconducting disk. I guess Podkletnov was a little bit shaky on some of those details, but that's just word of mouth. I don't really know. And then you've got Martin Tajmar, who's done a lot of great work in this field. Did I think gravitomagnetic detection of a London moment or something to that effect. Basically, induced acceleration fields on the order of micrograms that were correlated with the angular acceleration of a superconductor. You've got the niobium-Cooper pair mass anomaly from Tate, which is another interesting, very thin film superconductor, measuring the mass of what they would expect the niobium-Cooper pairs to be versus what they measured, and there was quite a large deviation there. And then you've got other sort of maybe related papers, enhanced induction into distant coils, things that seem like they might be related, but I'm not actually sure. So basically what I'm trying to say here is that the idea that I'm presenting here isn't new, but it seems like we're missing something. It seems like there's, we're missing the replication, and perhaps that's because the way that we're thinking about it is incomplete. And I think my sort of thesis here is maybe that thing that we're missing is kind of the impedance matching to free space. We need to think of this as a gravitomagnetic antenna that is emitting a field that needs to interact with the field around it. I can imagine designing a very poor antenna and exciting electrons in the right way, but actually reflecting all of that electromagnetic energy back to source because I didn't design it correctly to impedance match to free space. And so you could probably do the same thing with a gravitational antenna. And so that's kind of what we're getting at here. I tossed this slide in here. I think properties as type 2 superconductors. This is kind of what I think is the the best avenue, the best avenue to actually engineer this effect. So if you wanted to align the angular momentum of all these lattice ions, as Ningley says, you probably need to look at superconductors because you can achieve coherent phase of all of the atoms in a material. You can also drive what they call Abrikosov vortices, which is like little supercurrents that are spinning around in circles. And these supercurrents can be on the order of tens of they can be on the order of tens of atoms in diameter to 50 atoms in diameter. And so perhaps you could imagine stimulating a pretty large percentage of the atoms using this supercurrent, basically driving that angular momentum up and down. And so there are some papers that suggest the Meissner effect requires this linear combination of magnetic and gravitomagnetic potential to vanish. There are other papers that suggest a transient gravitational fluctuation should be detectable, which kind of derives this from Ginzburg-Landau equations and a lot of fancy math. Basically, this slide is trying to say, hey, this coherence of lattice ion angular momentum could increase your gravitomagnetic permeability. Perhaps we need to look at superconductors in this kind of vortex regime. And perhaps those superconducting materials in the vortex regime need to be made of atoms and or isotopes that have the kind of spin characteristics that, a large ground state spin that can be enhanced, that can be throttled up and down. So recently, and I actually discovered this while I was preparing this presentation for this talk here, is Tajmar published a paper last year that anomalous force measurements from a Cooper pair, which was a null result, unfortunately. He basically put a supercurrent through a high temperature superconductor within a cryostat in a vacuum chamber. He's got a setup that can measure on the order of 100 nanonewtons. So that is the best resolution I've ever seen for a thrust stand. And it seems very well characterized and very well put together. He's got an onboard battery system. He's got the ability to apply decently high magnetic fields. Unfortunately, he did not observe a thrust with his experiment, but maybe there are some reasons that it didn't work. I mean, he had a DC electronic stimulation. He didn't have a time rate of change of the nuclear spin. He's just pushing current through. He's got potentially a lack of gravitomagnetic impedance matching to the surroundings. He's got a large thickness of superconductor, which I've seen a lot of places. The Tate Cooper pair mass anomaly had a very thin superconductor on the order of microns. We've also got other observations or other papers that talk about the thickness being very important to seeing this effect. So this paper specifically says that if you generalize the Ginzburg-Landau equations with the gravito-electric and gravitomagnetic components, and you look at the situation where you're close to the second critical magnetic field, so you're in that vortex regime and you've got a maximum coherence length, you can run the math. This is a paper study, and you can say, hey, well, we could potentially predict a transient fluctuation in gravitational field. And so basically the conclusion of this paper is that you would want to minimize the thickness of your superconductor to find a larger effect, but for a shorter time. And so then you would imagine that you would need to oscillate this effect or pulse or continue to stimulate so that you can see the effects at steady state. Or maybe you design your setup so that you can detect that very quick pulse. So all of this to say, and then we've also got this metamaterial of extraterrestrial origin, which I find kind of interesting because, we've got this, what's claimed to be an atomically engineered material from To the Stars Academy, Tom DeLonge and many others, which is pretty interesting. We've got micron thick alternating layers of bismuth and magnesium. So there's bismuth again. We've got magnesium positive ions that are enhanced 60 times more than typical. An article from Linda Howe. I didn't find like any kind of study article or I don't know, scientific paper backing that claim up. So that'd be cool to see data from that. Same as the next one, material acts as a waveguide at terahertz frequencies. That was from To the Stars Academy website. They kind of just threw that in there and didn't have any kind of source. And I thought, hey, that's kind of like a big deal. If you can make a waveguide out of magnesium zinc, that's worth, publishing. As me coming from the microwave engineering side, looking at, electron cyclotron resonance, waveguides, high frequency waveguides for fusion. I know waveguides pretty well, and I couldn't find anything related to magnesium zinc waveguides at terahertz frequencies. That would be pretty cool. You can imagine that maybe, so I put together a little simple COMSOL model just to illustrate a terahertz waveguide, and it's on the right order of magnitude when it's air-filled. So you can imagine if your magnesium zinc was somehow a dielectric, which I'm not sure how that works, but if that had a high dielectric constant, then those dimensions would shrink, and you'd be on the order of tens, hundreds of microns. And I guess this is maybe, if this is related to a warp drive at all, this material, this claim, then maybe the size scale of the atomic vortical oscillations is an important aspect of it. I'm not sure, but I found this kind of interesting, possibly related, possibly not. So I'm not sure how things got highlighted. I wasn't intended to all be highlighted, but anyway. So I think the proposed next steps. I think Dr. Tajmar has like a state-of-the-art test apparatus and just needs a better test article. He's got the nanonewton resolution thrust stand. He's got the ability to put cryogenics, bring your superconductor down to cryogenic temperatures. He's got the ability to apply high magnetic field strengths. All of the ingredients that you would need to actually test this effect, we really just need to design the right test article. So maybe that requires proper selection of the superconducting material, considering the elemental and isotopic composition. Looking at that ground state nuclear spin, thinking about the microscopic lattice structure alignment. So if you've got, grain boundaries in your material, and some of your material is oriented this way and some is that way, it's likely not going to be a good emitter of gravitational waves. Test article excitation, magnetic stimulation. So, what kind of magnetic stimulation, what time rate of change do you need in the RF excitation? Do you, what regime of the type 2 superconductor do you want? Do you want actually that transition region right between type 1 and type 2 superconducting phases? And, it's probably something to be said about the penetration depth and also the thickness of your material. So as you know, the Meissner effect, magnetic fields within the material, within the superconducting bulk will cancel out and you have some penetration depth. So that's probably something to keep in mind. And then there's the test article macroscopic characteristics. So, you need to design a gravitational antenna, some sort of radiation pattern, something that's going to couple outside of the body itself. And so, I've been able to get gravitational acceleration of a moon-Earth system in COMSOL, using like the partial differential equation solver. I haven't figured out how to do the gravito-magnetic side of things, and that's kind of been on my to-do list for a while. I haven't figured it out yet, but being a COMSOL guy, it's a fun little side project for me, so I think I'll get there eventually. But for now, that is my talk. Thank you.
Kurt, thank you. Thank you, man. You know what? Let me bring everybody in here. We need to give you an enormous applause. I'm going to pop everybody onto the stage here. Let me take down your slide deck. Now, you actually had another slide deck. Did you have more to do there? I'm going to add everybody in. We need to give, let me see. Let's give Kurt Zeller an enormous applause. I have a couple of folks who don't have their cameras on. Hang on. Let's get SoCal in there. Mark, I haven't seen you clap. Mark is co-hosting with me. You look tired. Okay, so
hey man, get a few monsters.
Yeah, should we do Q&A? Do you want to do Q&A?
I have a question. That was interesting. That was amazing. So I have a few questions if I could present those.
Yeah. I mean, we have some time, so yeah, go for it, Alex.
So my first initial question is, I'm sorry, what was your name? Because I came in a little late. I just want to make sure I'm addressing you correctly.
Oh, Kurt
Respectfully.
Zeller. You just call me
Okay.
Kurt.
So, Kurt. Okay. So I was curious from a perspective of, I know a lot of PhDs who specialize in vocabulary used in various disciplines, and I'm curious how you define gravito-magnetic versus electromagnetic. Is it just the fact that it's intertwined with gravity, and you're just expanding on that? Because I'm just a little curious how you define that. I'm not trying to rub you the wrong way or anything.
Yeah, that's a good question. So
Replace the
gravito-magnetic.
Q with an M in the
Well,
Coulomb
more
equation.
just the vocabulary. Yeah.
So we're looking at this as four fundamental forces. You've got electric, magnetic.
Yeah, exactly. So I'm just curious about that.
Gravito-magnetic. So you can think of the gravito-magnetic as really just an attempt to make that link that, oh, hey, if electric charge moving causes a magnetic field, mass charge moving causes a gravitomagnetic field. So it's really just building on the analogy.
That's a great explanation, and I think you'll see when we present the metamaterials we have, it does align with a lot of the interesting technical details of the unknown material you were speaking of, and not only that, but it is very well known that, well, not very well known actually, but you can do calculations with non-Euclidean math, which is what we've been doing with the metamaterials, which clearly shows what you said, the vectors affecting space-time, dark matter, dark energy, gravity, and relativity, and I think there's one more. I woke up a couple hours ago. But those are all going to connect with each other. They're all going to have interplay between the vectors, where you can clearly see, if you have non-Euclidean math, where it factors in the fourth dimension, how gravity is affecting things like time, how it's affecting things like EM, dark matter, and electromagnetic energy. And I would love to give you some of those equations because it's really easy. You put in the parameters for whatever measurements you got on EM. It'll directly show, how that's affecting time, how that's affecting every other gravity affecting constant, which is very clearly able to be defined based off of the things you were saying. So I'd like to talk to you after. That's very interesting. And the stuff you said, based on the actual hard materials engineering, is very accurate. And I was kind of freaking out on the backstage thing because you did fantastic and are going definitely in the right direction.
Cool, thank you. Yeah, I'm going to drop my email in the chat, so feel free to reach out. I'd love to engage in more discussion on this.
Will do.
Thanks, Alex. So let me see. Does anybody else have questions? You guys have questions for Kurt? Mark, go for it, sir.
Okay, Kurt. Great presentation. Have you heard of the Alzafon experiment, dynamic nuclear orientation?
I'm sorry, I'm having a hard time hearing you. Can you get closer to the microphone?
Have you heard of the Alzafon experiment with dynamic nuclear orientation?
I think I've heard of it. I haven't really looked into it. Alzafon?
Yeah, Frederick Alzafon. He describes a process called dynamic nuclear orientation, basically orienting subatomic particle spins.
I have heard of it. I actually was in touch with them, trying to do an experiment with them in collaboration with General Atomics, but that kind of fell through. They wanted money, and General Atomics didn't want to pay anything.
Oh, okay. Yes, I actually been replicating it for the past couple of years. We got some positive results over the past weekend. And in the process of getting those positive results, I left the traveling wave tube amplifier on for a bit too long, and I think I fried it. So I'm wondering if you have any, if you could be of any help with traveling wave tube amplifiers.
I can't say I have any direct experience, but maybe. I don't know. Feel free to reach out. I'm definitely, available to pitch in and maybe just at least lend some feedback or connections. I have a lot of connections of people that do RF source development at General Atomics, who one of them did his PhD actually creating something similar to a traveling wave tube. So maybe I could pick his brain a little bit and help you fix it or diagnose.
Well, and Kurt, if I could interject, so Mark has been showing me over the last few weeks. He's using LabVIEW to track this, and during the lab time, maybe he can put some of that up. He's getting some pretty amazing results. I mean, I'm going into 2024. I'm really pumped up. I know, like that's like kind of my job, right? I'm cheerleading, but I mean, I mean it. I'm seriously pumped up about this stuff. So. Mark, do you think you might be able to do that during lab time? Show folks some of the like lab view
Yeah,
stuff?
probably in a couple hours from now. I got some stuff to do, but at like 7 p.m. Eastern, I should be
Yeah.
at the lab to give you guys
Yeah.
an update.
Yeah, this year is exciting. It is exciting, and it's not like it's coming from nowhere. This is like what I'm seeing is people have been doing. They've been buckled down. They've been doing hard work, and it's moving forward. And we're starting to see results, right? And like, you know, like Drew and Charlie Bueller, they did that presentation. You know, this is years of work for them, but it is paying off, and it's generating results, and it's just amazing. So.
Yeah, this came out of the pandemic, and so we've just all been buckled down at home in the lockdowns, and all us nerds had nothing better to do. So,
Yeah. Well, let me see. Does anybody else have? Yeah, go for it, man.
So, and I should have written this down. I had one question about this. So terahertz metamaterials might be one way to do some of this stuff. These layered nanomaterials of different varying lengths. But what about the idea of a quasi-crystal? Because you could have 8-dimensional quasi-crystals with 8-fold symmetry, and they have hyperdimensional symmetries. So there was a question about, interdimensionalism, and if I was just trying to think of anything physical that we could actually use to experiment with to test some of these hypotheses. And I remembered that, Ed Fouché a long time ago had said that quasi-crystals were the trick to how the alien saucers work, which, take it for what it's worth, but there are some interesting optical properties of quasi-crystals as well. But I just I wonder about this this material, and if indeed you said about the chamber that Tajmar has over at the European Space Agency. What if we could get in touch with Gary Nolan and get that piece of material over to Tajmar to test in that facility?
Yeah, it's an interesting idea. I'm not very familiar with quasi-crystals or 8-fold symmetry, so I'd have to look into that. But and I think Tajmar is located in Dresden, so I'm not sure if he's associated with ESA at all. But yeah, I think I've spoken with Tajmar personally before, and he's very receptive to people that are interested in working with him, collaborators. And so I think that if we had a compelling enough design for something, he would probably be willing to test it. And especially given the amount of work he's put into the test apparatus and the tone in his paper being a little bit disappointed that he didn't see anything, I wouldn't be surprised if he would be open to a new test article.
Right. Can I comment on that? Quick, so what my question would be, the way I look at higher dimensional math, which is the thing I'm very familiar with, is observed, like relative measurements might not have any effect on how an actual higher dimensional structure or anything like that would operate. I'm just curious how you correlate, or how you would correlate when engineering the expected results versus the relative results of perception and how that's affecting it, because you could seem as though you were mimicking higher dimensions as I'm sorry, what's this guy? Jimmy Rice said above me, with the engineering patterns, like the geometry of and I'm just kind of like, lattices and stuff can clearly mimic multiple dimensions, but how do you know that's translating to what it is in reality is what I'm curious about. That's been a huge engineering solve for me, accounting for the fact that those things are imperceptible, and I may just be accounting for what I can see and what I can measure. So I'm just kind of curious about that, because even though the structure of the crystals could possibly relate to what you're talking about, higher dimensional structures or whatever, how do you know that it's actually relating to that while accounting for relativity and perception and stuff? Because you could do that with energy outputs, you could do that with the measurements you're getting, but without being able to account for that, it seems fruitless to me. Because the humans have inherent limitations in that. But I'm just curious, I'm not trying to like put you on the spot. I'm just curious how you account for the fact that there are imperceptible measurements as well that cannot be accounted for. Is it like, what would you do about that?
I'm not sure, to be honest with you. Imperceptible measurements don't sound like an outcome that's worth pursuing, because if it's imperceptible, then what use is it to us? So
I would say that you're figuring out how to make it perceptible.
Exactly.
Because even though you can't perceive them, they're still constants, you know, that like gravity-wise and dimensionally. They're like, I think the main engineering solve would be figuring out how to account for the fact you can't perceive a lot of those things. And like I said, I'm not trying to call you out. I'm just curious about how that process would be worked towards or anything. Because things with dark matter, we can use the interplay between how it's affecting gravity and how it's affecting time to get the measurements on what, you know, that dark matter, which we're still not even sure of, is likely doing. So what's the equivalent of that with what you're doing?
I'm not sure I have a good answer for that.
Yeah. Well,
No, that's an honest and good answer. So sorry, I was just curious. Go ahead.
Yeah.
Let me go. Yeah, let me go to Curtis Horn. Curtis had a question. Curtis, go for it, sir.
Hey there, Kurt. Hey guys. So I noticed you're using COMSOL, and my question was, were you trying to figure out if there'd be a response, or a thrust with the COMSOL model, or were you just using that to kind of get a understanding of the material?
Yeah, so I think one of the core theories or core components of my theory is that you kind of need this gravitational antenna. So, and in COMSOL, you can arbitrarily change material properties. So if you can input these gravitomagnetic equations into COMSOL, they look just like Maxwell's equations, and COMSOL is great at solving Maxwell's equations. So really, you're just then changing material properties to be whatever you want. And if you could imagine the gravitomagnetic permeability of your material arbitrarily changing, then you could say, oh, well, if I design my material to be this shape, it might have this radiation pattern, which might cancel off, the DC static gravito-electric or gravitational field of Earth. And maybe that's a component that a lot of experiments have kind of neglected. They're just trying to stimulate an atomic lattice coherence and some sort of oscillation, but they're kind of missing that radiation pattern. So that would be my goal of the COMSOL modeling. That's not even close to what I've actually done. I basically put in gravitational fields, and that's about it. So my experience with COMSOL is really the electromagnetic side, thermal, CFD, electrostatics, particle tracking, that kind of stuff. And also a good resource if anybody has a COMSOL model that, I'm pretty quick with it. So if you ever need something, I can't offer my services extensively, but I'm usually pretty open to collaboration with others.
What about for payment?
For payment?
Because that sounds useful. That's a good skill.
It's not my COMSOL license. It is my employer, and that is the startup company. And so I would have to talk to him, but it's certainly a possibility.
Cool. Okay. Yeah, I definitely have some stuff we might need to talk about. So.
Cool. Yeah, feel free to reach out via email.
Yeah. The reason I asked that is that, as you know, COMSOL, it's going to use the equations that are in there. And so if you're just using the standard formulation of things, you're not going to find what we're looking for. You have to put something. So it sounds like the basis of what you're putting in is the gravitomagnetic theory. Is that correct?
That is, yeah, that's what I'm going for.
Okay. A follow-up question I had was about the in terms of like a replication. Later on in my talk, I'm going to go over what we're doing in a Mach effect drive near the end, or maybe at the lab update. I'm not sure when, but you know, it's looking like we're going to need another third-party test because things are looking good. So yeah, if you know somebody that has a lab that can do a really small forces, although we're getting bigger than nanonewtons, we're definitely bigger than that. But yeah, I might be interested in that as well.
Yeah, I would encourage you to reach out directly to Dr. Tajmar. You know, I'm not, it's like I'm like close friends with him. I've spoken to him once before. So I know he's a friendly guy and I know he's really involved in this topic. And so I think, you know, if you've got good results, he'd probably be interested in collaborating.
All right, thanks.
Awesome. Let me see. So does Dan, go for it, sir.
So just to if I'm understanding your magnetogravitics, we're just dumbing down really simply, like looking at the stress energy tensor. Are you just like say like modifying the momentum flux and the momentum density in your stress energy tensor to adjust your gravitational fields? Is that basically what's going on?
Yeah.
Okay. Thank you.
Sure.
Awesome.
I got a question,
Eric,
Tim.
go for it, sir.
So first a comment and then a question. So the comment first about arts parts, that bismuth thing. If you look at science.gov or apps.dtic.mil for all the military documents, there is a bunch of good resources of research out there based on bismuth magnesium and especially bismuth silver, because silver is another component in arts parts that's not often talked about. In Linda Moulton Howe's book, she has like, I don't know, 10 or 15 pages about the analysis that was done back in the 90s on it. And you can see some of the stuff that's in there.
Okay. What's
anyways,
that book? I can probably look it up. It's fine.
Yeah, you can look it up. I'm sorry, I can't remember the name of it offhand, but it's from like the mid 90s.
Okay.
Anyways, so the important thing though about the bismuth silver stuff and the bismuth zinc and the bismuth magnesium stuff is that bismuth is able to convert heat or IR into energy, right? It's an energy conversion thing. Additionally, bismuth has negative susceptibility, which is useful because if you have negative susceptibility, now you got negative permeability, now you got negative, you got something to push off of basically. So just comment on the bismuth stuff. There is good reading material out there. There's at least, I don't know, a dozen different papers. Some of them are from the 60s and some of them are from the 80s. That's the two decades that you should be looking in. So anyway, that's the bismuth thing. The other thing, at the very beginning, you had a really interesting thing with your calculation about the 10 to the minus 18 second squared over meters kilograms for the gravito-magnetic moment or something like that. But that is comparing it to the permeability of free space, or the permittivity of free space, right? The 377 ohm. But that is not necessarily a constant. We take it for granted that it's constant because we say as long as epsilon and mu never change, then you're totally good to go. But that's not the case because as we see with many of these craft, the surfaces of these craft are emitting very strong magnetic and very strong electric fields. Sometimes they can even get close to like Schwinger limit level stuff, right? So now you're starting to alter those indices, which I think is just something you should consider as you look forward into this. Is if you're using materials, so rather than impedance of free space, you have the impedance of the materials, or if you're altering the impedance of free space. Either of those two cases are cases that should be considered when you're looking at your gravito-magnetic calculations.
Okay, yeah, that's a great comment. Yeah, I'll definitely have to look into that a little further.
Awesome. Well, so let me see. It's 12:55. We got about 5 minutes left, but Curtis is next, so we could go right to his. Does anybody have any final questions? Christopher, go for it, sir. Let me unmute you. There we go.
Okay. I just wanted to really support you.
Thank you.
Nanomaterials,
Ah,
materials, and the multi-layered. I do use magnesium as well as zinc in these, as well as other materials like these metamaterials, which are for body armor and radiation shielding. And I'm generating time distortions physically from my warp core using gravity. So there are gravity interactions within the warp field, and they trigger temporal distortion in more than one place around space. I just thought, to support you along the path you're on, that it's a different direction to one I'm taking, but at the same time, time and gravity are key components within achieving tic-tac performance. That's about the nicest way I could say it. I'm also, on the other side of the energy field, the warp field, I'm generating the same distortions that you see at a corona around that warp shift. They're there. But you've got a long way to go yet. Just keep going.
yeah,
Wonderful.
fascinating.
I didn't want to ask a question because everybody else has, and I just wanted to give you a bit more support.
I appreciate that. Thank you very much.
And Christopher's going to be he's going to be presenting after Curtis, and then Alex is going to be assisting him as well. So again, we have this is exciting. This is going to be a very exciting event. Kurt, thank you so much. It is truly an honor to have you with us today. It's wonderful to have you present. If you want to come back and do more, we'd love to have you. And let me see, Curtis, do you want to go? And Curtis is up next.
Yeah,
So,
I'm ready. Just real quick, Kurt, I have a quick question. Do you know if there's any open source software that can be used besides COMSOL that's multi-physics?
Multi-physics, not off the top of my head. I know OpenFOAM is a good sort of software, but I'm not familiar with it. I've just heard it tossed around before.
Yeah, okay.
But yeah, thank you, everyone. I appreciate the feedback, and yeah, looking forward to participating in this community a bit more.
yeah. Well, Kurt, thank you as well. It's wonderful to have you here. It's wonderful to have you cover this material. And I would say this is absolutely the time. I mean, I've been in this topic for a long, long time. And what I'm seeing right now, and I'm sure like Jeremy and probably everyone here would agree with me, but it just seems like things are surging forward right now. And it's really exciting. So,
Very cool. Yeah, thank you.
okay. So let me take everyone. Oh, before we do that, let's give Kurt one more applause. Sir, thank you yet again. Thank you yet again. And let me see. And I will put your presentation up on the page, and people, again, they can see this in replay on the website. So I'm going to take everyone out except Mr. Curtis Horn, and he will do his in just a second here. Okay. And let me see. So Curtis, thank you, sir. And you're going to be talking about the Sachs-Dirac Matter Field Equations. And basically, these are, so Mendel, Sachs, and Paul Dirac worked on these. And these are particle-antiparticle pairs and quaternion E&M. That's kind of what you're going to be going over there. As well as, if I understand correctly, how those relate to propulsion and potentially Woodward's work with the mega drive as well, right?
Yeah, I'm going to cover at the end. I have a lab update to give and a couple slides, so I'll cover that as well.
Awesome. Okay, so let me put your slideshow up, and you should be able to go back and forward on this one because you did the upload for it. So we're good there. And thank you yet again. Thank you. And I'll be here. I'm just gonna disappear from view so that you can proceed.
Okay, sounds good. So yeah, so the title of this presentation is the Sachs matter fields, or how I learned to stop worrying about how to interpret quantum mechanics. So it's a little kind of homage to the presentation that I think is going to happen later about what happened on Mars potentially. So anyway, so I figured do something fun. So I have quite a few slides to go through. So basically, in my previous talk, I covered Sachs's theory at the big picture. Because it's a unified field theory, there's a lot of ground to cover. There's the unification of E&M and gravity, and inertial matter. And so, I went really quickly. This time I'm going to more focus on the kind of the details of the interface between quantum and general relativity, which has to do with quantum. If you're wondering why I'm talking about quantum mechanics here, is that quantum mechanics foundationally has to do with the inertial matter and what matter really is, right? So this is where I'm going to go slower in the development. I'm going to cover more or less, what I did in like maybe one slide and several here. So I'm going to kind of walk people through so they can, hopefully with this talk, people can get more of a intuitive understanding, or, understanding the justifications and the route and the different thinking, different path that is taken here. So now, and as we go through this, we'll again dive into, where inertia comes from and what might be happening and the potential for, manipulating that with technology. So, the big motivation here, I mean, the big thing that's obvious that people have talked about for maybe 100 years is, quantum mechanics and general relativity are incompatible, right? So we're trying to make progress in physics, but fundamentally, you have two theories that are highly successful. I mean, you can argue which one has the most accurate prediction, and they both have like really, astounding numbers. 10 to the pick the number, 15 or whatever it is. I don't know, some number of decimal places, but that's not really what comes down to how you select what's fundamental. But both are very successful, right? So it's really hard to say, okay, I'm giving up on one or the other and go a different way. But they're clearly incompatible theories at their core in terms of like with the standard interpretations of them. So relativity is a continuous theory. You have interactions between bodies. It's a realistic theory. It's not something where you're just describing matter. You're like explaining. It's explanatory, right? It's objective. Like I said, it's deterministic. And you have nonlinear, non-homogeneous equations. You can't use linear superposition. Some of the math tricks you use to solve ordinary differential equations are not possible because it's nonlinear, right? And there's no special reference frame, right? So things are covariant. Quantum mechanics, on the other hand, you have particles that could be, infinitesimal or discrete. You're looking at things as you're descriptive, and you have a probability interpretation because things are you have a superposition principle. Things are linear, and you can use the probability methodologies to make a prediction of a probability distribution of what your experiment is going to have, what you're going to observe, right? So it's more of a descriptive theory than an explanatory theory, kind of like at its base. So how do we make them compatible? That's one thing. Of course, if they're incompatible, we want to make progress. How do we fix this? Quantum mechanics being a descriptive approach, and GR being analytical, they're so one or the other we need to do something different with, right? So we got to step back and look at the big picture. Of course, a lot of man hours has gone into attempting to quantize gravity, and it's so far not been successful. And if the other side is correct, Einstein and others that were in his camp, it might not even be possible to quantize gravity, right? So at that point, now that we see that, okay, here's the problem statement, what can be done? So we can assume quantum mechanics is more fundamental and continue to attempt to quantize gravity. We can also assume that GR is more fundamental and find a field theory, a nonlinear field theory that is compatible with general relativity and gives quantum mechanics as a low energy approximation. Okay, that's another route that can be taken. And the third route is finite abstraction, whether it's, you know, category theory, some kind of topological theory, something, you know, more abstract, where we find a mechanism where both can exist despite the compatibilities that it's somehow allowed. Okay, so those are the kind of three general, I mean, there might be more, but these are the kind of three general paths that you can take. So the path we're taking here is we're going to be attempting, and it has been attempted to derive quantum mechanics, the mathematical formalism of quantum mechanics, from general relativity and the principles of general relativity that we're going to use. So instead of trying to quantize gravity, right, we're going to do the opposite. And to do that, you got to think about what you're doing, right? You got to think logically. You have to have solid physics principles that are the basis or the axioms that you're proceeding with, okay? And they need to be something that can be verified, all right? Now, it may be that some of the axioms you have, as a result of them, logically you can deduce other things that are expected. So you don't necessarily have to throw in all the things that are expected and make the theory from there. You know, the simpler, the fewer number of axioms, the more likely the theory can, you know, have a solid foundation, especially if it's predicting things, or things are come out as a result that are expected. So that's the approach we're taking here. We're starting with the GR approach with the covariance and going from there. So first question is, okay, so, well, Curtis, if that were possible, wouldn't someone have done that already? Well, okay, we're talking about somebody that did do that, Mendel Sachs. But, you know, looking at general relativity as it is now, traditionally, right, it doesn't have, you know, when you take the tensor equations as they are, it doesn't have the ability to predict what's in quantum mechanics. You can't get that, right? So something does need to change with GR to get one more step further. And what that is basically removing the space reflection and time symmetry that restricts the group, the foundational group, algebraic group of general relativity. So once that's done, you end up with you go from a second order equation to a first order equation, or a set of them, and you have a fundamental group that is compatible. It turns out later to be something that can be used to derive a field theory of inertia. So that's what has to happen there. And so what do we need to add to relativity? So one thing we got to take away is those symmetries. And what do we need to add? So of course, covariance is the fundamental, the principle of relativity, right? So this is where that fundamental quaternion group is there, okay? The other thing that we need to add is, for Mach's principle, is it needs to be generalized. It has to be about all properties of matter, not only inertial mass, but the charge, magnetic moment, and other, isospin, whatever you find. It all has to be tied to this theory, right? To this principle, okay? So, and the other thing is that if you do take a generalized Mach principle, it will logically imply a conservation of interaction between matter fields, right? Because there has to be a way for matter to connect, and that is something that we find does have to be conserved. The other thing we need to add is we have to apply the correspondence principle here. So basically, the correspondence principle is, the way we're often familiar with it is saying that, okay, well, I have this general relativity. Does, at a low energy approximation, does it give me, do I get the gravity formula that Newton did, right? And that comes out. So basically, we need to be able to, if we have a new theory, and we're saying that it's nonlinear at a high energy, a high interaction, at a low energy or a linear approximation of that theory, we should recover the current successful formalism of quantum mechanics. The mathematical formalism should come out of that or be compatible with that theory, right? So that's what we need to add to general relativity. So how how does quantum mechanics need to change? So first of all, the interpretations, there's like tons of them. I put a Wikipedia link. I'm not going to click it, but we're not going to consider those interpretations of having any meaning, right? Because we're taking the general relativity route. And also, given the data, looking at what happens with quantum mechanics is we're going to treat matter as waves, right? So or analytical functions, and so we don't need a particle model. Basically, we're not thinking of little tiny balls of condensed charge moving around. We can treat matter as a wave, and that's because that's what we find experimentally. And if you guys saw the open mic where I covered Carver Mead's work, he's it looked like that's what's found. And what I find another thing I want to comment about this is that a lot of times the semiconductor industry and their successes are pointed at by people that advocate for quantum mechanics and say, hey, look what happened because of quantum mechanics. And if you ever go look at Carver's Mead, especially his presentation last year, I think I linked to that in the previous open mic. He really says that, hey, we weren't able to use quantum mechanics. We treated matter as waves, and that's what got us where we are. So it's a very interesting take from someone that was in there and actually was able to give us proved what we needed to know, which was that as you shrunk down the transistor size, you got more efficiency and more computational power. That's what actually propelled that industry. So it's a very stunning thing that I just recently found out about his presentation and his work, and it's a really solid. If you're questioning this, thinking about it, well, are we sure about that? Go look at that work. I would highly recommend it. So we're also giving up linear superposition. Hilbert spaces is not treated as fundamental, right? So we got to release that. And the interpretation, the probability interpretation of the wave equation, also we need to give that up, right? In order to take this path. So what do we have to add to quantum mechanics? So basically, quantum mechanics has to go from a linear theory to one that's nonlinear, but at the low energy approximation, we retrieve it. And we need to treat the equations of quantum mechanics as field equations of inertial mass field, right? Or a wave. So no longer is it a probability, it's the field, and that's what's interacting. And so we do need to apply the consequences of relativity and the generalized Mach principle to make these field equations, because we got up to a certain point with quantum, the Dirac equations or the Majorana equations, and and those are used for quantum field theory, and you're able to calculate and make some predictions, but we need to further develop those to make them compatible with our current formulation of GR that we're talking about here. And then also we need to apply the fundamental of interaction, right? So we're getting rid of particles. If you have two waves, they'll have and they interact, that is one-to-one, right? So that's where the so-called discreteness that we observe is explained. So quantum mechanics, up until now, of course, you had the Schrodinger equation, right? So, but the Schrodinger equation wasn't necessarily compatible with special relativity. So what you end up having is a Klein-Gordon used the Schrodinger's operators and actually made a theory that was compatible with special relativity. But they were second-order equations, and they included space and time reflection symmetries. So what Dirac and Majorana did is create a set of equations that basically you could take the Klein-Gordon equations and factorize them, and you remove the space and time reflection symmetries, and you end up with further predictions. Okay, so that's kind of where things kind of ended up, and then of course there was the additional power that quantum field theory brought in of being able to further do calculations with that theory. So So one thing I want to emphasize here, I talked a little bit about that earlier, but I wanted to kind of emphasize this again, is we're not proceeding in this theory. We're not proceeding with the particle concept. We may talk about particles, like just because it's just something that we're used to describing. Okay, an electron, it's a particle, whatever. It's an entity, right? Entity is a very general thing. Particle is a little bit more. Okay, we understand electrons, protons, muons, etc. Right? So, but the concept of a particle as being, a little tiny ball, that's what we're talking about here. That concept, we're not gonna be using that. So, and I have a quote here from Carver Mead. I won't read it all off, but basically what he's saying is that, and he actually quotes Feynman about this as well, is that we fundamentally matter is a wave. Okay, it has a wave property, and that's how we need to treat matter to understand things. So we need to go and look at the matter, the wave properties of matter, to understand how things in the bigger picture and in the small picture, how they actually work. So here we're going to go over continuing the matter field equations and what quantum mechanics is contributing. So initially, like I described, we have the operators from Schrodinger. Schrodinger had his Schrodinger equation. And Klein-Gordon used Schrodinger equations operators on basically the energy equation of special relativity. Okay, this is where the famous E equals mc square equation comes from. That's the full form. Okay, if you're not familiar, so E equals mc squared. If you have p equals 0 and you take square root of both sides, that's where E equals mc squared is recovered. So, but this is the full formulation of that matter, momentum, and energy relation in special relativity. So using the Schrodinger operators, Klein-Gordon used that to get the Klein-Gordon equation. And Dirac and Majorana both basically factorized the Klein-Gordon equation to get the Dirac equations. Okay, so that's where what quantum contributes to this theory. So for the general relativity side, basically what you have is in the special relativity, you don't have a covariant operator, right? It's not true for curved spacetime. So what we do here, actually, I'm skipping ahead. That's the bottom side, but what we do here is we transform the second line here I have is we transform the operator from a linear kind of a flat space operator to a curved space operator. And when you do that, you get the spinifying connection. So the spinifying connection is something that in Sachs's theory of general relativity, you have spinor equations instead of tensor equations. And with tensor equations, you have the affine connection, which is kind of like the fundamental where you calculate the curvature of space-time, which with the kind of mathematical entity you use for that. And here, because it's a spinor equation, you have a spinifying connection that's equivalent to that. And it turns out that that has to be that's the contribution of general relativity to the matter fields. Now, the thing previously is that because we are saying that we have matter fields and the Mach effect is fundamental here, you have the fundamental of interaction principle, and that's where that I comes in. So the I is basically a functional that describes the interaction of any given wave particle to all the other wave particles in the universe, right? So that interaction functional, if you have an aggregate of particles that are very close and interacting strongly, that I will be significant, and if they're free from each other, that I can be very small, right? So you can take the limit. So that interaction functional is part of this theory, what we put into the Dirac-Majorana equations to get to have that fundamental of interaction principle applied, okay, to our matter field equations. And then the next step is, I started talking about this first, but the next step is going to be taking that operator that's at the beginning there, and making it covariant. So making it applicable for curved spacetime. And what you end up with is what I have here at the beginning. And I'm going to take you guys through kind of, I'm not going to go in too much detail, but I'm just going to walk through the big picture steps to get the final result. And I know it's kind of like the slide a little goofed up a little bit here, but you can get the picture. So initially, when you do that, you end up with instead of the Dirac matrices, you have a quaternion there, right? We're in curved spacetime. That's that first set of equations. And what you want to end up doing is you notice that m is 0. So we set in the Dirac equation previously, we had an m there. So we set that equal to 0 because we're not going to be inserting the mass. We're going to be actually deriving the mass from this equation because we're taking as fundamental as the generalized Mach principle is in the theory. So we're building it into this theory, okay? So next thing, the spinify, you notice the spinifying connection is there, right? And as I described before, it's going to end up replacing mass in the Dirac equation. So using kind of basically the properties of the spinifying connection, we can rederive that equation to have a kind of a I would say an eigenvalue type situation where you have mass represented by that lambda e to the I gamma. And so one of the things is with that e to the I gamma, we can actually use gauge invariance to kind of factor that out and get rid of that. So at the end of the day, you know, the equations on the bottom, those are the kind of the full covariant matter field equations. You still have an interaction functional. You don't have explicitly shown the spinifying connection, and you have the lambdas, which represents the mass, which inherently in that lambda is going to be the connection to other matter. So that's how we end up with a fully covariant set of equations that are compatible with the curved space-time and compatible with the formulation of general relativity that is the spinor formulation of general relativity. So what are the consequences of this? So now we have a field theory that's compatible with general relativity, given that we give up the space-time reflection symmetry. We have to do that for general relativity. That's already done in the Dirac formulation. So all we have to do then is update the operator as I showed, and a few mathematical tricks, and you end up with that system. And the other thing we got to realize is the generalized Mach principle is fully applied here. So you use that as a principle of, okay, I know that I'm assuming that is true, and developing your theory around it. So it inherently has the Mach principle in it. It's not something discovered, right? So the source of inertial mass is clear in this theory, right? So you can using this theory, using some more fancy math tricks, you can figure out the mass of particles. One of the things that pops out of this is the Pauli exclusion principle can be derived from this formulation. As well, but that can be derived, and it's derived in a fundamental way. It's not a low energy approximation. Fermi-Dirac statistics, on the other hand, is recovered, but it's in a linear non-relativistic approximation of the theory. So you get back Fermi-Dirac statistics, which allows us to get the periodic table, right? So. It looks like my slide messed up there, so I'll continue to the next thing. So now we have a fully covariant matter field equations, and what we can do next is we can use those to look at or think about and figure out what happens with particle and antiparticle pairs, right? Derive what they do, what the solutions are for them. Okay. Before I kind of just showed basically the equations at the bottom, But here I'm showing a few of the steps. So if you recall, the first set of equations here I have looks like a lot like what I had before, but I have the gammas in here. And this is basically, instead of taking the Majorana form, this is for compactness, we're using the Dirac bispinner notation. So there's only 2 equations instead of 2 for each particle here. So 1 for each particle is shown here. And you notice that there's an interaction functional in there. There's the lambda, and you have the matter field, right? So these interaction functionals, I show them explicitly here. G in there is the Green's functions. There's a lot of different things that come from the spinor formulation of electromagnetism that pops up in here. I'm not going to have time to cover that in detail. That formulation of electromagnetism, that probably should be its own talk because it's so in depth. I was hoping that I could do both things, but I figured that this is probably enough. So the solution to those bispinor notations is shown at the third line here. And so you end up with an exact solution that can be kind of shown explicitly. And given that, then you end up with 2 spinor equations, 1 for each type of particle, 1 for electron, 1 for positron. And so those are exact equations that fall out of this. Okay. Now, so that particle antiparticle pair, one of the things about that is that it kind of gives us a mechanism for the generalized Mach principle to have inertial mass that we measure. So I'm going to cover this again kind of step by step so you guys can get my understanding of how the Mach principle mechanism works in this theory. So first of all, full covariance allows for a formulation of general relativity that gives us first order equations resulting in a spinifying connection. It's okay. And the matter wave field theory, it has to use that spinifying connection as part of the operator to be fully covariant and fit the theory. That spinifying connection is now found to act as the mass, right? That connection with all the other mass ends up being the mass in the matter field equation, right? Taking the place of that. So the M is gone and there's that lambda. So the resulting matter field equations, if you look at them, they result in a null state for particle antiparticle pairs where they're electromagnetically coupled, but they retain their inertial mass. So the inertial mass field, when an electron and positron come together in this theory, the inertial mass field does not disappear, right? The electromagnetic coupling is there. And so you see the electromagnetic energy, but the pair still exists. And that pair and that density of the particle antiparticle pairs is what interacts with matter, the matter wave fields that we are made of. And that's what gives us the inertial mass we measure. So that's how the detailed mechanism of the generalized Mach principle works in this theory. So what's the physical consequence of that dense pair of gases? So first, the solution of the coupled pair, it can be showed that interaction functional operating on the electron and the positron, that's 0. But the interaction functional itself, if you recall, of that bound state is not itself 0. Okay, so there's still an interaction there, and the energy and the linear momentum for the bound state can be derived to be 0. Basically, once the particle couples, it has 0 momentum, 0 energy. It's at the ground state of the universe. Okay, there's no jumping down to negative energies. Now, and that can be derived. That's derived using Noether's theorem. Now, in this being a analytical theory, it's not allowed to go from positive energy to negative energy. That being said, your theory, you can choose whether the energy levels are positive or 0 is the highest and you go down negative. Okay, so you could choose either formulation; they're equivalent, but you can't go from one to the other in this theory. And given the quaternion formulation of electromagnetism in this theory, you can look at the previous solutions and you can figure out what the ground state maps to in terms of like the electromagnetic sources. And what you end up finding is that they're equivalent to two oppositely polarized currents that are mutually transverse in kind of like the z direction. Like if they're on X and Y, they come together there, you'll find that they're transverse. And that's what's shown here. You see the J1 plus J2 is something. It's not zero, right? You have the e to the 2I lambda t. So you end up with that kind of current going out. And that's what actually is measured. When a particle-antiparticle pair come together, you end up getting an interaction that we measure you can measure with a Geiger counter or something. You measure the gamma, what is referred to as gamma rays, right? The other thing that consequence of this background pair gas is what we measure as black body radiation, right? So in this theory, this is an analytical theory. So if something is interacting, if you have two electrons and one's moving and the other one's moving because of that, right? You have this interaction. In this theory, there's no photon traveling. It's the electromagnetic field is coupling, and you have interaction happening there. You don't need a separate, a packet or anything like that here. So how does black body radiation happen, right? So that dense sea of particles would replace that. So basically, we find that there. The other thing is that density of particles, because it comes close to nuclei, that's what in this theory, that's what explains radioactive decay and why it's statistical. Okay. Of course, the magnitude of inertial mass of matter, and as well as the Casimir effect, right? The Casimir effect is something where it has to do in the conventional description with the vacuum and the way it's interacting. And when you have two plates close to each other, you can get this attraction because there is less interaction happening there due to that matter configuration. So those are the things that are consequences. Now, what are the consequences if you modify that density, right? So like, let's say what we're talking about here, one of the mechanisms to lower inertial mass or get propulsion is to modify the density of matter or the inertial mass of matter. Now, if you lower the density of the background pairs, because the black body radiation is in this theory is described by the background pair density, you should see lower measured temperature, right? Because when you measure temperature, what's really happening is that density of background pairs between you is kind of transmitting that, right? So you might see lower measured temperature when the volume is lowered. Also, you should see if someone's lowering the volume by splitting and rejoining the background pairs, then you should see a radiation signature indicative of that. Also, you should see in the volume a lower inertial mass, and you should also the charge to mass ratio and the magnetic moment will also lower with the same ratio, right? So you don't get like atoms flying apart or collapsing because the mass went down, and so the electron just flies off or collapse down and form a neutron star. You don't get that kind of thing because in this theory, at least, because that both of those manifestations of matter have to do with the interaction with the background pairs. Now, at the interface, you would expect, because you have a gradient of density of the background pairs, you would expect to have some birefringence type effects for matter at the shell. Okay, so that's about it for that. I have a couple of lab updates. One is that we were able to get another turbopump and get that in there. So we're able to get down to, I think we were at close to 1 × 10⁻⁴ torr. This I reconfigured it here, and I put the gauge closer to the chamber, and it was at about 2.8 is what's shown here. 10 times 10⁻⁴ torr. So that, and there's some more parts coming in, and we're going to be getting that turbo pump closer to the chamber. Unfortunately, I can't put it right on the chamber. I'd like to do that, but we would have to make a new end cap for the chamber. And we're not going to do that just yet because we're getting close to we're basically in the regime where we need to be, where the air effects are not something we need to worry about. The second update here is I can show this video maybe later on, but basically this was one of the better runs that we had. This was a sweep over 2 seconds. And you can see here, this graph on the right is the position of the torsion arm itself. The device is not graphed here, but it had the same kind of curve. They were both pushing in the same direction, and basically the sweep repeated every 2 seconds. So you get something that after you get a push, and then for a time, and there is here there's clearly an impulse that happens, and you can see that the points here at that first rise, that as it goes up, that the points are further away from each other. That's indicative of an acceleration, and then all of a sudden it stops, and you get like a kind of like a nice curve. That's where the forces stopped being applied. So whatever was happening, whether it was still the air or the Mach effect or some magnetic thing, who knows? There was a force happening. It looks like, and that kind of goes away, and then it comes back again, right? As the sweep goes down, we get back into that regime of those frequencies that activate the piezo stack, and you get the force again. So this one was a really good run because it repeated like a force in one direction. It wasn't a back and forth type thing that we've been having for the last couple of years. So I think one of the reasons why is probably has to do with us getting a good vacuum. We're not getting the air interfering with the effect. So that's the update.
Awesome. Curtis, thank you. Let me take down the slide deck, and I'm going to bring everybody back in. We need to give you an enormous hand. Curtis is becoming a regular presenter also. Let me see. It looks like everybody else has their camera off. Everybody, please put your hands together and give Curtis Horn an enormous applause.
Curtis,
Curtis.
that was very, very, very good about understanding the differences between quantum mechanics and general relativity. Great job.
Thank you. Bring Dan in also.
This is fascinating because I had, proposed to Eric Weinstein, what if you could, GR was derived from quantum mechanics? And then he said, well, why not the opposite? And, well, why not?
Yeah. Mendel Sachs did it back in the, I think, 60s or 70s. That's already been done.
Can I make a comment on that? So I do agree totally. I think the main problem is thinking binary. I mean, I don't think they're mutually exclusive theories, quantum mechanics and general relativity. And I do believe there are mathematical ways to parse some of those differences. If you look at the paper we have published, and that there's a lot on that about what you spoke on, parsing differences between general relativity and quantum mechanics. And so I wanted to speak a bit on the covariance. So basically, what I put in the chat, which for anybody who can't see that is accessible as published research, I do believe highly that there's multiple forms of things which can account for everything. Basically a theory of everything, quantum mechanics, general relativity, and parsing it. And I think that considering binary action is very limiting because you have to expect that everything's going to be equally probable, both the wave, both the particle. And you may disagree, which I also coincidentally and paradoxically agree with. But I wanted to go through the covariances in the theory of everything, the TOE, which again, I do not believe there's one form of. I believe there's a lot. I believe it's essentially very limiting to think binary, and that light existing as a wave or particle is basically based on how you're perceiving it and how you're measuring it. So I'll go through some of the covariances here that you spoke of, if that's okay. And I have some information.
Alex, hold on. Let me jump in just a sec. I do want to try and limit things a little bit so
go ahead.
We stay pretty focused on Curtis's, and then yourself and Chris, you guys are coming up next, and then I hope that you're able to go into some of that during your presentation.
Oh no,
as well.
Sorry, yeah.
No, that's okay. I just don't want to get too deep into it in the Q&A, right? Because that
it's highly technical. Contact me.
Sure, no problem. And one thing I'll comment on, Alex, about what you're saying is, sure, there's more than one way to look at it. Like, for example, you could look at general relativity and you could say, well, it comes from entropy, right? I mean, there's all sorts of ways to look at things. And I'm not saying that all of them are wrong. Here I'm covering, kind of strictly what Sachs developed and kind of bringing that back because, like you mentioned, Eric Weinstein's, talking about it like it's a new idea. It's that particular idea. It's not. So credit where credit's due, right? So Einstein, right? He was the one doing this path. Now, what I think is that, just like we had back in the day, we had the epicycles, right? And all of a sudden, it's like, no, things are rotating around each other, and it's a whole different way of looking at it. And it turns out that, okay, yeah, we can verify that, right? There's something we can test. So just like with anything, there has to be a predictive nature of this, and it'll kind of clarify for us, okay, what is reality really doing? Like, like Einstein said, what's God thinking, right? So in this case, one of the things I want to bring up is there is an experiment that I heard about that's coming on this year where they're going to be taking gamma rays and probing the vacuum. So I'm very interested in the results of that, because that should reveal, is it background pairs? Is there a finite number, right? I don't know the exact details of that experiment, but that's one of the things that is interesting to me. And the reason I'm giving this talk here in this group, Alt Propulsion, is because a lot of the consequences of the background pairs existing look a lot like the observables of UFOs and what people are describing there. So I found that that all came out last year, and that's why I kind of so my interest is the physics, and I think that one of the things that we got to really keep in mind is that there's likely something like this where there is a way of doing something that we can't access here. There has to be a reason why, right? So the background pairs being so tightly coupled and being so difficult to interact with is likely the reason why we don't, it's not easy to make a craft like this work, right? You need a lot of energy or some kind of really intricate understanding of how they're coupled and be able to, elegantly get them to, do what you want them to do.
I agree.
Curtis, if I could jump in really quick, let me apologize. So Shiva and Michael Boyd were hiding. I had to scroll down to find them. I didn't even, they were here in the studio, but I had to scroll, so I didn't see him come in. But what you were talking about with being focused on the physics, a lot of what Alex is touching on kind of goes to the philosophy of science. And I know that, Alex, you're going to talk about some of that a little bit later. And then actually, I'm really excited to have Shiva with us too. He had reached out and sent me a paper that's very focused on the philosophy of this as well. And so I think, I'm not positive, but I think that John Brandenburg will probably miss today's event. And what I'd like to do is actually have Shiva do his presentation. Well, that's okay. John is, John is always welcome.
I gotta change my title then.
Well, and just between you and me, without giving away too much. So you remember the movie Oppenheimer? They had the atmospheric ignition concern. So
Yeah.
John had a concern that might happen from neutron bombs. And I thought, well, that's worth mentioning, but we're all juggling schedules and we're all in holiday recovery mode. So it's one of those things.
Yeah.
But anyhow,
I would highly suggest that, I don't know how many of you guys are familiar with Carver Mead, but I just recently found his presentation, and it reinforced for me what Mendel Sachs was doing, because it's along the same lines, looking at matter as waves and not imposing our ideas, our limiting ideas to what matter does. And it's really, I'm really excited about the future, and kind of clearing out our old kind of what we were taught, the rote things we learned about force and matter, and just kind of taking the road where you're looking at solid principles, and it's not easy to think about, covariance, like what does it mean? It takes a lot of introspection, a lot of thinking to understand these things and to be able to use them mathematically. And at the same time, there's a danger of abstracting too far, where your math, you can do string theory and just I can predict anything, or just, my math can come up with anything you give me. At some point there's has to be a kind of a limit, like where do you go too far? It's like it's a subtle work, and it's not straightforward, right?
Can I ask you a question?
But go ahead.
Yeah, I was going to ask. So it seems as though you're trying to reach for something that is more continuous theory, and so how are you dealing with some of the discrete properties of particles? Like, for instance, you could see the in a fog chamber, you can see the particulate nature of particles, and so are you doing something to transition there in your work?
Yeah, so if you think about the presentation I gave, where I went from, okay, there's a Schrodinger equation, it's not relativistic, then you get Klein-Gordon, and then you factorize that, you get Dirac, right? You can think of that as kind of going higher and higher in energy, describing more and more what you can do with at least flat space-time, right? With this thing, what we're doing here basically is we're taking that and we're going, okay, I'm now taking that matter field equation and making it fully covariant. So now it can apply in a dense neutron star, okay? And that's where you would have to use that equation to describe what matter is doing versus the others, right? Those low energy linear approximations no longer apply in that portion. But if you're in regular matter, the linear approximations, the Dirac equation, all that stuff, those predictions, they come out. You can still use that. You still have that. Now, where does the discreteness comes in? Well, one of the things that's mentioned here as part of the Mach principle is that fundamental of interaction. So you have particles where there's built in an interactional functional, and that's where particles interact one-to-one, right? These waves interact one-to-one, and that's where the discreteness comes in this theory that we experience, that we measure in the lab.
Yeah, I'm still not quite understanding how it becomes discrete, though. I mean, you're saying that the waves interact one-to-one. In other words, like one peak with one peak, or one trough with one trough, or whatever. But that's still a continuous wave at that point. And so I'm just curious how you breach that transition to a discrete particle.
So when you're taking the low energy limit, basically all those higher terms are ignored, right? The majority of the interaction is one-to-one. So when you have a peak, even though we call it discrete, we all know that there's a line thickness, right? There's always, if you look at the spectral lines, for example, there's always a thickness there. It's not exact. And so approximately it's, discrete, but it's not really discrete, right? There's something else going on. There's nonlinearities there. and that's kind of in the particle model, right? The cloud chamber, that particle is a free particle in the free field limit. You're going to get that interaction as it goes along. Now, if a particle-antiparticle pair is coupled, the ground state, and it's moving through there, you're not going to see that in the cloud chamber because it's not interacting electromagnetically.
And I'd agree, because the Minkowski metric numerical equivalents are generally defined as 1, 1, 1, 1. So I 100% agree with you. And also, if you have a chance to, what is the name of the main paper you would funnel people towards, and what is the name of the paper, just to make sure that everybody can get it?
Yeah, so I would look up Mendel Sachs. He had several books. He has a lot of papers out there. And I know his stuff is not really, there's not that much on archive, but the first thing, there is a paper that somebody did about 10 years ago, I think it was now, where they took Mendel Sachs's relativity or general relativity formulation and rederived the Schwarzschild solution from that. So that's kind of like a good introduction, because they go over, how we factorized the equations of general relativity to get the quaternion formulation.
Was it 0 when the Minkowski metric was calculated?
I don't think Minkowski metric was mentioned in that paper.
Oh, okay. Sorry. Okay.
Did I answer your question, Shiva?
Awesome.
I think Michael has his hand up.
Oh, Michael, go for it, sir.
Yeah, I have a couple of questions. Would you be assuming that the speed of gravitation is the same as the speed of light? And the second is, what I'm assuming is that you're assuming that matter and mass is the source of gravity. Is there any gravity associated with the absence of mass?
If there's no mass, there would, in this theory, if there were no matter, there would be no mass. And so in this theory, the gravity would propagate at the wave speed. And that would probably depend on the density of the background pairs.
So I'm feeling like confused about your second answer. The wave speed, are you saying the wave speed isn't necessarily the speed of light?
No, it would be the speed of light. It would be the local speed of light. So in the theory, to know what the theory would say, the theory that we're discussing, Mendel Sachs' theory, we would have to set up the wave equations and find out, okay, what the wave speed is for that equation, right? And in the equations I'm showing, he's setting h bar and c equal to 1, just to kind of make it compact. But you can put that stuff back in there and derive what c is. And there is no assumption in the theory that c is constant or what, of a certain value. The assumption of the theory, the fundamental axiom, is general covariance. So in this theory, you would want to derive what c is, and that's the way you would do it. You wouldn't necessarily make a claim one way or another.
So basically, what you're saying is that the speed would depend on the density of space-time?
The density of the speed for gravity would likely depend on the density of the background pairs of the
background pair. You mean virtual pairs?
Well, so the virtual pairs, you can think of it that way. That's the quantum mechanics interpretation. But with this interpretation, there's actual when positron and electron come together and they couple, their masses still exist. So they don't annihilate in the sense that they disappeared and they turned into energy. In this theory, they're electromagnetically coupled and their matter is still there. So we're living in a kind of dense sea of these particles.
So kind of like a Cooper pair? like a Cooper pair in superconductor?
Kind of like that, but they're like so tightly coupled that the only way to get them out is to have a couple gamma rays that hit them and separate them out.
So my confusion is that my understanding is matter's mass comes mainly from protons, not electrons. So how do you account for the non-symmetric nature of the proton mass to the electron mass?
Oh, so I didn't cover what Sachs did with protons here. That could be a separate thing. I'd have to go over that and show you guys. But that is something in this theory that he did work on. So that's available as well.
So
in terms of mass,
a theory with protons instead of electrons. Is that what you're saying?
Yeah, he does cover protons in the theory. So that is available for us to kind of look at and see how that is approached in the theory. And the proton and the theory also, this theory also does have a prediction for the mass of the muon, and it does predict for fermions pairs. So you get the electron and the muon as kind of a pair, and the muon's about 206 times the mass, and that's predicted. That comes out of this theory as well. So you get muons, you get pions, you have protons and neutrons. Of course, neutrons are a composite. It'd be a whole different presentation to go over the particle physics analogies and where the line is with this theory, right? So, yeah.
Okay, thank you for your answers. I appreciate it.
Awesome.
Sure.
Awesome. We have just about 4 minutes left. Alex, I think you had another question, and then I think probably it's yourself and Chris doing a presentation.
Yeah, I'll be quick, and I'll make sure I relate it to his insights. And I would say a simple way to explain what he was talking about is that in general relativity, generally the speed of gravitational interactions is associated with the propagation of gravity waves. So that's going to be inconsistent. It's going to be whatever the source of the gravity wave that's emitting the gravity. And I think that would be a very simple way to explain all some of the differences that you were explaining at the beginning there, because it's not a constant, I think. And that's my opinion, at least. But I was just going to touch on that a bit. It's very detailed. I'll touch on that a bit in my portion of it. But accounting for light, I heard Michael Boyd mention the asymmetrical nature of photons and how they're represented in measurements. And that can all be explained by wave particles, by duality. And they can be both massless particles and like photonic waves, basically, and particles containing mass at the same time. If you count for both those things and you sit down and do the math, you're going to find it works out perfect. Like all this stuff, all the differences are going to immediately become apparent in those calculations, even with a calculator and pencil and stuff. So I just all I wanted to say is that's definitely correct. And I have that supported with a lot of our work, not only theoretical, but engineering wise. So I just wanted to say that.
Awesome. Alex, thank you. So we have just about 2 minutes left. Curtis, do you have anything else, or should we do another applause, sir?
No, I think, I think Jared has his hand up.
Oh, there he does. Okay.
Yeah.
Jared, go for it. We'll squeeze one more in.
Thanks. So Curtis, you were starting to talk a little bit about how the particle-antiparticle pairs, their momentum splits, right? You get a momentum vector for each one. And with the mega drive, it's all about, this asymmetric capturing of momentum, right? I was just hoping you might be able to kind of reiterate or recorrelate how the particle-antiparticle momentum stuff might relate to your mega drive stuff.
Yeah, so there is no explicit correlation that I have in mind about that, other than the fact that this theory is like explicitly incorporates the Mach principle in it, and using that does a unification of inertial mass and general relativity, right? So my interest in the mega drive in that experiment is to kind of bring back the Mach effect as something. Okay, we have an experimental proof. Now, that being said, when I brought up Carver Mead stuff last time in the open mic, that's already experimental proof, right? What was done with neutrons, that shows us that the Mach effect is real. That if you look at matter waves and the way they interact, there is an effect there due to those motions. So all that being said, I am investigating for this theory, what could be a mechanism that is used here, because we are having a piezoelectric stack where we're putting a lot of energy, taking it out really quickly, and we're timing it with the mechanical motions. And so it's it's kind of a nonlinear situation, right? So, these things, this theory applies here. And what I suspect is that we are somehow interacting with the background pairs and pushing off them, and pushing off in a way where, okay, because we have a bigger mass on one side than a smaller mass, when we push off, we get a reaction in one direction, and it's a very interesting effect, and to me, the experimental side of it, I think it's a very critical to have an experiment that's obvious, where, okay, yeah, we can put this in a vacuum, put it on a set of bearings that can slide it with low friction, and the thing just moves, and there's no other explanation. There's no error, there's no magnetic effects, right? That's what we want to see. And at that point, we can say, okay, there's fundamental physics here. We can start, investing time in figuring out what the mechanism is really going on, right?
Awesome. Well, so we are just past the top of the hour. So Curtis, let's put our hands together for your presentation one more time. Everybody, giant applause. Curtis, thank you, man. You have been such a tremendous contributor to this conference over the last year or so. It has been absolutely amazing. And again, I would love to see more work from you going forward. You're doing tons with Woodward's Mega Drive, and you're helping take that further as well. So it is tremendous, man. Thank you so much.
And if I may say too, you did great. You're on your way to your own theory of everything, to be honest.
All right, thank you.
Awesome. Okay, well, let me take everybody out. And again, Curtis, thank you one more time. I'm going to remove everybody so you guys are still in the background there. And I'm going to go to Christopher Maylor and then Alex Wolf. And so Alex is going to be helping Chris. Let me apologize a little bit for some of the confusion. So Chris is there. And I'll tell you what, why don't I'll bring Alex in as well. And what I'm going to do now is... There we go. So I think you guys wanted to start with this, right? Was this where we wanted to...
Christopher has his own presentation, and I could follow up on that in the last 15-ish minutes. But if you wanted to start here, that...
okay.
That
okay.
works.
Well, why don't I start? Chris, do we have yours? Did you send me yours?
I can send it to you.
If you can, or if you'd like to upload it too, that would be perfectly fine.
And I can speak on mine while he does that as well.
Okay. Well, do you want to do that? So why don't we do that then? We'll start with Alex. Alex, if you want to do that, and Chris, do you know how to upload? There's a present button, and then it has slides, and it can come from your computer.
Mm-hmm.
Okay. So I will start here.
Okay.
First off, very interesting here about, sorry, I'm reading my notes. I'm not trying to look like I'm not paying attention, but I wanted to speak on the covariance that Curtis spoke of. So you can basically, some quick notes before I get to the presentation. So if you essentially you introduced the idea that disturbances in space-time are caused by massive objects in motion propagated outward by waves, which is directly in contradiction to viewing things binary, one or the other. And that's, I believe, how you would solve that. And I believe that's supported as well by the fact that the metamaterials developments we've been doing have had major advancements due to non-Euclidean models. Like I said, I don't believe that there's one toe or anything. I don't believe there's one theory of everything. I believe it's basically and essentially limitless. And as long as you're non-Euclidean accounting for time, I believe as well that can be varied based on what uses you have for something like that and how intensive you want it to be. So I pretty much went over all that. But I just kind of wanted to let Curtis know that if you start looking at things as propagated waves, you might find that the mathematics between parsing QMGR start to work out very compatibly, beautifully. So let's go through this this presentation here, and I'll touch on that at the end as well if I don't forget. So Tim, if you could go to the next slide. Am I able to do that? I'm sorry, I'm not sure how this works. So how do I go to the next slide?
Sorry about that. That was Mr. Brandenburg on the phone. He will not be able, he's going to postpone until February, just so you know. So Alex, if you move your mouse over the slide deck, you know what? I have to do that because I added it for you. So it won't let you. Sorry about that. Just let me know when you need to go to the next slide. I'm still here in the background and I'll be able to move it.
Thank you. So essentially first, here's a little introduction. Alex Wolf III, PhD materials science and quantum physics, and we've been undertaking experiments, data verification, R&D, based on the metamaterials engineered by Christopher Maylor here, which he's been working on for, I believe, 40 plus years. So he engineers the metamaterials based on his education, and honestly, more important than education, the years and years and years of technical experimentation in a personal sense. And that's the main thing I wanted to touch on. Advancements in an independent sense can circumvent the need for large amounts of funding or imaging, software in imaging machines. And that's kind of what we've been doing. And Christopher has been instrumental, the main orchestrator of that. I did put here, it's based on Dr. Mark Moody's NASA, he's a NASA alumni, theories and pilot waves. That's not correct. It is, we've made developments majorly based on that, and it's been extremely instrumental, but his work are entirely Christopher's, and me, myself, and all of the consultants that work with him are basing everything off of data that he's provided based off of 40 plus years of work. So it's not necessarily based on Dr. Mark Moody's work, but I did want to mention him here because he's been instrumental in assuring constants and things like that. So the third point here, one thing I wanted to make very well known. Within a small, very limited group of scientists with the correct education, but not only the correct education, but the correct, procedure for experiments and stuff. And especially if you have engineered materials, you can quickly circumvent large amounts of funding, machines, imaging machines, photon imaging, the systems that NASA uses for gravity can be completely circumvented by unconventional materials, which greatly advances experimental data in a way more accessible way than has typically been available to people. So that's what we've been doing, and it works very well. So the last slide here, we have an array of outside consultants that verify the data we produce. I identified one, my very great friend, Richard Moeller, who's a BS of materials science. And it's very easy to create a very confined group of extremely knowledgeable people, and then also correlate that with outside data verification, experimental verification, and you have a very quick route to basically circumvent peer review. I mean, I believe wholeheartedly that data and experimental output greatly reduces the need for anything like peer review, especially if you have a self-contained system where people are able to cross-verify, you're able to get around $1 million machines. And I have tons of pictures, as you'll see. But that type of experimentation is the main point, is this information, all of the information here in this presentation and everybody else's is accessible. You don't need a degree. You don't need advanced machines or funding or anything. If you know what you're doing, you can kind of build these systems. So if we could go to the next slide, that'd be awesome. Okay, so here we go. The MetaMaterials Armour. Okay, and these are the properties of the MetaMaterials Armour, and here, right here. Oh, nope, not at all. Nope. Wait, sorry, 1 second. Let me get this fixed. But essentially, this Armour here is radioactivity diffusing. It maintains an electromagnetic field. It's compression force. It maintains abrasion protection, impact protection, and enhancement, which is interesting. Not just protection. You can distribute impact pretty evenly across pretty much anything. Like you could affix it to an object and hit it with the object. It's going to display anomalous properties of impact. That's something I found very interesting, which is still under investigation. I can provide technical details about that, but as I said, it's still under investigation. Contactless magnetic engineering of these materials is astonishing. I mean, basically, you can use the material to circumvent the need for a circuit board. You can fixing things to things with screwing, and that makes a lot of advancements that are typically not very accessible, along with the anomalous properties of the material, very accessible. And I have been, as you'll see in these slides, we're about to go over probably a year, 6 months before I had access to the engineered materials physically. I made basically off of sentences of text, interpretations on physics-wise what is going on here. And he was describing to me light emissions through the metamaterials with systems like this one right here. And there you go. I mean, I'll try to do that again. But contactless engineering is amazing, and I've been studying that a lot. I've greatly reduced components and other things by just routing the wires through the magnetic field. And that's pretty interesting. And that's what Curtis was talking about too, is all the vectors are related. There is no difference between EM, between dark matter, dark energy. You just need to figure out the interplay between those things. So I've been experimenting with all these things on the screen here. And I have some pictures right here. This guy, sorry, I'm not good at perspective, but I've been experimenting with contactless engineering. Nothing in here there's a few minor wire connections, but other than that, everything is contactless. I mean, the material itself maintains an electromagnetic field, which is very easy to not only manipulate, but study outputs of. So if we go here to this small picture, which I cannot see at all, we're going to talk a bit about how I can how different fields are evidenced through this material, including gravity waves. And if you look at that picture here, you'll clearly see that. And
oops. And it looks like Alex froze out there for a second. Alex, can you still talk, or have we lost you?
I'm going to keep moving just in case.
Well, and we do, Chris, thank you for loading your slide deck. So we do have your slide deck while we're waiting for Alex here. We'll see. He should be back in just a sec. And if not, we can always jump over to that and come back to it. And he had some videos as well.
Yeah, the MetaMaterials.
Oops, there he goes. Okay, let's see if he comes back in. And if not, we can switch gears.
I'm still talking until he comes back.
Oh, there he is. Okay, let me see.
I logged into that.
There we go. Alex, you were back, sir.
Sorry about that. And yeah, my connection is not Ivy League, I'll say.
Oh, that's fine. Let me take myself back out and yeah, just continue and let me know when to change slides, sir.
Thank you. If I do cut out here, I'll be right back on. But this is detailing some of the experiments, and that's some of the things as well. You can easily circumvent multi-million-dollar imaging machines by nanoscale engineered materials, which circumvent the need for those things. And that's what we've been doing. Not only what we've been doing, but what we've been verifying with experimental data and outside consultants, such as Richard Muller, who is great. So if we could go to the next slide. Okay, let's see. So here we have what I was talking about earlier, non-binary representation of light emissions, of photons, basically. And I will be honest in saying I don't know what a human or person or eyesight interprets as a wave versus a propagated wave versus a particle is accurate. And this is a good way to circumvent that. There's copious studies on this. And so from my perspective, it's pretty easy with the materials that are nanoscale engineered to mimic double slit experiments. And basically you'll see on the bottom there, double slit, two eyes or one slit versus, So I interpret that as positioning the photon as a wave on the bottom. I interpret the top as positioning it as a particle. I also interpret that as completely subjective. It's both correct, and that has been evidenced by not only our experimental data and the engineered materials, but I don't know if there will be a link or whatever, but we have a non-Euclidean model for a toe, which I also said I believe is non-binary. I believe there's endless amounts of that, which you can't calculate certain things like what Curtis was talking about, correlations between different vectors. It's basically impossible with Euclidean math. So we've been focusing on that. I've been trying to, and right here, this data I got is far before I had the physical materials. It's far before I had anything. All I had was a few paragraphs of information about a description of a video of light emissions through the metamaterials. And we're going to correlate that here in the next coming the slides with the actual experimental results once I had maintained the materials and had a good understanding of how to experiment with them, which did take a while. But you'll see here in the next slide, it's perfectly mimicked. And you'll also see from the other slides that light is evidenced not only as a wave, but as a particle simultaneously, which has been instrumental in advancing the materials. Christopher, I think, inherently already knew this always and kind of brought me on to figure it out on my own once I could independently peer review these materials. And it's been painstakingly slow. I'm not going to lie. I'm very busy, but what little data I have gotten is extremely lined up with what I based on known physics principles, interpreted based off of the described data. And I did that on purpose because I wanted to have no information and correlate it later with actual experimental technical data on the materials, which perfectly matches up. And it's good to keep in mind as well, the paper I have published on the TOE, the non-Euclidean TOE, is been instrumental in helping some things, advancing some things, but no, I wouldn't say advancing. I'd say analyzing data. It's been very useful for, because it's not going to change the physical output of any measurements you get, but it has helped us make a lot of sense about what's going on here. So if we could go to the next slide. Okay, here you go. I mean, this is the oscillating metamaterials setup. So what this is it runs a frequency, and I can determine the frequency. As Curtis said, I had to find a numerical value for that TOE. It was mainly based off of variables and stuff from general relativity, such as GIJ, which represents the localized space perturbation in localized space, stuff like that. And and that's an interesting thing too. You don't need to know the numerical values to calculate with it. All you need to know is the measurements of the inputs. So calculating the numerical values of an equivalent TOE to everything that can count for a gravity affecting constant has been tough, because you don't need that really to know. It's almost unnecessary inconsequential data, because as long as you're inputting measurements, it doesn't have any bearing on what you're doing. But here we clearly see, and you'll see from the other slides, there's very clear activity of hair-like structures right there. I mean, I did that with very little imaging access. You can see the double slit pattern, which I believe indicates a wave, which also, based off of my education and experience, is just my educated opinion, but I would assume that's the wave formation of the light, or the photons, or the emissions, however you want to define that. And this here picture is just based on this little setup. It oscillates, it blasts the frequency through. It stimulates the material, which is magnetic, through electromagnetics. There's a bunch of very strong magnets, and also an electromagnetic currency ran through. And when you get all those three things in unison, you start to be able to easily visualize some very strange behavior. And also this here is not through a typical camera lens. We have a what's called a chroma X filter, which makes it easier to, and you can read all about that. I'm not sure if that'll be linked or what, but if you look up my name, Alex Wolf III, on Google, you'll be able to find research about those filters. And it makes it very easy to do what we're saying: circumvent $1 million machines, circumvent the need for excessive amounts of funding to do research. And I will also keep open to everyone in this group. These materials are very openly available. Anybody who talks to me or Chris, if you want any information about how this setup works and stuff, because clearly I do fully believe, and I have mathematical mathematic calculation, whatever you want to say, with the ale or not, about this picture here correlating to a wave propagation. And then you'll see in the next pictures, it's clearly a particle. So I do believe, depending on observation and measurement, it can be completely dependent. This picture here, the hair-like imaging here, that is ran through the filter we have, the proprietary chroma X filter, which they don't make anymore. And it makes it very easy to identify and visualize photonic emissions, light emissions, gravity effects, and stuff. And as long as you can correlate directly with a non-Euclidean model what the physical data is saying in an image, it's very easy to verify that type of thing. So that's what we've been taking advantage of. And I am fully in relation to Curtis, wanting him seeming on the right path to look at that type of thought process, because it really, I do believe, is non-binary. And a lot of the stuff he was saying, almost all of it, actually, to be honest, seemed completely on point. So I would like to, if we could go on to the next slide here. Okay,
So how are photonic activity, light emissions, and EM, as well as space-time and gravity studied in a simple and accessible way? Christopher, I don't want to, like, I've been talking a lot. So if you wanted to take this one,
That's fine. You carry on.
yeah, go ahead.
You want to carry on with your slides?
Oh, sorry. Oh, you want me to finish?
Yeah, you finish it.
Okay, so this slide here is kind of redundant.
Alex,
I mean,
sorry. I would say, yeah,
little bit-
finish with your slide deck, and then we'll just bring Chris on after that. I know we have some videos too, but
perfect. Yeah. Tim, are we able to bring up any videos that I uploaded of the light emission videos or anything?
yeah, I can actually. So what I need to do is I will share those, and we will cross our fingers here a little bit.
Yeah, share that link. It's a bundle of links. So.
Okay. Well, and that's okay. What I'm going to do is there we go. Okay. So let me.
And I'll talk on that while you bring it up too. We have the light emission videos, which clearly evidence photonic activity, light emissions, and give mass to the particle of light. Not only that, but from material science, I don't know I don't know stuff about quantum physics perspective. It is a very small surface area. What you're seeing in some of those videos is a stimulated magnet attached to scissors, literally. And it's able to move a material with probably 40 or 50 times the mass of it, just from running it through that. This one here, you see, that's a smaller piece. And what that is, I have electrical stimulation going on at the top of those scissors, my instrument, my very fancy instrument. And all you do is just put above it. I put that surface with conductive gel and just pulled it. It would not move whatsoever at all without the gel. And I thought that was interesting. That whole surface, that little notebook there, is coated in conductive gel. Once I ran a current through the scissors and put it above the material, I was getting some pretty crazy pulls, basically tractor beaming, off of this conductive surface that had a light layer of the gel. So that's what you're seeing here.
And Alex, let me know when to go to the next one, sir, because you sent me
go
4
ahead.
of those videos.
Yeah,
okay.
sorry.
Oh, no, that's okay. That's okay. Just let me know.
And then here's another one. Electrically stimulated the metamaterials, pulled out the wire and set it down. The current runs through the material, and that's interesting as well. It's not generally, as electromagnetic study goes, where it's going along the outside. If you stick a wire in that, which looks very messed up based off of the video, but I pulled out the wire for the electrical stimulation, which was just a basic electrical wire, put between the 2 porting layers, stuck a magnet in there, and pushed it on the material. With the conductive gel on the surface, it basically glides. I mean, it's pretty cool. So if we go, yeah. And here is the light emission setup I was speaking of. You can see those particle indicating waves here. And I'll be honest in saying as well, a lot of these emissions we're still studying, I suspect, Christopher probably feels different, but I suspect highly these are photons. He thinks it might be something unidentified or electrons even. But you can look at different areas of the light emissions, and that supports the contactless engineering here as well. There's no components connected, there's no wires, there's no anything. It's all ran through the electromagnetic field produced by just the armor, which I think is very interesting because we're actually scrapping this armor for a more advanced model. And even the models being scrapped are going to provide endless research for stuff like that. And it does look weird. I mean, just as a human being looking at it, not knowing anything about science, I'm going to say that looks not normal. And we're running it through the Chroma X filter here. And then, you get material scientists, you get your own information, and you just consult for free. I mean, it doesn't have to be for free, but that's been extremely useful. I have a large network of PhDs and stuff from or even just BSs, or even just independent researchers. Not even just independent researchers are important, but once you have all those people analyzing the footage frame by frame, or let's assume 24 frames per second, between 20 people that are in my network of people who approve of my work, you're going to see a lot of variation between how they interpret the data, and then a lot of correlation between the things that they all had in common. And that's my goal. I'm working with Christopher is I take a lot of his data, which he's heavily proven, he's heavily provided evidence for, and seek outside consultation and my own consultation to verify that in theoretical and mathematical constructs. Here you go is the materials again. On the left, you're going to see the oscillation setup for the frequency, the light, and running it through the material, which is, again, I cannot probably get into the specifics of how that's engineered, but it's nanoscale engineered. It's nanoscale engineered, which will create some very weird effects. And the middle there is the gravity and time displacement warp core, which we have written on and provided endless amounts of proof of. If you, again, just Google my name, Alex Wolf III, you'll see that as the most popular research thing we've published. A couple thousand readers have looked at that, talked to many doctors who had questions or trying to construct similar things. That middle part, purely for gravity and space-time study. And that's I'm not going to get into that, but there's a whole paper published. It's about 40 pages long. Christopher, I don't know if you can link that here. On the right, we have a shin plate, I believe, for the Armour. And Armour has all those properties I discussed, reducing radiation, reducing abrasion, reducing or enhancing impact. And it's been amazing, because I was thinking that as materials stress testing, and I didn't start submitting it to analytical testing until about a week before this, because I was thinking it purely hit it with stuff, shoot it with stuff, run it over with a car, have your dad hit it with a bat. Stopping thinking like that, I thought of nanoscale engineering and decided to apply it analytically, and that's how you got the setup such as the one I just showed you. I was surprised to find out, verifying Christopher's work, that there was a lot of light emissions that indicated anomalous properties based off of that. The back of that material on the right, the golden looking one, is a mesh screen that protects from abrasion. The middle one, well, there's a whole paper on that. It's a compression forged material, and we've been getting small outages, small measurements that indicate manipulation of or variation of space-time and also gravity. And I will be honest in saying we don't have a time machine. It's working towards something bigger when you realize very small analytical measurements that indicate something weird, and that's what we've been doing in combination with circumventing a lot of machines and a lot of funding, which we still do. Between all of us have some funding, but it's been a lot easier to do it that way. And yeah, so these three materials here, it's on the left, I'll go again, the oscillation frequency and light emission setup. The middle study for that's the toroidal piece for is space-time and gravity perturbations. And then on the right, pure Armour. But all of it affects light.
And do you want me to go into the next slide for you now?
Yes, please. Thank you.
Okay.
Thank you. And here we go. So this slide is a little confusing. Let me get in closer. This is an experimental, or not experimental. This is a prediction I had based off of the available data when I had basically nothing about this. I had a description of a video of the light emissions, which honestly, I'm going to be honest, probably Christopher's first time hearing this, I didn't watch at that time. But I had a very detailed description of the video. I had some minor information, and I decided it would be an indispensable time for future Alex, to figure out, does it line up with what I'm finding with the material studies? I was studying the negative refraction index, so I came up with this little equation here. And
So the N1 and N2 are the refractive indices. So that just means how light's bending, respectively, the different points on the material. O1 and O2 are the angles of incidence and refraction. So basically that's what I had calculated as highly technical angles and stuff. I don't really feel like I need to get into that or be like overly technical about that. So the metamaterials, regardless, which is what I found, Armour, the toroidal piece there for space-time perturbations, they can have negative refraction indices, and this equation is how that is accounted for in accepted physics. And I was interpreting and expecting far before that that's what it would be like. And for example, blue shift, I had interpreted likely is going to have a negative refraction index, allowing light through the material. As you'll see in my later pictures, you can see fully through it in the blue spectrum, validating my interpretations later with the material science. And on other spectrums, you don't see it. On other spectrums, you see that obviously material is black, and you can't see through it. But yeah, okay, so let's see. Expected NRI, negative refraction index, rendering invisible, basically, or light's able to go through it. I expected as well lensing on red. Lensing is very interesting with this material, and reviewing Christopher's materials, I've found that one of the most interesting things with the filter, and sometimes without it, is you can look at components in a very small setup, basically nano components the size of a grain of salt. And if you focus upon them and shine light in the right way, which I'm pretty sure I have some videos of, I might need to upload or publish later, but I'm pretty sure I have that, it'll repeat the image in the array of the horizontal gravity wave that's getting emitted from that, where you can see the image repeated over and over again. And it eventually cuts off, but you can look at those copies to see greater detail of small components of something that you're working on, which I've been using to engineer a lot, because you can see something super tiny, and I have horrible eyesight. Both of those were experimentally validated by the images you're about to see. So if we could go ahead. Oh, so yeah, okay, yeah. So let's see. These were some predictions. Predictions versus outcome. That's what I'm saying about data and experimentation superseding the need for peer review. It speaks for itself, especially with the self-contained kind of little collaborative think tank we have, where people can cross-verify each other's work and have no predilection to saying somebody's correct. You know, it provides a great way to quickly advance things, as long as you can remove the aspect of needing validation from the greater scientific community. It's great, and also numerically, there's no way to argue that. It seems pointless to me to do things like peer review, but also it slows down a lot. So these were my interpretations, and they were all proven right. Based off of the small amount of metamaterial I had, I predicted that, blue is gonna basically, I said, reverse the polarity of blue light. I guess by that I meant negative refraction index for the things I just showed you. And clearly I have some pictures later where you can see it coming straight through, compared to other frequencies of light where you can't. It comes straight through. And so I spoke on that a little bit. Completely cancels out the purple light. It goes through all the colors of the spectrum, just so we can study the emissions. And these emissions are minor. We're not saying we have a time machine. We're not saying we have a UAP. We're saying, based off of the data we have, it is progressing very, very, very fast, because you can get information like that, small information of small measurement changes, and then build on it very quickly, especially with non-Euclidean model. That last one there, I could explain that, but I don't want to get into the math of that. So we'll, but another one, lensing. I talked about that on the redshift, the opposite of blue. Interesting. Blue has let through light through the material. Red results in that repeating pattern in a horizontal shift when you focus on stuff, especially through the lens, sometimes without it. So that's pretty much it. I put other predictions, but I messed that up. Ignore that. Okay, let's go to the next one. Okay, so now I wanted to have this just be a question mark. The framework I published on is what got me and Christopher. I'm doing that like a grandparent video chatting. But sorry, I wasn't really looking at my camera. But how do the metamaterials relate to the SGUT A3? Basically the theory of everything, the non-Euclidean framework we use. I can say a few things about that I've seen, and I have uploaded on my research page countless examples of. Message me when you get there. Sorry. So my wife is leaving to work. Sorry. But so basically, we have countless examples of consultants or people we work with, myself or Christopher, using those equations to further not only his work but mine. It's easily calculable. We have a published document, I guess, of pen to paper calculations, which is the simplest method available of authentication for that, and it scales all the way up to AI and computation verification. So basically, it's impossible to tell the pull between different vectors that are affecting space-time and gravity consistently with any Euclidean model. So sometimes when we have to verify data or check data, we've been using non-Euclidean models such as that one, which are verified mathematically consistent to calculate what's going on and how to further enhance the materials. And since we have a self-contained method of verification, it's very fast. Like I could probably send an email to the collaborators or the think tank that we're in and probably get a response on how magnetism was affecting the material and how to enhance the material within like an hour. So that makes things very fast. You don't need to get bureaucracy, verification, funding, anything, because a lot of the people involved too have either personal or independent funds or access to funding, and that's been great too. But you don't need that. You can use analog basically systems to do the equivalent, and it's more work and more involved. But I don't believe that should compute to spending more money. And that one of the major aspects of that is these functional non-Euclidean models, which you need to be able to account for both easy, like quantum mechanics. Okay, calculate with it. It should, if you see any model that you're suspecting should work for that, get an output and then compare it to the GR output. The difference should be negligible. Like if you account for the differences between measurement, the difference should be measurable. And there's literally, I found maybe, I'd say 2 to 5 very involved researchers I work with, PhD wise, who have their own versions, and it calculates but only sometimes for specific things. And that's how we've cut down on a lot of the cost by using these non-Euclidean models. And it gives you data that otherwise, if you're using a Euclidean model, would require A, massive amounts of funding, and B, massive amounts of energy. So it's been great circumventing that. And if we could get to that.
Yeah, Alex, if it's okay. So we are at 2:40 now, and what my thought was is that we should go to Chris at the top of the hour.
Oh yeah. Go ahead.
I think you have three slides left, and so I was thinking that would probably work pretty well in terms of timing, if you're okay with that.
How many minutes should I give each one? 1 minute each one? Is that okay?
No, like five minutes each one, maybe, or something.
Oh, okay. Okay. Yeah, I don't even need remotely that much time. Thank you.
Yeah.
So here we got some of the different emission spectrums from this EM stimulated setup of the metamaterials, which does maintain its own magnetic field. Interesting because the material breaks, it's cloth-like, and it's very weird. Because like I said, I was submitting the metamaterials Armour that Christopher developed to stress testing. I didn't think of it analytically at all. Once I did, I got stuff like this. That piece you see on there is, I believe, a breastplate for the metamaterials Armour we have now with all the properties that I had indicated. So here I set on blue. You see an inverse shift from blue to red, and that's interesting because of what I spoke about. Blue is very good for negative refraction index, and red is very good for lensing. So the quick shift between those two indicates a lot of activity that I'm still investigating, and I'm not going to pretend like I know what's going on there. Christopher had said here, detailed as quadruple layering of light, evidence of inertia / rotation. Well, this setup is oscillating and really helps visualize things, especially with the EM going through. Here we have the blue light to purple light shift, evidencing anti-gravity as a horizontal lamination of light. In parentheses there, I put interesting photon clusters to the central left of the image. That might be cropped out, but there is sometimes when you run these on red, weird spots where it's gonna, like, the longer you take a video, even if it's a lens artifact, it will like change really weirdly, and I'm still investigating that. Like, will get very bright, like a dense red spot underneath that emission there for blue light to purple light, the second one. Oftentimes there'll be a really dense, very visible, like basically looks like a laser point underneath it that just keeps getting stronger the longer you record, that isn't visible by the human eye. I thought that was interesting. And I don't know the implications. Maybe somebody here can figure that out. And now we have the horizontal effect of the potential anti-gravity. That's been interesting because, as you can see, it's not evidenced on every single the color shift. It's different color shifts have different properties, and I think people should think more about why the things they're looking at have quantum explanations, and that's kind of what we're doing. We have found that gravity waves are easily imaged vertically. So, yeah, and that's the last picture there. The red and purple spectrum seem to get the most. Blue seems to kind of diffuse it and let stuff through. So I'm still kind of trying to study the implications of that. If we could go to the next one. Here we go. That one kind of looks like a supernova. I'm proud of that one. You can see some hair-like structures there that I thought were photons, but maybe electrons or something undefined. Maybe somebody else can figure that out. And this is what I'm talking about, is some machines take a lot of money to get similar images. By creating materials science, like a way to circumvent that, you don't need a machine. You need you need engineered materials, nanoscale materials, where you can circumvent those machines. And that's what I did. That's what we all do in our little collaborative group here, is try to find ways to get these images to advance experimentation very quick without the need for massive funding or anything. So here we go. There's the yellow to red transition is very interesting, and I'll be honest in saying that I'm still studying that. So I can clearly see, compared to some photonic imaging I've seen, and potentially what they assume is gravity imaging, similar things. There's very fine detail, and nothing was really needed beyond the nano-engineered materials, nanoscale engineered materials, to get pictures like that. And then all you need to do is use the non-Euclidean models to run that. Sometimes, I'm going to be honest, I use AI. I'll run that through AI with the non-Euclidean model. It'll tell me all the implications. Boom, 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 boom. Like, it doesn't necessarily replace intelligence, but greatly aids in it. So that's been a very important part. I can run images like that through AI. We have a proprietary AI that we use for engineering, that I worked with Mark Moody on from the NASA alumni, and it'll spit out, like you can put in hundreds of pages of data, and it'll start working with you very easily on how to interpret pictures and stuff. So that's part of what we've been doing, is running pictures like this through. That's not necessarily my interpretation. It's Christopher's based on all his experimentation, mine based off of my education and experimentation, and then combined with the AI. We only really talk about things where all three of those agree. And then here we have the crimson, white, yellow transition of the light emission. You should be able to see some photonic particles if you make that big. It might be a little messed up. I think maybe the image on the left is better than that. We do suspect that the atoms could be electrons or something unknown, like something dark in nature, and at least evidences for sure gravity and mass, it looks like. So if we could go to the next one. Now, this is the last slide before I give it up to Christopher, but I was hilariously unspecific about my secretary/awesome wife making this slide because I don't think it required a lot of detail, especially with the scientists here. You can see how manipulating these things and controlling them to an infinitesimally small degree and figuring out how to do that mechanically and engineering wise is going to directly relate to propulsion. There's not a single thing I really discussed that couldn't be applied to propulsion in some way by just simply thinking about the equations that would be required to make a system like that. The anti-gravity waves, the photonic emission, all that stuff, it all directly relates, and pretty much nothing here was mentioned that didn't have a relation to propulsion in some way, however roundabout. So I'll give it to Christopher now, and that's pretty much all I have to say. To Curtis, if you want to email us, we have tons of data about detailing those covariance differences and how to account for them in a non-Euclidean model. So yeah, that's available if you need it, and I'm done pretty much. Thank you.
Awesome. Awesome. So you know what? Let me do this. I'm going to bring, let me see. I'm going to add, we don't have that many people with us. Yeah, Jeremy's there. Okay. Folks are just kind of wandering around. I'm going to bring them in as we can. Let's give a giant hand.
He looks happy. He's smiling.
The third. Oops. And there's Jared. We'll bring Jared in. Alex, thank you. Thank you so much. And again, that was build up. Alex has been doing work to work alongside with Christopher Maylor. So we're a little bit out of order, but it's absolutely wonderful. Alex, thank you so much. Thank you so much. And as your guys' work moves forward, I would, love to have you guys back for updates. So what I'm going to do right now is I will take everybody out. Oh, I love Drew's puppet there. I'll take everybody out except for Christopher, and then we will put his presentation up. And then Alex, I'll bring you back in for Q&A if that works.
Oh yeah, he's the smartest of all of us. Let him.
Okay. So Christopher, sir, okay. And let me put your presentation up. Perfect. And you uploaded this, so you should be able to use the back and forth buttons. And it looks like you got about 20 slides there. So what I will do is take myself out. Your voice has been a little faint. If you're able to speak up or move the mic, that might help.
I'll do my best.
Thank you, sir.
Okay, so my name's Christopher. I'm not used to talking to people. It's the first one of these presentations I've done online. I tend to be in the lab more researching and experimenting. So I set up WTRC 4 years ago. I've been working to develop a functional warp core for seven or 8 years now, and I've gone through multiple stages of development to get to where I am. So basically, my field of expertise is in distortion mechanics. I don't use conventional methodologies to develop toroidal systems. I use a means of distorting the current as it travels from point A to point B to generate an effect, and then I apply that effect to keep an equal opposite effect to generate a new distortion effect, and I employ those distortion effects to build a warp core. So I know it sounds complicated, but it's based on fields instead of currents, and that's the best way to explain it. So I'm looking at distortions within fields. So you have an electromagnetic field, which is quite fluidic, and then it's about generating a variable within that fluidic field to create an impact that will benefit you towards the object of your or purpose that you're driving towards. So in my case, it's a warp core. A warp core needs to generate a warpage, and that warpage needs to generate an effect. I use quantum energy, quantum technologies to power my warp core. It's not powered by any man-made electrical system. I don't use electricity, I don't use litho batteries or lithium batteries or any other power source. Everything comes from the subquantum. And I think that's a very critical start from where I'm going. So if we move to the next slide. I came into physics on a tangent. I was working to develop a new type of ground penetrating radar system to detect skeletal remains. Skeletal remains are neutral materials. There's no iron in calcium or in bone. And that's a reality. So you can't detect bone with normal ground penetrating radar systems. So I worked on developing a new type, going through saturation theory into elongated magnetic field theory, where I elongated the magnetic field 10.5 meters. And then from there, I moved into warp technology, where I distorted that elongated magnetic field to produce the world's first warp field. At least, as far as I know, it's the world's first one. So moving from there, I stuck with that with the Beetlebomb project. So the Beetlebomb project was the very first true warp core I built. And it's the first warp core to displace zero inertia, which is a sphere of neutral energy. It's not true energy, it's more like entropy, if you like. When you displace that from a field, from the warp core, you generate elliptic slices. Those elliptic slices are split into two segments, one and then a second one at maybe 2 or 3 meters apart. And they're quite large, you can stand inside them. Within those fields, there is no energy, no electricity, no magnetism of any kind. You read zero using an EM field detector. So for measuring radiation or measuring your television, your computers, the space you're in, that's what you use, measure the electromagnetic field. Inside that zero inertia field, there's nothing. And any radiation in your body is removed. So, you know, it's a really useful new advance for medical fidelity. Beetlebomb was the first true warp core to be able to do that. It's the one that's led me to where I'm standing today. I have developed a lot more than 70 prototypes, but I lost count a long time ago. So WTRC used it. We're approaching this from a completely new perspective. The warp core, which is quantum-based, takes energy out of the quantum field. We displace zero inertia to create a zero inertia bubble. At the parameter of that warp bubble, there are two fields. One of them is an EM field, which is the symmetric asymmetric electromagnetic field. The second one is the zero inertia distortion field, where all the energies have been compressed to the parameter of the warp field, the warp bubble, and they're rotating. But as they rotate, they generate new exotic distortions within the field, and that's the best way to describe it. Within the zero inertia pocket, where there is no radiation, no electromagnetism, no damage, no harmful, there are some displaced quantum particles, and they're called quantum dots. But very recently, we have evidenced these as quantum stars. They are spherical, they have an axis, they rotate, and they have a corona, they emit mass as ejections, the way the sun does. If you look at the sun, when it emits, it fires out plasma from the sun. That's the same thing as a quantum dot, which is a quantum star. And what the implication is, when you go subquantum, there is a quantum universe. And we don't really understand the quantum dot totally yet, but my perspective is within the quantum bubble, the bending space, and that quantum dot as quantum star is connected to the meta universe. And I don't mean anything to do with Google or their metaverse. I'm talking about our universe, our cosmos. So I think these quantum dots are tied to those stars, and that's part of my research, is looking to see if there are any objects moving around them, which could be classed as planets, if you like, subquantum planets around these stars. If there are, then that establishes something very important, because that means there's a possibility that these quantum dots are connected to the stars in our universe, the universe itself, which means if you pull on these quantum dots, you move from here to that star system, and it's done instantly, which is why you have this field, which is why you have a warp field, and it's why I'm researching metamaterials which interact with that warp field, and part of my research is about developing a metamaterial that is collaborative and works in harmony with these warp cores to achieve an objective, which is to go, obviously, beyond our solar system. So this is very intricate and complicated research. It's diverse. There's lots of fields. I interact with many scientists around the world, connected to different aspects of this, and they relate to zero-point energy as quantum energy, something I've achieved, and evidence powering different devices, motors and lasers and things like that. So the warp core I'm currently building is called Armour. It's an ancient name, goes back to Ireland and the indigenous population. We shall move to the next slide and we'll carry on with this. So these next slide, this is to do with micro warp cores. The micro warp cores are part of my research. I use them for geometric amplification and to study the geometric layout of the EM field and how you can apply it. And there are different ones. This is the very first warp core on the planet to produce zero-point energy that I know of, has a direct voltage. So it only produced 1 volt, it's the start. And from there, you go to the other warp core, micro warp core, which produced 98.6 volts. And that visibly shows in the image LEDs and the laser being powered. And that's mostly through a thing called negative induction. So with negative induction, if you think of the nuclear power plants producing a positive energy, there's also a negative energy underlay beneath that field. And by tapping into that negative energy through a single Earth connection, you can draw quantum energy out of the quantum field to power other items, other devices, like the laser, like the LEDs, and any motor that most of them are powered with, like a couple of 12-volt motors and lasers and a few other things. But we started, it's a new piece of research, it's new innovation, and it's a process. And solar power started somewhere. It's taken a long time for them to get to where they are. Same goes for nuclear power, same goes for everybody else. Zero-point energy is just starting, and it has a long way to go. And the fact that we can draw upon zero-point energy as a current and the empower do small things, it means it's refined. And from here we can move forward. And the same goes for the warp core, the same goes for everything else. The second image on the slide, that relates to quantum particles. And looking at the space around the warp core with diverse cameras, I have 22 different cameras looking at this thing. You can see them in different lenses and under different filters and different types of camera, and they can evidence multiple changes within the atmosphere, because this is a zero inertia pocket that I stand in. There's I'm quite healthy in this space, but what you can see is an environment that is quite exciting. All the particles display quantum light, and that comes from the quantum field. So you can see 0-point energy has been triggered by quantum light, because you can see it flowing as a fluorescent transmission, which is very interesting. And I'm studying a great many things connected to this, along with quantum dots, quantum stars, because it's all part and parcel of the process. It's one of the reasons why maybe some tic-tac-toe, unidentified alien craft may be emitting some light colors. It may be connected to quantum displacement. So as the field expands, as the zero inertia field expands, those colors become displaced further and further from the warp core, maybe to the outside of the warp core, outside of the warp field. And that might explain some aspects of this. So, unlike other theories, I'm not relying on just a warp core to achieve warp propulsion. The warp core itself is it's not necessarily a power source like a rocket engine or anything like that. It's far more advanced, and you have to think of it in a far more advanced way, where the quantum energy interacts with the meta hull to achieve a status of symbiosis, and together they form another reactive state that lets you achieve or propulsion, or as for his name, I think it was Kurtz. I think Kurtz was touched upon temporal distortions. Well, part of the warp field does generate temporal distortions, which are quantum-based gravity impacts. These quantum-based gravity impacts can mean that in the future, I am experimenting with temporal control. I've been able to adjust time distortions on atomic clocks, setting back to neutral, to zero, and then we're working now to see if we can accelerate those time distortions, which are currently running at 1 hour and 24 seconds forward and 24 seconds past. The past atomic clock was adjusted back to zero, and I lost the 1 hour 24 seconds when I realigned it to the National Physics Laboratory and corrected the time. But since then, it has recovered another 24 seconds backwards in time. I'll just check it. Yes, it was Curtis. I have to keep notes because I'll forget. So Curtis did touch upon time. Time is linked to gravity, and it is linked to the quantum field, which I'm evidencing. You can adjust time. I've been using 50 and 500 hertz as resonances to try and change time, but it's only touched upon time past. I haven't been able to alter time forward, which is something I'm still working on. So this is not a simple process of building a jet engine. It's quite complicated, but if you want to achieve an anomalous action like a warp propulsion system or a UAV or something, then you need to move out of the normal realms of physics towards something a little bit more exotic. And by taking this approach, I've been able to evolve the warp core from a toroidal system, which was quite simple, to something far more exotic and advanced. And when I first started, the only person in the field that I knew of was Harold Sonny White with NASA. He used a very simple toroidal system. There's basically a round bar with some copper wire wound around it. I've gone way beyond there and developed hundreds of different distortion-based toroidal systems, which are a variable. You could say the simplest one is to merge Harold White's round bar toroidal capacitor with a Casimir experiment where you use two plates. If you put a layer of copper between them and then wind that around with copper and then merge that with Harold White's toroidal system, then you have a distortion toroidal system. And expanding on those, you can achieve a little bit more than a standard drive system. And I think it's quite important to explain those advantages so that other people can experiment with them. Because it's not necessarily about how quickly a current travels from A to B, but how it travels from A to B, and if it can generate another impact or another influence as it travels, which is how I'm approaching the field of quantum mechanics. So within this, the field is quite extensive. I look at everything, I examine everything that crops up, and there's loads of new things cropping up every single day. With the metamaterials, you generate anti-gravity, gravity impacts, you generate some electrical currents. With the warp core, it's very similar, and the waveforms between the two are matching up very quickly, as are the resonances generated by both. And that's part of the symbiosis process. You need something that will work in harmony. And then ideally, once these items are built, so the warp core is completed, and we have a fully functional, fully built, full-size meta hull within the parameters of the warp field, the pilot should be able to interact as a symbiont person between the two components to generate a warp drive or a temporal displacement. And this is the theory behind the process that I'm approaching and the direction I'm coming from. So there's a lot of new technologies, there's a lot of new experimental developments, and most of which haven't even been studied by other people. I have a massive data for quantum dots that I haven't analyzed myself because the time it takes to edit all the videos, which are taken in a completely blacked out room. You can't see anything but black until you edit them, and then you see quantum dots. You see the infrared in the warp core, and you see any other anomalies in the space around it. So you might see a temporal portal. It's not really a portal, but it's more like an orb. But it's that's connected to time, and within that temporal or sphere, there is a distortion because it separates two times. There's time forward and time past. The biggest experiment I've achieved with that so far is moving past time to the opposite side of the warp field. So where it was negative time, positive time, it's now positive time, negative time. And that's when I cancelled out the 1 hour negative incursion into the past. So I research and I experiment every single day. I've included videos in this presentation so that you can go onto LinkedIn, where I release most of my videos. These are of experiments and evidencing then every reactive state. So if I'm working with negative induction, I evidence negative induction like I'm doing behind me. This is a reaction between two metamaterials. One is a brand new reaction plate, there's a pair of them, and these are to measure the warp field. And I'm looking for anomalies within the warp field, which will then advance my research forward. It'll also then impact upon metamaterial development or a meta hull. which will also advance. I developed my own sensors for this, and these are nano sensors. They're ultra small, size of a pinhead. You know, they're really small, very thin. They're designed to go between each laminate. These are micro laminates and metamaterials, so they are literally this kind of less than a millimeter in thickness. And you have 64 or so laminates, and they are intensely compressed to achieve the metamaterial structures that I'm working towards. I use them for metamaterial for meta-hull development, and I'm using metamaterial body armor to advance meta-hull development. So as I develop a process to refine materials for body armor, removing radiation, they're really good shielding for radiation. If there's ever a nuclear attack, then that's what you want to be wearing. Great for in space because they were designed to protect you from EM radiation, solar radiation, cosmic radiation, and they are a really good shielding. The experiments Alex was doing was testing them to destruction. I wasn't expecting that, but they were designed to take micro impacts from microparticles in space. So it's nicely survived, and he was using X's and all sorts to have a go at them. I believe in quantum tethering, so I think the subquantum field I'm generating in this warp bubble is connected to the macroverse, and I do believe that the quantum dots, which I've evidenced as rotating stars, quantum size, obviously, showing that they're formed out of either plasma or gas, and maybe in some parts they are solid. They are maybe have mass like some type of larger body. I don't know. It's not my field of expertise in astronomy, but I would say the physical body. Maybe that's the best way to explain it. Some of them may have physical properties. I don't know. This is just a new discovery within the past couple of months. So until now, no one's ever seen the quantum dots. They haven't been able to photograph quantum dots until I think it was February 2022 when I released the first one, where I achieved the first quantum dots. In the past 2 months, I've been able to record a quantum dot rotating and evidencing star-like behavior, and that's why I refer to them as quantum stars. And I do believe there's a quantum tether connection. So that might support then quantum mechanics as a science. But we'll see how we progress, because the warp field is in theory, a magnification system. As normal space folds over the quantum field, then you should see the universe in a whole new way. And that's where it's possible that quantum dots are simply reflections of our universe. And I am looking to look for constellations within the makeup of the quantum dots. I have seen some close proximities, but nothing that matches exactly. It's still work in progress research. You know, it's just relentless. So we talked about quantum dots, so we can skip past the next one, because I think I've gone from there. The quantum bubble is the zero inertia field, and it does displace the radiation. I could get a radiation detector and evidence of that, but the computer in front of me, 400 millimeters away, I suppose, the radiation coming from that is a third of the radiation coming from everybody watching this video, this program. Their computers display higher levels of radiation, and that's because of the quantum field I exist in, this zero inertia displaced field, which extends 3 meters and 6 meters, okay, 4 meters and 6 meters. So it's more oval, like an American football ball, a football or a rugby ball in shape. And this is very important. I need to measure all these parameters, which is why I'm developing the reaction plates. So then I can design the metal hull to a higher specification and the right shape to fit the parameters of the field. But it has to fit inside this warp field for it to function, and that generates then the symbiont connection between metal hull and warp core. So the next slide, we're moving to two beetle bombs, first one and the second one. First one was for archaeology. It did succeed in detecting the skulls remains underground, but it lacked range and it was radioactive a little bit, within 1.5 meters. I've since removed the radiation from the system. The new warp core, you can get within 100 millimeters of it before the radio detector starts to alarm. It's very low levels of radiation and really, really safe. The second black beetle bomb, that was the next stage in the evolution, and that the warp core that preceded the Liana warp core, which generated a significant amount of 0-point energy, 98.6 volts. I stopped the research at that point because it's all about funding, and my priorities are, although they're diverse, and I do try my best to research multiple fields, there's a limit to how far you can go within those fields without a serious amount of resources behind you. The only thing I would say about 0-point energy as well, I only researched it in the first place because of a professor in Australia called Robert Pope, with the Science Arts Centre of Australia, and he asked me to focus on 0-point energy for the world's sake. But I wasn't really interested because I was looking at other options. I'm looking at wormhole generation, I'm looking at warp propulsion system and temporal displacement system. I'm looking to develop a system that can take you from this planet to a planet around another star almost instantly. And this is the direction I am pushing towards, which is why everything I'm doing is intricate to the actual central warp core, and that goes for the metamaterial research, for the metal hull and the body armor, all the sensors, everything. They're all either metamaterial based, nano based, or quantum based for the same purpose. And it's all about advancing the research. Every prototype leads to the development of another prototype, and that prototype is always more advanced because you have to learn as much as you possibly can from the work you're doing. And even if you have a negative piece of research or evidence, you must absorb that, take it on board, and look at why it failed. And it's through those failures that you advance, because you find new discoveries within failures. And it's always a good resource and ability to embrace those negatives and turn them into a positive way of moving forward. And it's only through those failures and hurdles that you can actually achieve your objective. And I think it's a very important learning lesson to recognize that there are lots of failures before you succeed. In the next slide, we see 3 different micro warp cores. I've already shown you the micro warp core. The one beneath it is a Liana warp core, which evidences 0-point energy. The Riffin warp core also evidences 0-point energy. 98.6, the same as a Liana, with a negative induction. And I put these in because I wanted to display that without any technical advance, without any really difficult, complicated technologies, you can build a warp core that generates small amounts of 0.10, which is free energy. So for places like Africa and third world countries, this is research that people need to consider. At the center of the Lian warp core, I have a micro warp core, and that's generating stimulation. There's a spring action taking place. It's like a flexible EM field, if you like, or a flexible EM thread, and there's a rebounding action generates the current in the endpoint. The negative tether to a negative vortex or an earth that actually draws upon the 0.10 to generate that current. You can go beyond them. This is the Anu warp core. On the next one, this is the most advanced one, the one I'm working on. It's the second generation. The first one was toroidal. This one is cyclonic. It's wired, so I can actually take all the wiring to piece and rewire it again to make it into a hurricane type drive system, which would be a lot more aggressive. I haven't done that yet. I'm apprehensive about that. This warp core, as it stands now, is a fully functional working warp core. It displaces zero inertia field between 4 and 6 meters. It's still waiting to get 2 more warp rings. These are very special gravity inducing warp rings. They generate a friction plane, and above them will be another 3 warp rings, both on the symmetric field and the asymmetric field, to complete the actual warp core. And then after that, I can start really experimenting and studying the warp core and all the benefits and effects that come from it before I start to consider moving on from that to a new generation of warp core, or simply accepting that it's at its limits, focus on the meta hull. The meta hull will amplify the warp core, all the energies and the quantum energies and the EM fields and the zero emission field coming from that warp core will be amplified and magnified by the meta hull because of the reactive materials I'm working with and developing to achieve this object. All the meta hull materials are very specifically designed to interact with the warp field, the quantum field, and to generate this advancement, this amplification, and potentially displacement. I won't discuss those in detail because they're sub-classified. I'm working on all the technologies all the time, and nothing is patented because they're all experimental prototypal research endeavors. So this is quite an advanced warp core. It's the most advanced to date. So we talked about electromagnetic fields, but they are a good way of explaining the electromagnetic fields is to think of them as shears. And if you have 2 shears in close proximity, and if you think about that as the Casimir experiment, but instead of using metal plates, you're using energy planes. And it's this that you're working towards with distortion mechanics to generate a new distortion between those 2 energy planes. And this is the thing that's pushing forward the warp core development that I'm working on and the research I'm undertaking, which is quite extensive. So that's the thing that's going to generate the warp propulsion system in the end of the day. It's these the distortion mechanics between the warp core, the meta hull, the warp field, all of them coming together to achieve an objective. So this is the symbiote part of the experiment and the research being undertaken. I have evidence considerable amount connected to this, so the quantum dots, the zero inertia displacement, the resonance is coming from the predecessor of this warp core as a resonance waveform. All of these, which are online and you can hear them, evidence the path I'm taking is the correct path. What's something I was going to say? I completely forgotten what it was. It's gone out of my head. Sorry about that. The resonances are a vital key, but the new one, new resonances, since I rewired this multiple to make it into a cyclonic system, those resonances are now inverted. Those inverted resonances within the warp core are generating the temporal distortions at the parameters of the warp field, and they didn't exist until then. So this is something new. Temporal distortions also, I should point out, have existed in some of these, have been captured on camera. Yeah, and you're conducting an experiment that takes like 30 seconds, and your recording lasts for 30 minutes. You don't know. You have no idea that you're in that temporal distortion. For you, it's a couple of minutes, couple of seconds, couple of minutes. You know, it's very strange, very surreal experience. I have quite a lot of evidence for this, and I did release some on LinkedIn. Some of them connected to experiments I did for university, even down to just staring water, and you go from normal speed, and as the zero inertia field rotates around, then so does this quantum wave, and this quantum wave generates this temporal distortion, triggers it, and you suddenly just slow down to a very slow cycle. Voice commentary within the video disappears. It's elongated, stretched out, but your actions are slowed down. The reason why there's no sound in those videos is because there is narration there, but yeah, time distortion. It's a very weird thing. No side effects because the zero inertia field actually protects me within this space. And I think that's quite an important thing for anyone to consider when they're dealing with time or when they're dealing with very substantial EM fields or radiation. They need to shield themselves. Zero inertia fields are a good way of going about that. With the spacing half or EM fields and radiation from the space you're occupying. And you need to consider these because long exposure to EM fields it can be harmful. You can get cancer. So you should think about this. So we can move on from there, I think. So the next one is toroidal capacitors, generated for core and distortion mechanics. I've got a couple of samples of here. This one is a metamaterial toroidal capacitor. It's really advanced. And it's tear-shaped. So the second one is an earlier version. This is a binary system. So I developed the tear-shaped system, which is metamaterial, and I'm using an aluminium and copper, wound in copper plate. I'm also using Fe3O4 inside the aluminium to generate a distortion, and then wound in copper in multiple stages of copper. So there's probably 3 layers of copper wiring attached to this particular toroidal capacitor. These are the most advanced, the ones displayed in the actual picture. And these include a negative induction, which is just something new, really at the cutting edge. So with the new anode warp core has a negative induction wiring system built into it that interacts with the toroidal system. Hopefully at the end of the day it will generate a significant 0-point energy outage as an additional outage. At the moment the warp core is using all the 0-point energy to achieve its solid state at the moment, so it's achieving what it is doing it uses more less energy for itself. But it is a complicated piece of technology. The torus itself is unique. It's non-standard. It's not like anything that any other physicists have built. They normally build the same standard ones. This is nothing like that. It's a really advanced system. And it has diverse toroidal systems in there, far more complicated than the ones I've displayed. Some of them are really, really elegant. Could be pieces of art, they're so elegant. I use very specific nanosensors. These are a small display of what I use in the next slide. I use butterflies, and they are basically 3 plates. They're microscopic, ultra thin. One of them is 24 karat gold, one of them is aluminium, the other one is metamaterial. And I can place these within different layers of metamaterial to generate a reading. I can generate multiple readings from them because they are that advanced. I can read the any electrical current being generated by ZPE. I can record also then the EM field, any anti-gravity, gravity taking place within these metamaterials, or within the warp core, or within any of the body arms. So they're quite really advanced and very unique. Very, very small. I mean, no point in putting one up to the camera, you won't get to see it. So really, I'm using ultra fine wires of thickness up to over human hair. As I stated earlier, the metamaterial body armor, like this sample here, which is flexible. I use a very special metamaterial called Ferrex. Ferrex restructures all the metals within this and all the other materials as well, because this is not a true metamaterial, and nor any of the metamaterial true metamaterials as a solid state metamaterial, like this tri-state system. These are partially organic metamaterials, and they have a very unique set of properties that were designed for my objectivity. So I really was looking at shielding against radiation in space, looking at harsh environments, and how best to protect people within those harsh environments. These are really complicated and they're quite expensive to produce. There are 3 or 4 layers of Kevlar in there as well, so it's just an extra bit of defense. But all the materials are really, really durable and designed to the best of my ability to protect anyone using them. The sample panel of metamaterial, just to give a rough idea of the type of research that's gone in, and these start with very early experimental research, like this piece of metamaterial here, which is the very first multi-laminate sample I produced. This is designed for the meta hull. This is the original sample, and I've gone from there to ultra thin samples like this one, and to these really ultra thin metamaterials like this one here, which is a really solid metamaterial. It generates gravity and anti-gravity within its field, which are they are not compressed under an even pressure. It's better to apply multi-pressures, and that can lead you to generate multiple impacts. So I think it's really useful to explain that if anybody is thinking about going this kind of experimentation. The properties are really anomalous in most of these materials, and I use diverse materials. I am concentrating recently, now that I've achieved enough on my own metamaterials to achieve what I want, to focus on those and pursuing my objective, which is this year I'm aiming to build the very first section of a meta hull so that I can test interactions with my warp core. And this means a full-size piece of warp hull, and then bringing it into close proximity to the warp core between 4 and 6 meters and looking at interactions. The reaction plates I'm developing are part of that process. They're part of the process of measuring the EM field on multiple levels. They're really complicated reaction plates, and they have the potential to draw energy out of the exotic warp field I'm producing. But that's experimental. I haven't tested it, so I don't know if it'll happen. But it's just an idea, and you have to test these ideas to see if it's possible to stimulate energy out of an EM field. Something unique, but worth pursuing. And I think we need to look at energy in multiple ways. So if we move on, you can explore any of these links. And if there's anyone who's a true scientist and they would like to look at quantum dots, we have editing software for videos. You get in touch and I can send you raw data. There'll be a couple of videos because they're really large. They take up a massive amount of space. Maybe 1.5 gigabytes of video. But you can edit them yourself, examine them yourself as raw data. And I don't mind sharing that. Because this is something really new, it's interesting. Some of the videos may not show quantum dots. They might just show radiation coming from the warp core as a heat signature, which is very, very low. Because I've been working to work in harmony with the universe and not impose myself upon the universe. I believe in equilibrium. So the warp core uses quantum energy because I don't want to extract them from the energy, from the universe. That energy travels through the warp core and back into the universe. And it's done as a series of 2 quantum bubbles, but they're not true bubbles, they're actually uprises and downrises. Best way of explaining it. So you have an upswell and downswell. This is what I'm aiming for, and we're generating 2 quantum fields that have a downswell and then an upswell, and it's this waveform that allows me to achieve what I'm aiming for. And I have spoken about this in all my papers. There's very specific waveform and there's very specific frequencies I'm aiming for. And all of these are now being evidenced with what I'm doing, along with some very new waveforms. And one of those, I think, is Mark Moore's pilot waves, which I'm getting as a recurring wave, a resonance wave, through the oscilloscope, and diverse other resonances as well. The resonances have changed a great deal since the new wiring system. And you have to take it on board. Things have changed. And the other resonances that you couldn't normally hear with your own ears, they are now out of the picture. They are really embedded in the upper side of that warp core, going into the subquantum. They're not coming here. So all the links on this page, they're basically to do with evidences. So you can actually go and examine ZPE, the light displacement from ZPE, and the quantum stars, and the other experiments I've conducted over the years to do with zero-point energy and development of the warp core, and that includes the other warp cores that preceded it. So this one is again the warp core, but this is a normal picture, it's the wrong way around. This connects to the time distortions. I'm using atomic clocks. I'm using 5 atomic clocks. There was a 6th that broke. But the 5 atomic clocks, 3 of them measure actual time, and that matches up with the computer and all the other timepieces. I have other atomic clocks that to support this at different locations away from the warp core. The two recording the actual temporal distortion are slightly out of phase with the National Physics Laboratory's signal. So that's why that signal isn't correcting them. And I have done a lot of research and switched them around to verify this. That's quite an interesting piece of evidence for potential for time travel, but we're not there yet. It's a long way to go, I think, when we get there. Maybe when the meta hull is built, we'll have more evidence to support more anomalous reactions, which will relate to time distortion and space propulsion. But there's still a fair way to go, and lots of research and experimentation to take place before that. But the Armour warp core is only been around since 2002. It's evidencing itself really, really well. Taking me leaps forward, where I'm having to come to terms myself with all these new advances ahead of everybody else, trying to make sense of some of them. And this is something you need to think about when you're going into advanced research. You need to be able to try and get your head around what some of these impacts are. I set out, I think in 2001 or 2, I think I spoke to Jackson McCarthy about this temporal distortion and trying to create them. And I think last year I just hit the nail on the head. And it's just been advancing since then. So I record these temporal distortions every single day, and they're advancing at a ratio of 1 second per 36 hours, forward and out. I'm very interested in temporal distortions as well, and in controlling them, because it's that control that's going to lead you to achieve time displacement. Which want to travel to a different place, a different time. You need this, and you need to understand how to manage that time forward and out, because there's no point going to a time in the past or in the future and not being able to get back. You need to manage it, you need to control it. And some of the research I'm doing connects to this. And in part, Mark Moody's research, I experiment with that to see how it impacts on these time distortions. And it's through his one-on-one pilot wave that I've been able to adjust time, although it wasn't that particular signal, it was a different waveform I was using, but I was with different resonance, I was able to adjust time backwards by realigning it to the current. And that is an advance. The only other thing I would say about the pilot wave is 1.01111 increases quantum dots within the warp core and the space on it. And that was also another interesting piece of research and experiment which I've been able to evidence. The photos for that have been released. I use 22 different CCTV cameras, digital, and I use Olympus cameras, OMD EM1 cameras with infrared to examine the quantum dots. I put those quantum the videos on the quantum dots then onto my computer to edit them. All I do is raise the lighten them, so I can actually see the quantum dots. If they're a video, I will use my iPhone to record those quantum dots under magnification, and then you can actually see the rotation. There's no trickery involved, it's quite simple science. And as Alex said, you don't need multi-million-pound pieces of technology. Advancing very well with a couple of oscilloscopes and various other pieces of technology, which are quite low cost to achieve everything. I think the best piece of technology I have is my radiation detector, which I use every day. and the EM detectors and various other things. Numerous my brain is going dead. System to monitor resonance and wireless communications and anything else that's taking place within the space. I have to do that every day and keep a record. So this is just one of the processes that's part, and you spend half a day just doing these small experiments and small registers of recording of everything you're doing to keep a log of everything for the future. So go up there. So these are some of my collaborators. I work with these. I'm very fond of these researchers and independent scientists. I have plans myself for Dr. Alex Wolf. I'm hoping he's going to end up working with me on the Meta hull, and he'll be the lead scientist because he likes destroying things and pushing them to their absolute limits. And I quite enjoy watching him do that. So it's very interesting to see how he reacts when he discovers new anomalous things and how he then explains them. Sometimes not the way I see them, but it's very interesting to see how young people absorb information and how they rationalize it. I try and share as much information as I can with all the people on this list. And I'm quite happy to connect to other people. And when it comes to the quantum dots and the information I'm not able to analyze because I don't have the time in the day, then I'm quite happy to share those raw data. But when it comes to the warp flow technologies and the very specifics connected to the technologies, I'm unable to share that. Some aspects to do with the metamaterial development, because these are non-patented prototype technologies. I fund my own research from top to bottom. I have no support from anywhere, so this is all privately funded research and experimentation. And I just believe that somebody needs to build a warp core that works so that we can get to where we need to be on another planet, or thousands of planets, or 8 billion other planets, and build a better future. And I think that's it. Done. We lost Tim. He's fallen asleep.
No, I am here. I am here. You're all set. You are all set. We only have about 8 minutes left. So let me do this. I'm going to bring everybody back in. And actually what I was doing was just updating the website. And let's see, I'll bring Alex back in. I think that's pretty much everybody who was here with us. We have a few folks that have blanked out their cameras. There's Jared. Okay. And everybody, please give Mr. Christopher Maylor an enormous applause. Enormous. Christopher, thank you. Your audio was very faint, but I know that you're new at presenting. And I didn't want to disturb you. It was wonderful. It was a wonderful presentation. Thank you so much. So we have about 7 minutes until it's time for Shiva to present. And Shiva, again, thank you for joining us and being patient. Do you guys have any questions for the next few minutes? Yeah, Curtis, go for it, sir.
Yeah, so one question I had was in terms of the effects you're measuring. I caught that you have you're measuring with atomic clocks some time effects. Did you measure anything in terms of inertial mass? Were you able to do any measurements of that?
I measure the field on a regular basis. I'm looking at the parameters of the field. I'm looking at the internal setup of the field. So the zero inertia field on the inside, I look at then the EM field on the outside. The actual mass you're talking about, that's to do with the actual warp field itself, which is difficult to measure at the moment, which is why I'm building these reaction plates. The experiment taking place behind me is connected to that. It's all about producing a metamaterial plate that is sensitive enough to measure a flux field, but it's a large flux field, and that's how you have to see a warp field. It's a state of flux. It's not a regular PEM field. It's watery in a sense. And you have lots of friction within the field because there are two fields colliding. One's rotating, and the others are one's symmetric, one's asymmetric. So it's a complex field.
Okay. The follow-up question I had was: is the field you're generating at all related to the Mach-Lorentz thruster that was kind of researched by NASA several years back? The MLT drive, MLT experiment?
The only NASA experiment I know of connected to what I'm doing was the one that Harold White undertook when he first he tried to build a warp core. He tried powering it, and it didn't quite work. I don't really engage with other researchers. I'm so intently working on my own. It's like my head's down. I do that every day, every single day. You can't read every paper that somebody sends you. It's not possible. I'm not a theoretical physicist. I don't teach in universities. For that reason, I'm an experimental physicist. I know what I do with these experiments every single day, and they think it would be forward.
Understood. And you're using a rotating magnetic field?
I'm using a distortion field. The rotating aspect is the displaced zero inertia field. That rotates. So the zero inertia is rotating at 3 to 4 cycles per minute through the space. Okay. And it's pushing all the radiation out and everything else. And that's how it works. And then you generate friction on the other field. Does that make sense?
Yeah, thank you.
Wonderful, wonderful. So let me see who else has questions. Again, we've got about 4 minutes left. And if nobody does, I'll tell you what, why don't we do this, guys? Why don't we give Chris a final applause? Christopher, thank you.
Sorry, I was focused on something else for a moment.
There's Michael. Michael with his bad camera. I'm gonna tease you about your camera again, Michael.
So what's the working theory here? What are you actually doing with this? Yeah, just like as a first thing, like that. Yeah. What?
My research involves distortion mechanics. I'm using distortion mechanics to build a warp core that uses quantum energy, no other energy source, just quantum energy. The quantum energy displaces zero inertia out of the warp core. The zero inertia rotates, and it also produces two fields. One is the parameter of the zero inertia field, which is like an exotic EM field.
What do you mean by zero inertia? How zero inertia rotating? So is that like a geodesic or something? Because like angular momentum is angular inertia.
It's a zero inertia field. It rotates at 3 to 4 seconds, 3 to 4 times per minute, and it interacts then with the asymmetric EM field, which is an intense EM field. That's where the radiation goes. It's transformed into partially energy, partially an electromagnetic field, or quite an intense one. And that gives me then the range, which is at most 6 meters.
So what do you mean by asymmetric fields here?
You have two fields emitted by the wall. One is above, one is below. But in addition to that, then you have the zero inertia displacement field. And as it rotates, it displaces any energy within this field to the parameters of the EM field, or the zero inertia space, if you like. And that generates another field, which is an exotic field.
Got you.
Even
okay.
Dots go to that parameter.
I could see how there might be something there, maybe. All right, cool. Awesome. I guess I'll just take a look at the numbers they got.
Well, and guys, we are just
I
about
would
there.
I
So
would look up the. Go ahead. Sorry.
well, actually, what I want. Oh yeah, sorry. Go for it, Alex, and then we'll wrap things up.
Oh,
here.
sorry. I just had a. I was just gonna tell him too. If you on Chris's part, mainly a theoretical discussion. If you need any of the technical details, because the time constraints, I would again direct you to the research page. Not only does it have the non-Euclidean model we use for full, like if you even emailed us, we can give you all the numerical values for all the equivalents of that. And the process is occurring. There's just not enough time here. I tried to go over as much as I could, but
Awesome.
Sounds
Well,
good.
guys, let's do this. Let's put our hands together one more time for Mr. Christopher Maylor as well as for Alex Wolf III. Both of you gentlemen, thank you. Thank you for presenting at APEC. And we'd love to hear updates as your guys' research moves forward. So what I want to do now
Thank
is
you.
I'm going to take everybody out, and I want you guys to pay close attention to Shiva Meucci. I'm sorry, Shiva, and I just took you out of the studio. Sorry.
That's all right. Nobody gets it right on the first time.
Yeah, I'm having mouse issues today. Okay, so there's okay, perfect. Now it's just you and myself. Do you want to try and upload your presentation, or do you want me to upload it
I
for
don't
you?
have a really current slide deck, but I've been doing this for about 20 years. So you know that I can
Yeah,
do
if
this.
you want to just speak, that's totally fine.
Yeah. Basically, okay. So just to let everybody know, I sent Tim one of my most concise papers that I published, basically on the history of modern theory, and this is going back to, well, especially there was a period of time from 1887 to 1905 that is especially critical. But before we get into that, I kind of wanted to point out one of the things that everybody is sort of wondering about, and that is, okay, if we've got these models of physics that are down to 12 decimal places, perfect prediction, but then at the same time we've got something like the vacuum energy catastrophe, where the difference between what is predicted and what is measured with our current theories is let's see if let me bring up this little phrase that it was put in. It's so great. It's a factor of 10 to the 120th, a factor of a million, billion, quadrillion, quintillion, sextillion, septillion, octillion times. So that's the difference between what we detect and what we predict with our current model is a difference that is larger than comparing one atom to all atoms in the universe. So how can we be both just really perfectly on track and so incredibly, unbelievably far off at the same time? And so before I get to the history of physics and how it is that we can look at various analogs, I want to talk about the very idea of an analog and limited truths. And so one of the stories I like to tell is the story of the fishing tree in Papua New Guinea. You can go to Papua New Guinea, and there's a tribe of people who they pray and sing to the fishing tree and to retrieve fish. And during this ceremony, it's a replicable experiment. So therefore, there is a science to it. You can watch them do it, and they will always retrieve fish using this ceremony by appealing to the spirit of the fishing tree. Now, that is a sort of truth within limits. And what I mean by this is they are using a theory about a spirit. And when we go and investigate a little bit deeper, we find that there is a neurotoxin that is not toxic to human beings, but is toxic to the fish, that is in a root that is a part of the procedure that they are using in their experimentation to achieve the desired result. So they have a type of truth, they have a type of theory, and they have replicable results that are basically a type of science. So the fact of the matter is we can do this same thing in modern times in a much larger way. And what we do is we produce an analogy to the truth that is off by a certain amount. And the reason why we can do this so well is because of mathematics. In other words, there are mechanical ways. Mathematics works like a machine, which is the first computers were Babbage's difference in analytical engine, and those are made with gears, etc. And it's because mathematics works like a machine. And so without knowing necessarily what the machine is doing, you can continue to hook things to it to make it do more things. And so that's the way in which what we can have right now is a understanding of physics that is a truth within limits. That's why we can get so close on so many things and be so far off on others. And so what differentiates between a good theory and a better theory? Because I'm not going to say a good one and a bad one. I'm going to say, how do we get closer and closer to the truth as we try to asymptotically approach, what is really out there? And the difference is really, it's in your ability to predict reality over a longer and longer period of time. Like, for instance, one of the things that they could possibly do with this spirit of the fishing tree is they could try to apply it to something else, like retreats. They could think of it as a food retrieval system, and therefore by burning it, they might actually, calm or even kill bees, because as you may or may not know, neurotoxins are various insects are very especially susceptible to neurotoxins. And so they might apply this spirit of the fishing tree theory to even extend their theory to other things and get good results. But that doesn't mean that their theory is the best theory that could be used. And so what I want to talk about today is how it is that we got to where we are, how it is that we are doing well in so many ways, and then doing so horrifically in others, and what it is that we might want to look at as a alternative path that we could take. In other words, where did we take those missteps that we might be able to back all the way up? And I like going back 200 years specifically, but how do we go back and find a specific place that we can interject a little change and maintain a perfect analogy all along the way with our current physics? Because we've got a tremendous body of evidence that proves our current physics theory, in other words, the mathematics and the way it comes out, to be correct in a variety of ways. But then how do we make that work with another theory, another interpretation? So what I'm talking about here is the change in interpretation, and how you achieve a better change of interpretation is by looking at the history of physics. So I said I'd go all the way back to 200 years. I didn't in this paper. This paper was back in 2018, I believe, and I go into it in a few other papers. But where I like to start is with Fresnel's index of refraction. So the way in which he developed the index of refraction was based upon the idea of ether. And now if you follow a tremendous amount of physics up to before I start talking about ether, because that's a very it's a topic people don't really like to talk about, and there's a reason for that, because there is this divide in ether between relativistic ether and non-relativistic ether, and most people only know about non-relativistic ether. In other words, everything that was prior to 1887. I won't say everything. A large portion of the theory that existed prior to 1887, the Michelson-Morley experiment, was non-relativistic. However, very quickly thereafter, they actually did immediately come to the idea of the base idea of relativity. And that was through the Lorentz-Fitzgerald contraction. In other words, so Fitzgerald was a scientist who proposed this initial idea that, well, maybe the reason why we're getting this null is because there's this perfect amount that matter is shortening. Now, he didn't come up with that out of nowhere. Unfortunately, a lot of people believe that that was very ad hoc. However, it does travel back to specifically the Fizeau experiment. And that's why I'm talking about going back 200 years. And I'm going to have to jump around here a little bit, and I hope you can follow along with me because I need to tell this narrative so you understand how it is that we took this specific deviation in physics that can be an alternative path that's running side by side and is present and alive today in a variety of different places. And I'm going to get back to that. So please bear with me as I jump around a little bit. So one of the things that happened in the Fizeau experiment, that's the experiment where they ran light through a tube of water, ran the water, and wanted to see how much it impacted the speed of light, basically by the movement of the water. And prior to this experiment, Fresnel predicted that it would not completely carry the light along, nor would it have no effect whatsoever, but would have a very specific amount that it carried the light along. And he predicted this, from the index of refraction. So that's why I'm trying to show you there's these little pieces. So I'm going to give you little hints, I'm going to try to keep it short because there is a tremendous amount to tell here. So So one of the things that you'll also find is that Einstein and others also kind of take this as the first grounding, the first experimental point in relativity was the Fizeau experiment. And so going back forward to Fitzgerald, he was actually rediscovering the works in ether prior to that. Now, let me just say first of all, before we go forward, and here's some of that jumping around. Special relativity was in 1905, and general relativity was in 1915. And in 1920, Einstein gave a speech to the University of Leiden in which he summarized it with space without ether is unthinkable. And in addition to that, you have, as late as 1950, Paul Dirac saying that we are forced to have an ether in one of his papers. I can put that there. And then there's also more recent books that also mention the ether, but there's still this sort of pushback against the ether, specifically because of this misunderstanding that ether theory really only advanced after 1887. So in 1887, there's the Michelson null, and shortly thereafter, you have Fitzgerald contraction, which is that is where you get the very basis of relativity, which is we call it the Lorentz factor or gamma, and so this is the amount that things shorten by. So you need to understand why this works in a fluid-based environment. In other words, how can this work? Because one of the things that you'll learn if you learn anything about modern physics, you learn about relativity, is that electromagnetic waves, they can't be compared to mechanical waves because relativity just doesn't work like that. That's the story that should be told. However, that's not actually true. It was based entirely upon the way in which waves would be traveling in a medium if they were carried along by that medium. And what I'm telling you is the central calculation that defines relativity is based upon the way that waves would have to move in a medium. And that is what Lorentz was describing. And before him, it was Larmor. By 1895, I believe it was, Larmor had actually come up with time dilation. So length contraction, time dilation, both of these things existed prior to 1905. Now, I'm not saying Einstein's a plagiarist or anything like that. This is the reason why he has two parts in his paper, which is the kinematical part, which he just takes everything that Lorentz did and just explains it in a way in which he feels like he can simplify it and not really think much about it. And then he does his part, which is the electrodynamical part. So that is the part that he is purposefully saying, this is what I'm contributing, this is what other people have contributed. So there's been a misunderstanding a lot of times saying that he was plagiarizing. That's not the case. He was importing work and saying, okay, that's what this is, and now this is my work. So that's an important thing to understand. So it is critical to understand that this is a mechanical wave theory. Relativistic ether existed and was very well understood. Now, here's the thing that you have to understand about the way that it works. It's just a simple fact that if you direct a wave into a moving medium, it's going to be carried along with the medium. So say there's a river and I direct a wave across this river. Well, like if I drop a pebble in a moving river, the circle that comes off of it is going to move with the river, right? So if I want to direct a wave to reflect off the bank over here and come back to the same location, I cannot, if it's in any way a coherent beam, in other words, a straight line sort of beam, I can't aim directly across the river, right? Because it's going to be carried along with the river. I have to aim ahead of it. There is a very particular angle by which that has to be done. And there's only one angle that it will work to come back to the origin. And it has to do with the wave speed in the medium. And so this amount, that is directly the Lorentz contraction. Now, the contraction part is that for it to go the other direction and back, in other words, travel upstream and back downstream, you may have an intuitive thought that's like, well, if a swimmer has to go upstream and then go back downstream, it'll cancel out. It does not. The amount that it is further is actually gamma squared. So in other words, it is the change factor squared is actually the amount that it is over. So the change factor is the square root of that amount. And so it's a simple geometric trick, basically, to say that matter shortens up just the right amount in the direction that the river is going, so that a swimmer that would have to go upstream and back downstream has a shorter distance to go overall, and the beam going across and back it travels the same distance, and they end up both traveling the same distance. You get the null effect in an interferometer experiment, which was the basis of it. So the story here, just to understand, is that it is a description of light being carried along by a medium. It is a mechanical wave in a medium that works, and there is a workable theory of relativity that is entirely mechanical wave based and based upon the ether. And of course, Maxwell's equations were based upon the ether, and there's a variety of things I won't go into because I don't want to take forever here. But so this is a point. This is a point at which most people are unaware that there is an alternative interpretation. We're aware that we have things like the many worlds interpretation, Copenhagen interpretation, pilot wave interpretation for quantum physics, but people are not aware that there is well, most people are not aware that there is the relativistic ether that is an interpretation of relativity, and it comes to the exact same calculations. And at the time, it used to be called Lorentz-Einstein relativity, and there was this thing with Poincaré, who also did the same thing that Einstein did, but he did it for the relativistic ether, and these were called mathematically indistinguishable. So understanding there are these two explanations of what's happening, and the difference between these two explanations is that in one case, we believe it's an illusion caused by the shortening in reality. And there's actually Oliver Heaviside, who is responsible for interpreting Maxwell's equations and giving them the version that we have today. He actually explained how it is that electromagnetism would lead to the shortening of molecules, atoms, etc. So there's plenty of theory that was developed in that initial 15 years before special relativity, and then when ether started to be discarded as not relevant, or at least not necessary to come to the certain calculations, and then there was a variety of metaphysical things that happened at that point. So now I'm going to start to tell a little bit of the history after that point, but it's just very crucial that you understand there are these two alternative ways, and these two alternative interpretations, a fluid dynamical perspective, continue to persist all the way up to the present day. One of the other things that are, so what is it if it's mathematically indistinguishable? One of the arguments that are frequently made is, well, if it's mathematically indistinguishable, then why would we care? Why would we pick one or the other? That's not real science, etc. However, there is a way in which we could distinguish between special relativity and relativistic ether with Lorentz and Poincaré. And they published right at the same time. There was a publishing irregularity, and historians talk about how there's a very good possibility that without that publishing irregularity, Poincaré would have been given primacy for relativity theory, and we would be working with relativistic ether today instead. But the point at which there is this deviation. Now, Einstein, in his paper on the electrodynamics of moving bodies, which is the relativity paper in 1905, he did give some indication. It's like, well, we don't have to think about the ether because we're having all these weird problems with the way at which it works. Well, I can clear up a lot of that, but I don't want to get too bogged down in so many different details about why it is that it seemed very strange and how you can resolve all of those problems with the simple thing of going back to for now. But moving forward here, where was I there? Give me just a moment. Let me take a drink here. The point at which relativity and special relativity, excuse me, and relativistic ether are differentiated, where they become actually differentiable by experiment, is called a one-way speed of light experiment. Now, according to most people today, that has never been successfully accomplished. In other words, we have never measured the one-way speed of light is a very common argument. And I would argue that is actually not true. It is simply they do not like the consequences of the voluminous positive experiments that have actually proven that there is a difference in the one-way speed of light, because there is a sociological problem here. And the sociological problem is that people believe that if you have a light speed measured different in one direction versus the other, that violates relativity. However, it does not. It simply selects between the two alternative interpretations of relativity. And so that is one of the key factors that has confounded us for about 100 years now, and why it is that people do not talk about the ether. And when they do, they're typically referring to the ether that was disproven by the 1887 Michelson-Morley experiment. But they are not referring to the forgotten theory that birthed relativity, that was prior to special relativity, and that is relativistic ether, and that they are mathematically equivalent. So that experiment, a one-way speed of light experiment, there's a lot of argument there. Like I said, don't want to get into that too much about that it has been accomplished or whether it is not. But that has traveled forward now, and if you want to look into it further yourself, there's something called the Mansouri-Sechsel test theory of relativity, which is about proposing a mathematical way in which you can account for this type of relativity. In other words, it is a ether relativity. And this was also, something that is only known amongst a very small group of people, but it is known in certain areas of science. And but let me travel forward a little bit. So here we have the sociological effect that has occurred over the past 100 years. Well, part of that story is that one of the close friends of David Hilbert, actually, he said he's more closer to me than a brother, or something to that effect, and is Hermann Minkowski. Hermann Minkowski is Einstein's teacher. Okay, he was a teacher and he put forward a version of relativity in 1907. So that's a couple of years after Einstein's paper. Minkowski comes forward and gives us Minkowski space-time. And then 2 years later, about the time that things don't travel as fast back then as they do now, so it's about the time people are starting to get a handle on Minkowski's thing. Einstein says some things in public where he says, now that the mathematicians have invaded the theory of relativity, I no longer understand it myself anymore, which was him referring specifically to Minkowski's space-time. And in Minkowski's convention, the way in which you mathematically treat it, it specifies isotropic constancy. In other words, there's not this two-way effect that cancels out in all two-way experiments. And once again, I was saying there's a one-way speed of light experiment, which everyone now says has never been accomplished. The difference between relativity, as we now are mostly taught, versus this other version, or this other interpretation of relativity, is a one-way speed of light test. And that would, should it be successful, and I'm contending that it has been successful many times and simply not been accepted, would prove that the other theory is the one that should take primacy. But I mentioned David Hilbert. David Hilbert is who helped Einstein very vigorously right at the time that he was developing, he was finally finalizing it. We're talking about 10 years of him struggling with general relativity. Then right around that time is when David Hilbert actually helped him. Well, you see, David Hilbert was very tied into this whole community. And why I'm telling you this story is because Minkowski, who was like a brother to Hilbert, suddenly died of a ruptured hernia after Einstein had publicly ridiculed him, his superior, basically, in everyone's eyes, and everyone came down on Einstein hard. And so you need to understand that basically there is this huge communal pressure for Einstein to make up for his faux pas and to use this dead man's work. And so he starts to use the Minkowski spacetime because it is a useful heuristic, because being able to detect the difference between two-way experiments and one-way experiments is very difficult. It's a subtle process. Like I said, theoretically, we have never done it up to today, is what the mainstream currently contends. So he integrates Minkowski spacetime, which then specifies isotropic constancy. And but then all throughout Einstein's writings, you hear him repeating over and over, we have to abandon constancy. Constancy is not anywhere. When you're talking about general relativity, it's only in places where there is no gravity that it's ever realized. So therefore, and he says this explicitly, the constancy is nowhere realized anywhere in the real world. And so he specifies this specifically, which is how he ends up coming to the speech in 1920, where he says space without ether is unthinkable. So the problem is the word ether. People, they immediately are thinking of Stokes ether. They're thinking of a specific type of ether that is not workable, instead of the type of ether that was developed during that 15 years, that is relativistic ether. So now, I told you all of that because now we need to continue into the modern day, and there is a lineage you can trace all the way from McCulloch, who was who first gave us something called a rotational elasticity that led up through Fitzgerald, who had rediscovered his work, who came up with who was the one who first presented the change factor in its mathematical form in 1889. And this lineage also continues up through me, who used a four-dimensional generalization of McCulloch's ether as the way in which he was working towards general relativity. So it's a little bit of competition between Hilbert and Einstein during that period, and collaboration, tremendous amount of collaboration. That is very historically. And there were some people who once again wanted to accuse Einstein of plagiarism because of that collaboration, but it's simply not true. It's been proven that he did come to certain things before Hilbert did. But the point is, they were very closely working together. And there's this sociological aspect, along with some of the things that were happening in World War I and World War II, that you have to understand why it is that we select one view of the way the world works versus another when they are mathematically indistinguishable. Now, they're not experimentally indistinguishable except in certain people's theories. So now all of that leads up to, now we need to get to the quantum era. And in the quantum era, you'll find in my paper, and because I am a little bit rusty on those things, I tend to load them up as I'm writing a paper to publish, and then they start to get a little fuzzy after some time. But there was a casting of quantum theory in hydrodynamics at the very beginning of quantum theory. And so what I'm saying is that there is an analog to quantum theory found in hydrodynamics. So from all the way back to Maxwell's equations, now up to quantum theory, you can trace this line of hydrodynamics in something called a rotationally elastic ether. And so what does that lead us to that can be a little more useful today? And that is specifically pilot wave theory. So I'm going to get you to something that is that starts to make more sense. So pilot wave theory is the alternative interpretation of quantum mechanics that people don't talk about. It's like for some reason it's the bad boy of the group. I don't know why people don't talk about it very much, but it is those people who are actually somewhat in the know when it comes to the physics of UAPs, etc. They actually do talk about pilot waves specifically, and that is because it is a deterministic way in which things work. Now, people hate determinism. That's just, nobody wants to feel like they're controlled, and nobody wants to feel like they're a puppet, etc. But determinism, as most people understand it, is not the way that chaotic determinism works. So there's the ways in which, if you look into chaos theory, the way in which the very small things can work together to make very large things happen in the butterfly effect. That is a deterministic set of effects, and you're only keeping up with the butterfly flaps its wing and that scares a frog and yada yada, instead of keeping up with all of the other things that are side by side with it simultaneously that contribute to these very subtle effects that we cannot track, but we can only keep up with via statistics. So in other words, now this is going to lead to the work of Coudet and John Bush at MIT. And what I mean by this, there is something called the silicon Walker experiments. These are silicon droplets that bounce on a bath that is driven by at a certain frequency. And these experiments have been proven to show all of the effects of quantum mechanics in this system at a macro level. So all of the things that, for instance, one of the things that Richard Feynman said is, the dual slit experiment, it absolutely makes no sense, and that is the thing that is really at the heart of the weirdness of quantum mechanics. We have no theory that can explain how and why that works the way that it does. However, now with these experiments, who were began by Yves Coudet and explored by John Bush at MIT, and I really recommend you go to Pilot Wave Hydrodynamics. That's pilot-wave-hydrodynamics.com, and you can get to his website at MIT. And I really suggest that you study the way in which this works, because all of those things which seem to be spooky action at a distance, the dual slit, all of the things that are mysterious, strange, weird, all of those things work within this macro-sized system, millimeter-sized droplets that you can watch do their thing. And the way in which it works is through chaotic dynamics. These chaotic dynamics have a feedback loop. So as the droplet bounces, and it's a droplet of the same fluid on the fluid. So the only way the droplet exists is by the energy that is pumped into the system and by the way in which it alters the surface. So in other words, the droplet itself participates in its own existence. And so this feedback loop leads to it moving around in a normal human time frame. You would watch this droplet just kind of move around randomly. Well, the randomness is pseudo randomness. It is not real randomness. It is a chaotic dynamic that is entirely deterministic. But the minute effects that lead to the way in which it moves there are too many to keep up with. So we have to treat it with statistics. But the map is not the territory. And what I mean by this is that statistical treatments can give you ideas about systems that are valuable and useful, and you can engineer based upon them, but they are a heuristic. They are an analogy. They're a way in which we take out some very important complexities that might be there and valuable to us, and instead deal with what we can deal with our, very blunt tools. So what we find is that this droplet, as it explores the corral, you watch it over a long enough period of time, it actually spends more time in some areas than others. And what it gives you is a waveform that exactly matches the experiments in which we have trapped an atom inside of a corral. And because it is it's the waveform that is resonant with that cavity. And that is just one of many different ways in which there's quantum tunneling. There's basically every one of the quantum effects are shown to have an analog in this fluid. Well, so remember what I was talking about was with relativity, you have a fluid dynamical way in which things work. And I started talking about pilot wave theory because that's what this is. It describes the way in which what we thought when we, the reason why people do not like pilot wave theory is because of the fact that there is this non-local components, one of the components to it, as well as this the pilot wave itself. In other words, like the whole universe seems to contribute to the way in which this a single particle works, and so this seems very confusing to people. But now we have the tools and have for I think they've been doing this work and advancing it for nearly 20 years now, I believe, but really a lot recently. And like I said, here in the U.S., it's John Bush, and so this gives us an alternative way to view what is happening and how it is that particles may exist in a fluid environment. So the story here that I want to tell in as short a form as possible, because there's really a tremendous number of other things I can get into here, is that there is a way in which we have a mechanical deterministic system that where there may be a structured space-time that has additional details in it and can be engineered. And so instead of it being space-time, and unfortunately while that is the word that has inundated our vocabulary, there's some subtleties there that you have to navigate in understanding what an ether-based version of relativity would look like. And that's just, instead of ether, that word, once again, it's, I hate to, it's the best word for it in my opinion, but it does not accurately reflect what you're referring to when you say ether, which is only that theory which matches special relativity mathematically. And that is the ether theory only after 1887. So this system then gives us a reasoning by which we should select the pilot wave interpretation as the appropriate interpretation and a deterministic background for all of the stochastic effects that we seem to see. And by using this system, we can see how it is that things like the dual slit experiment, the wave particle duality, all of those things start to make a lot more sense. And then we start to understand a way by which we can look at these ideas of engineering space, and that there may be a structure in space itself that is actually present and relevant to this engineering process. So that was the short of it, and I could go tremendously long on this, but I think I'd like to go to a Q&A session so that we can go over it a little bit more, because I think a Q&A session will actually, bring out some of the things that people might have when it comes to questions, contentions, etc. So I hope some of the guys there are in the background and they've got some good questions queued up, some hard questions, because I'd really love to go through that and talk about how the history of the hydrodynamic interpretation of modern physics can work at every level, all the way, going back 200 years right up to the present. And of course, there's my paper that you put there in the display that will that people can use as a starting point. It's a very concise version, but there are other versions of it that I can give as well.
Awesome. Shiva, thank you, man. Thank you. So the first thing I want to do is I want to bring everybody in. We need to give you an applause. That was one heck of a lecture. I did add your paper in just to kind of have it there, but it looks like you didn't reference it that much. So everybody, Shiva Meucci, that was tremendous, man. And that was all from memory too, which is insane. So thank you. So yeah, if you guys have questions, let me know, start. Dan?
I got one. You got whoever can go first. I can wait.
Yeah, Dan, why don't you go first, sir?
So wasn't there just it's kind of a two-part question? Wasn't there just an experiment recently in the last couple of years? It might have been 2001. I don't recall the name of it exactly. I'll have to do some researching on it to find the exact one. But didn't it debunk pilot wave theory in essence? And tacking onto that, what are your thoughts on the statement that pilot wave theories are just many worlds in denial?
Okay, that's great. Yeah, you're talking about the article. Actually, keeping in touch with John Bush occasionally. He puts up with my emails, and you're talking about the article that came out in Quanta magazine, and it was a report by the grandchild of Bohr, who of course Bohr is the father of Copenhagen interpretation, and this is his grandchild who did an experiment, and it was said that he replicated the experiments of the pilot wave walkers, and Bush has refuted that 9 Ways to Sunday, and basically that is a pop science version versus a real science version. In other words, Bush has shown that this is an absolutely ridiculous non-replication, where they tried to test one thing and didn't do it properly, and they just didn't cover anything at all. And of course, like I mentioned, I'm sorry, the truth of the matter is there are sociological effects in science that are very, very direct and unambiguous. And as I said, this is Bohr's grandchild defending the legacy of his grandfather. So that would be one thing. And then the other thing, the idea of many worlds in denial, I would say that is kind of ridiculous, because what many worlds postulates is additional actual reality splitting off. Whereas, okay, so there's two different ways in which
the wave function.
Say again?
It just postulates the wave function evolving smoothly with no Heisenberg cut.
Well, it's saying okay. So many worlds is that there is a world which matches every possible outcome of the wave function. In other words, instead of having a collapse, you instead have a different world that comes off of it. So there are infinite worlds in any infinitesimal slice of time. There are infinite additional worlds being created for every particle.
Not
It is
necessarily infinite, but sure.
It's okay. Well, nearly. It's nearly there, but let's not strain it out there. But the idea that there are all of these additional worlds. There's two different ways in which you can understand the idea of additional dimensionality. In fluid dynamics, we treat a system like one of my favorite experiments, and is one of David Bohm's favorite experiments, is the reversible laminar flow experiment. And in it, you can take a vat of glycerin, put dots in it, of ink, wind it many times so it's completely looks like it's perfectly mixed, and then you unwind it, and it's the dots are restored. And this reversibility is a way in which you can understand the idea of why we use additional dimensions in treating fluid dynamics, and that is not external realities, that is different ways of slicing the current pie. So higher dimensional, whenever you're using higher dimensional mathematics, you don't need to be talking about things that are external to this, but a different way of slicing this one thing. And that's the way in which fluid dynamics uses those additional dimensions. It is not something outside of our current reality, additional to it, higher than it, etc. It is just a different way of viewing it. In other words, the droplets, even when they look like they're completely mixed in, they still exist in a different dimension, because you can recover them, right? So so that is the idea of dimensionality that is important to understand, would be preserved. And yeah, you could have an idea of other dimensions existing within this one in that manner. And you could say that could give you a view that it's sort of many worlds like with Pilot Wave, but it would be fundamentally different in character.
Okay.
Awesome. Wow. You guys are getting heavy really quick. Okay, so let me go to Curtis next. My brain hurts, by the way. Like, seriously hurts. I need Advil.
I really enjoyed your talk. And one of the things that I have always wondered is, why did Einstein include the symmetries that he did, right? So that's something I haven't gotten. I don't know that you have the answer, but when you talked about the sociological situation, I can see why he would maybe subconsciously make that mistake, or bring in such assumptions that are were more standard at the time, because at the time the mathematics was developed for the full Einstein group that Sachs uses, the quaternion type group, and it's not like he didn't know that was there, but I don't know. Do you know why he went that way?
There's some of it that has to do with I don't know if you've heard of the whole problem. There were a lot of different developments preceding general relativity that where he was trying to solve covariance, and it gets a little too heady to really comment on in any cogent way, in my opinion. But a lot of the idea of symmetry that is built in, as I said before, the what's occurring, okay, in the view that I am saying that is the superior view, which is a substance of space view. There is that preservation of Lorentz symmetry. In other words, there is a shortening that will happen that is exactly equivalent to motion through the ether. And how that's carried out. And there's a variety of questions you guys are going to come back to me with if you don't think I'm now. You're going to be asking, well, what about the Michelson null? Shouldn't it have been non-null in that case? I can give you details about that. There's a variety of things that are going to occur to you, and I hope we continue this conversation because I'd like to answer those questions for you as they come up. But when it comes to the symmetry, there is a symmetry that is preserved because there's when you look at it from the advanced ether theory that is kind of going by different names. Everything from what's it called, the quantum vacuum foam. There's a variety of ways in which they treat the space that all are that come from those developments during that period from 1887 to 1905. And you can trace the development specifically of Kelvin up through what is the Sachs-Dirac work, which is called micropolar elasticity. We now use it in material science, but the micropolar elasticity was originally just an ether theory. In other words, it was a way in which we could look at the way that rotational elasticity worked. And so there's all this work with Thomson and Tate Lord Kelvin. And, you know, when it comes to developing a model of elasticity that works, and they had a problem with Maxwell's equations when it came to the way in which elasticity is working, and all of that got resolved right after 1887. Kelvin actually resolved the physicality of it in 1889 as well, with the what was it called, the gyrostat, what's it called, the adynamic gyrostatic theory of ether. I forget what it was called, but I can give you the paper. I think I will refer to it in my paper there. But basically shows the way in which this very counterintuitive motion that can occur in what is basically a superfluid. In other words, we have to understand that any kind of version of ether actually has to be an inviscid fluid, and recalcitrant continua actually are it's a version of superfluid before we knew superfluids actually existed at all. And so that was I'm sorry, I am kind of bunny trailing here, and I'm no longer on your question. I do that sometimes, but so let me get to other questions.
That's okay. I just, as a follow-up, I wanted to see what your impression is of the fact that mental Sachs' theory, taking, you know, from those kind of simple axioms, not simple, but, you know, a couple axioms, develops, you have a quaternion formulation of general relativity, a matter field. So it's kind of related to pilot wave theory, but, you know, more taking it as, okay, it's a matter field. But using that theory, you derive this background pair gas that, you know, recovers this whole ether idea, and it, you know, explain, and because it's so tightly coupled, it explains the fact that it's not easy to detect. You know, it's hidden deep in you know, in the 0 point energy. I'm just kind of wondering what your impression of that whole methodology is.
Well, the thing is, whenever it's, you know, I actually have a background in programming, and one of the things that occurs is that as you start to use more and more abstract languages, you can't keep your eye on the ball of what you're using the language to do. And so the same thing is true of mathematics. In other words, there's a point at which I could write a program right now that you can show me the real ones and zeros, or you can even show me assembler code from it. I would have no clue what my program is really doing. You know, I know what it is doing at a higher level because I'm taking the tools and making them work in a certain way. Well, mathematics is the same way. You are taking tools, putting them together in particular ways that we know work, like a machine. So this part of the machine works, this part of the machine works. We ram it together and it does something else. And so that's kind of the way in which theories continue to progress without necessarily having a very good theoretical background that we can intuitively understand in any really good way. So what I would say is that that you're probably coming to mathematical truths that are where you're representing one part here and another part there, and because the theory doesn't necessarily match the truth that you're actually retrieving, it's hard to understand that connection. So that's one of, I think, what has stymied progress for the past 100 years is that we are working with an analogy. I'm saying that the hydrodynamic view is the superior view that will allow us to understand what our mathematics are doing, and we'll be able to, because of what our developments in just fluid dynamics, et cetera, we'll be able to apply some of those lessons learned there to our current theory and be able to start making advances that are workable.
Yep.
That's amazing. I'm just writing in chat here how stupid you guys make me feel, but like in a good way, you know, but like it's there. It's like, damn, now I feel really stupid. So just the entire world knows that you guys are really, really smart. So yeah,
Right, so
this is absolutely wonderful. Alex, I think you'd started to say something, right? You had a question earlier, or
yeah? Well, I had an aside for Shiva. Or do you have an eidetic memory? Because it seems like you do. Jesus, the amount of information.
It's 20 years into doing this, so that's, you're going to go over the same material a lot. You end up, you can't help but remember all of it. One thing, I would say that I forgot to add to this that I think is that everybody's going to come to this question later on is how is it that if there was an ether that it wasn't detected at all by the Michelson, and it's going to come to some details, and this is why I actually tell the story going back to the Zoe experiment. So some of the things, something I'll send you guys off with that you might want to look into is Dayton Miller was given the 1923 Newcomb Cleveland Prize for the detection of the ether, and he is the reason why Einstein did not ever get a Nobel for relativity, but instead only got a Nobel for the photoelectric effect. It's specifically him that blocked it because of these experiments that he did. He did tens of thousands of replications of the Michelson-Morley experiment, and he created a double blinding type of methodology in this physical science, where the person reading the interferometer as it spun around was talking to a person in the other room, and they were just writing it down. That way, they couldn't have any bias about where the person is, what direction they're facing, and years later, this data was so voluminous that Maurice Allais, who is a Nobel-winning economist, actually looked at the data and found correlations with the sidereal day, with the position of the Earth with respect to the sun, all of these things in these interferometer experiments. And so you have to say, well, isn't what you're saying that an interferometer experiment should be exactly null? And this is the point at which it's very important, and that is the index of refraction in the air is going to have a very minute effect, according to the Fizeau experiment. In other words, so the index of refraction, which Fresnel called that the coefficient of ether drag. So this partial effect, and it's going to be based upon the material substance. So therefore, any experiment in a vacuum should be null, but an experiment that is in a gas should have a non-null result. Go look at the original Michelson-Morley experiment of 1887, the data. Plot it yourself. Now all you have to do is just it goes all when it goes in a full circle. So you just need to change the temperature variation, and what you'll see is a dual sine wave of readings. That is exactly what you would expect of an ether wind. In other words, you expect an ether wind, but there's a nonlinear relationship between the size of the result and the speed that it means. The wind speed of the original 1887 Michelson-Morley experiment was between 8 and 12 kilometers per second, which is only a third of what you would expect of the Earth going around the sun. So the lesson here that I want to tell you, because you're going to go back and you're going to think about some of this, is that trying to navigate from North America to Africa by putting a little paddle wheel underneath your boat and measuring how far you go is not going to ever work. You're going to be hopelessly lost, because there are various currents at various different scales that are going to radically change what you get as you navigate through it. The same thing would be true of an ether, like we were talking about. There's a relativistic ether. There would be very different currents in different places. And so there's, like I said, very long story. You're going to have questions for me later. You're going to say, what about this? What about that? And like I said, I've been doing this 20 years. I do have answers for all of those. And this is something I want to, let people know. This is not my thing. This is history. They already had these things worked out. We just selected one thing over the other because of sociological reasons.
Okay. Let me go to Dan really quick, and then Curtis and Michael, if that's okay. Oh, sorry. Yeah. So Dan, if you go quick.
In your opinion, is the cosmological constant a version of an ether theory?
Well, it's too deeply embedded to call it that. There are things like there are various analogies. Dark matter, for instance, the reason why. Okay, one of the aspects of this ether theory that I sort of when I talk about going back 200 years to Fresnel is his way of explaining the index of refraction. So wave speed has to do with density and rigidity, and so increased density slows the wave, increased rigidity increases the speed, and so you have to do a calculation based on those things. He assumed that there was increased density inside of a material object, and that is what caused the index of refraction. If you merely think that it is reduced rigidity, and so in other words, simply change one for the other, the math comes out exactly the same, but your whole perspective of the universe turns inside out, and you end up seeing that matter is instead the foam at the edge of the universe. And what we're looking at is material bodies are they're more wholes than they are the thing, and the thing is the ether itself. In other words, the vacuum is the primary substance, and matter itself becomes the effect. Now, this is going back to
the polarizable vacuum model.
Say again.
So it's sort of like a polarizable vacuum model.
Well, this goes back to Kelvin's ring vortex. Is not, which goes to knot theory. His ring vortex atom actually works especially well once you start to understand the mechanics that that John Bush and Coudet did with the rockers, understanding the way in which both the wave interacts with the droplet. In other words, the discontinuity in the system, the droplet, the way in which the wave interacts with those things actually is well, I'm not sure exactly where I was going there. Your smile threw me off. But I lost the train of thought.
Oh, it's okay. Let me go to Michael really quick. And again, we're pushing up against the top of the hour, and we have to do lad time. Michael, go for it, sir.
So she's very, very good. You're spot on with all of this. It looks like indeed there are a bunch of papers on Google Scholar that say they measure the one-way speed of light, and then not many people really cite them. But that may indeed be more due to sociological reasons than clear thinking. One thing that you might be excited to hear is, at least with the model that I'm working on, maybe Todd Desiato also has a similar model, Professor Tejinder. All of these models, we're looking at, well, even like spontaneous symmetry breaking in the vacuum. Mm-hmm. You can think of it as a material phase change. So when you have virtual particles close enough together in large enough quantities, so when you have enough energy density in the vacuum, then the virtual particles overlap and you get the electroweak unification. And it's due to that overlapping. It's identical to like a phase change, like from liquid to gas, or well, in this case, gas to liquid, more like, or liquid to solid. But you're creating a particle. You have like a droplet of a different phase in the vacuum, in a sense.
Yep, exactly. And I explained this through the idea of cavitation. In other words, you've seen a cavitation in a fluid it's basically a hole ripped in the fluid. Well, one of the things that will occur, like say for instance, you have a vortex in a fluid that it's already starting to it hasn't reached the threshold yet, but a wave which traverses the center of that vortex will then cause it to cavitate because of the additional energy. Increases the speed of the rotation, which then would give you the idea of here's a particle created. It is emergent by the way in which the wave and the vortex interact. And so there's a wave vortex duality is actually something that's fairly well known in fluid dynamics and especially in plasma physics. And like I said, there's too many things I can bunny trail on, and so we got to kind of keep it short.
That's fair. But yeah, it's exciting because you get this phase change and. I mean you can just look at even like with the strong force, then you look at like neutrons and protons and you can think of them as particles that have non-zero conduction because of the quark model. So like you can imagine the charges moving around on the particle surface. So you can think of these as conducting plates, and then you see that in fact you can if you see what the Casimir force is at that size scale, it's equivalent to the strong force. So like it matches really nicely, all of this stuff.
Absolutely.
Yeah, and that wasn't my idea to begin with. I think another researcher thought of that idea. But yeah, the material medium approach is the right way to go. And the Michelson-Morley experiment got it wrong simply because people assumed that if something didn't have a reference frame of its own, it couldn't possibly have material properties of its own. But we know that virtual particles don't have a well-defined position and momentum. So if you make a material out of virtual particles, it could very well be generally covariant.
Well, also part of the reasoning is they kind of had a Stokes model that they use. In other words, like a grid type of ether instead of one that could flow against itself.
Of course, a solid instead of a liquid.
Dragging, it's we know
fluid.
space moves as a superfluid, and space does move against itself. And so because of that idea that the universe is this one grid thing, their expectations of what speed you should get were ridiculous. And then he also only looked at the readings for east-west. He didn't pay attention to what was the highest readings and lowest readings, and the fact that it was a dual sine wave, exactly as would be expected of that experiment. And so, there's a variety of things like that. But the funny thing is, it's an accidental advancement. In other words, the looking at the effect in a vacuum is actually what leads us to relativistic ether, which is we do need relativity. And so it's so weirdly serendipitous that it was reported as null. But anyhow.
Yeah. Okay. Well, let me see. We are at the top. We have 1 minute left. Curtis, do you think you could go super quick? And then
just real quick. I wanted to understand the mechanism for particle and antiparticle pair creation and annihilation in the theory you're discussing.
Okay, so if you go and I really recommend you learn a little bit about Kelvin's ring vortex model, but then there is something called the Faraday wave mode of a cavity. So there's a variety of different things in fluid mechanics that are at play here, but there is the creation of laminar flow layers that can occur, and then whenever something is a standing wave, one of the things that will occur, like say for instance, you have you create a wave pool that has a checkerboard of standing waves. Underneath those standing waves vortices will then appear. But then there are also the various, like if you've ever seen cymatics experiments, basically what they're looking at is the Faraday wave modes, where you have you'll have an octagon and a hexagon. Like for instance, we see there's a hexagon on the North Pole of Saturn, and then there's a 5-sided and an 8-sided figure of vortices on the top of and bottom of Jupiter, and they're persistent. And so the understanding of the way in which waves and vortices interact, and the way in which there can be a spontaneous sort of creation of a virtual cavity, can make it such that there are these stable vortex structures that are interacting and pumped by the waves that are occurring in them. And so when we're talking about this spontaneous emergence of an electron, for instance, as this fluid that is not a perfect flow, of course, it's going to have various subtle changes in the flow of the fluid within this cavity that has a stable wave mode, and there's going to have a certain number of vortices. Well, as the waves cross the vortices, they will be spun up and then cavitate, and that would create your particle. And so, in other words, the cavitation, the momentary existence that's one of the things that we see whenever we're looking at electrons, for instance, this kind of momentary existence. The momentary existence of it would be mediated by this interaction of the wave and the vortex, where there is a wave vortex duality. And of course, there's issues of nonlinearity at the quantum scale when it comes to a fluid dynamical approach, and how this would lead to solitons. And like I said, I'm just talking about these are things that I've done research where there are a wide variety of people who dare not call it ether, and who have been doing this research for many, many years, and they've been publishing papers and not being noticed, and they're out there right now. And that's why I'm just referring to this as the neoclassical interpretation, because there's neoclassical physics.org, I think. That's not was there before me, and this guy who actually is the English translator of the Cosserat book from 1909.
Awesome.
If I may add one thing regarding the soliton models, I've been studying those recently. I'm starting to catch up. With even just with the KdV equation, you can see as solitons move through each other, they change their motion speed. So with physical particles, you can think of the if physical particles are solitonic, you can think of the if you compare the standard two-way wave equation, so for waves instead of particles, and you calculate what the refractive index of the particles would be based on the KdV data, then you find that the finite structure constant is just the refractive index of these particles.
Yeah, there's a lot of fun stuff that pops out.
Yeah.
Awesome. So, guys, let's put our hands together again. Giant thank you, Shiva. Thank you so much. Thank you so much. And I hope to invite you back and have you share more, and we'll have a little bit more time then. So for today, what I want to do is I'm going to go to Mark Sokol. We're going to start with lab time now. And again, guys, thank you so much. Today has been absolutely tremendous. Our conference just keeps getting better and better and better. So let me go over to Mark. And I think, Mark, you're the co-host, right? So
I am, yes.
Yes. And Mark is okay.
The whole time today, but
I'm just going to take everybody off the screen. And Mr. Sokol, the ship is yours. Dun, dun, dun.
Okay, so as we sail away, we have some updates for you guys. As you can see, the traveling wave tube amplifier for our alpha experiments taken apart. There was a something happened to it. They were still trying to figure out why it's not working, but that happened in the middle of an experiment that gave us some very interesting, I would say nearly conclusive results that we're seeing some weight loss relating to this experiment, and I will be showing them to you shortly right here. So what you're seeing is a screenshot. Looks like it's chopped off on the side a little bit. Nope, that's how it comes. Okay. So what you're looking at is on the x-axis is time, and it's about 5.5 hours. So it's a pretty long length of time. The red line over here that goes up and down, that's the magnetic field strength. And the yellow line that follows kind of with it is what the computer's telling the magnetic field to be at. You can see over here on the 7th run that is visible, something happened with the electromagnet. That's happened sometimes. Sometimes it voltages out because it's voltage regulated. But the bright green you see over here is the weight of the sample. And what we are seeing, besides these two little bumps in the beginning, which seem to follow on almost every single run, we're seeing a constant weight loss about halfway through the magnetic field sweep. So it starts at around, that's around 4,000. It peaks, and then it reaches its lowest at around 5,200 or so. And this happens on every single run. But what happened over here towards the end on the right is something happened to the traveling wave tube amplifier. I think it overheated in some form, and it went into error mode. So all this purple, which you see is the signal coming back, that all zeroed out, and the weight loss did not continue at that spot. It is a bit noisy, I'll give you that. It is noisy. And this sharp swipe over here is probably a relay switching inside the traveling wave tube amplifier. That's probably what that is. But you can clearly see that the magnet was not the contributing factor to this weight loss, because the magnet continued to doing its sweep that it was doing before after the RF shut off, and yet we only saw the weight loss when both components were running. So that acted as a control test. I have seen such weight losses before. This isn't a very significant amount of weight loss. What's significant here is the repeatability. We have 8 times in a row we're seeing a weight loss in a sample which was aluminum powdered mixed in with some iron powder in a encapsulated in epoxy hanging inside of the waveguide, which is inside the electromagnet's magnetic field. So this sort of proves that alzaphan is, there is some sort of connection there. Next things, we're going to fix the traveling wave tube amplifier and get some more repeatable tests like we see here, and we're going to add in our triplet state electrons with the pulsing light or laser method, as well with the pentacene crystal that we've talked about earlier, and hopefully we'll be able to increase this signal and see some more weight loss. So any questions? I'll leave this up here for a moment, and we can continue the conversation. This This is the same data that I have. If anyone wants to look through the raw data, meaning the Excel sheet that this is derived, I'm willing to share it.
Mark, so that's awesome, man. Can I bring Drew was asking if he could come in. I'm not sure if anybody else wants to come in too. Let me see, Drew, and does anybody else want to come in there?
Looks like Curtis turned on his camera. Hey, Curtis.
There's Curtis. Okay,
Hey there.
we're squeezing in tight here.
Yeah, Drew. So finally got my lab view running, and this is our first run. We got
Awesome. Just in case you need any help, Joe said he'd be happy to jump in there, and he's our lab view genius on our end.
Yeah, I might take you up on that, but for now,
just contact him directly. He'll jump right in there, and if he can unscramble whatever you have scrambled, or if he can help, he's happy to. He's out in Texas.
This was about 2 months of work. I was working with a LabVIEW guy out in Pakistan to put this all together. Many of these things he had to write the drivers by hand manually. It was a very 30-year-old equipment.
Oh man, I would love to learn how to write drivers. Is that the guy from Pakistan?
Yeah, he's working with Jared now too.
Well, I would just pay him to teach me how to write drivers. That's awesome. That's a
Michael,
skill.
I don't know if you have the time for it, but it did involve finding the programming manual too. Just caution you.
Well, yeah, no, but writing drivers is just a super useful skill, like for all of these old pieces of equipment. Yeah. Yeah. Anyway, I better head out for the night. But awesome stuff, Mark. Now we're getting good data on this. I'd like to see a bunch more of these so we can average them out and see we can get better error bars on this and stuff like that.
Yeah, I'm so Mark. I'm as I tell you all the time. I am so excited. I mean, it's becoming real, right? And it's not just the results. It's like the professional test apparatus, the methodology you're using, the way you're arriving at samples, and it's not just what you're doing. I mean, like right below me on the screen there is Drew, right? And it's the same thing. It's little bits. It's every day, every day, every day. Everyone here is doing that, is moving forward. And for me, from kind of like because I'm not doing experiments, I'm like an onlooker. And as an onlooker, dude, this is seriously exciting. I mean, I cannot congratulate you guys enough. This is it. It's happening.
Mark, yeah. Can you just walk through them little green squiggles again slowly? And because I want to get excited for you, man, but I don't understand what the green squiggles mean.
Okay, so there's two different shades of green. There's the light bright green. That's the weight of the sample. The darker green on top is the weight of the test chamber itself. The test chamber is on a pivot, and you're able to weigh it separately because of the pivot joint. But the test chamber is made out of copper. We haven't seen much of a weight loss in that. There might be. I haven't teased it out of the data. So what we're seeing here is the magnetic field and the RF. The RF is going into the chamber. Some of it's bouncing back. What bounces back goes to a spectrum analyzer, and the peak of the energy coming back would go into the purple line over there, which is really thick because the RF is pulsing on and off, and the spectrum analyzer isn't reading it fast enough. So sometimes it catches it when it's on, sometimes it catches it when it's off. So you see the full gamut, either the on and the off, all together as one big fat line. What really matters with the purple line is the line on the bottom of it, the edge on the bottom. The magnetic field strength is the red line. Now, so as the magnetic field strength is changing, with RF is staying constant, the RF that's coming back from the chamber is changing. That's because of electron paramagnetic resonance. The Armour precession of different electrons that are in the sample change the sounding wave ratio of the entire apparatus, hence bringing you back more RF. And you know that that's correct because we have 8 repetitions here, and almost every one of them has the exact same line on the bottom of the purple. The next thing you see is the green squiggly line is losing weight at about the 3/4 mark of every single test. It's losing a consistent amount of weight almost every single time. And not only that, there's some smaller signals in the towards the beginning of the test. There's two like little drops and peaks that are also replicated in every single run. Now, these equate to about 1% of the weight of the sample being 1.75 grams roughly. So we're talking milligrams over here, which I normally wouldn't get excited about. But the fact that we're seeing it consistently at the same point of every sweep, and it's not just following the sweep. If it was just a Ferris effect that would be following the magnetic field, that would be taken into as a standard error. It's not. It's the weight loss is happening about 3/4 of the way into each sweep. Magnetic field is sweeping, I think, between 2,000 and it goes from 2,000 to 5,430 Gauss.
So as you align everything, it gets lighter, and then as it springs back, it gets heavier. And then at the next pulse, it aligns, and then it springs back.
Then it gets lighter and lighter and lighter. But we're not actually staying in one spot. In order to actually amplify this effect, I would have to pick out from the data where the signal was the strongest, where I was getting the most weight loss, and just keep it there or in a very small range of that with magnetic field.
Kind of hunt for like a resonance or something?
Yeah, it needs to stay in that resonance spot for a long time. With this setup, I'm jumping between different resonances. We're getting a spectrum of the weight of the sample as it changes.
Damn. All right.
We expect it to be slightly different for each sample, depending what's in there, because EPR, electron paramagnetic resonance, it depends which valence band of electrons you're dealing with. Bismuth, we expect to have a lot of noise. We expect to have a lot of different peaks and stuff. We expect with lithium metal to have the sharpest peaks. That's based on just what some NMR, EPR people told me. But I'm still working with just these aluminum iron sample. And right now our RF amplifier is broke, so we got to fix that.
Okay. Well, Mark, if that's everything, let me take that screen down. I'm going to bring everybody in. We need to let's give Mark an applause. He is doing the work, getting the results. This is coming together. This is coming together, man. I congratulations. Congratulations. If it's okay, let me go to Curtis Horn. Curtis, you were going to share a video. Here, I'll take everybody else out.
Sure.
Do you want me to share that for you, or do you want to try
I
and
can
do
share
it?
my screen.
Yeah, go for it.
Let's see here. Let's see which screen. I'm not sure which screen you guys can see.
Okay. Yeah. So you go into it's the present button and then slides. Oops. So present, screen share, and it'll show your tabs. And if you have one open for YouTube, it'll let you share that.
Okay. Entire screen. There we go. And okay, can you guys see my screen now?
No, not yet. Not yet.
Let's see.
Here, I'll stay with you until it's up. Yeah. So again,
hold on. I need to give Chrome permission. Apparently.
Okay.
So let's see here.
Yeah, Bernie Conkin is the person who got us on StreamYard, and I really do love it. It grows on you. It's got some really nice fluid features to it. It's got its share of quirks, but
I'm gonna have to change this setting. I'm gonna have to come back in, so I'll be right back.
Okay. Oh, and Mark just left. Okay. Yeah, so we are waiting for what? There we go. Okay, Kurt, yeah, Mark, dude. You guys, I know you guys think I'm just like a brown noser, but like I'm seriously stoked. I'm seriously. Oh, there we go. Okay, Curtis, you're all set.
Yeah. So let's see if I can share my screen now. Share screen. Okay.
Wonderful. And I know you're doing awesome stuff too. You were getting results too. Everybody is right now. There we go.
There we go. All right. So this is one of the runs from 13th of January, and I'll put it full screen here. And so what you're gonna see is in here you can see the device. It's mounted in a way where it's free to move on these bearings. And what you have here on the right is a brass reaction mass. On the left is an aluminum cap. So the brass is heavier and larger, and in between them is the piezoelectric core. And so basically, what will happen is as this moves, if the Mach effect is working as intended, it should be able to push this side. So we have some registration points here for video analysis, but this is rigidly connected to a torsion arm, so it can move left and right. So I'll go ahead and play it. And and by the way, the squiggly lines on the left, I'll describe as it's going along. So the bottom left is basically showing some where the resonances are. In this middle layer, there's different squiggly lines doing different things. The blue one is the waveform of the energy that's going in. And then up here, the red line is the actual position that measured on the other side of this torsion arm of how far that torsion arm is getting pushed. So you can see that basically this guy is moving and he's pushing it off to the right, and really there's not a lot of swing back and forth. And in the past, we've had it so that it'll swing back and forth and look a lot like noise. And you see there's some very large reactions that happened here. And this was at 1.4 times 10 to the minus 4 torr. So basically there's almost, there's very little air or atmosphere in there. That was not the best. That was not the best run. I think the best run was number 4, which is what that graph I showed in the presentation was. Let me mute that. That's one of the pumps, and you can see this one immediately just kept on pulsing and kicking off the entire run. So we're getting a lot of movement here, and it's actually overranging the measurement. So you can see this is going up to 5 volts. So this is really was really a really good run, and throughout that day that was working. Now we've since put this back on here, and while it does do the same thing, it's kind of binding. Unfortunately, these bearings sometimes because there's so much vibration and energy happening, they sometimes start binding on the metal rods. So yeah, we're getting good good effects. And let me stop sharing here. We're hoping to get at least 3 more test articles and be able to repeat this, repeat it reliably. And once we do that, we might need a replication. So yeah, that's where we're at.
Awesome. I may get a little echo here because I had to take my earbuds off to charge them up. I just ran out of juice, but let me see. So Curtis, thank you, sir. Thank you. Let's go to Drew. Do you have an update for us? I think Drew does.
Yes.
Okay.
And I don't want to sound cryptic, but I have to sanitize this because this test is only like an hour and a half old.
Oh, okay. Do you want? Should
So
we come
just
back
give me
in a
a
moment?
yeah, just if you give me 2 minutes, and I'll be
Okay.
ready. So go on to
Good
the
deal.
next person, and I'll be right here.
Okay. Yeah. Well, Curtis, thank you, man. Thank you. I'm
Sure, no
not going to
problem.
force you guys. I'm not going to force everybody to clap like every time for lab time because it'll drive you nuts, and I'll get beat up. Wait, there's Jared. Jared's okay. We'll clap. Well,
Tim, I have
love. Oh yeah,
I
Jared.
have a little 20-second clip to show.
Okay. Let me do that then. Yeah, and again, it's if you present, share screen, and then pick the
All right, we can all see it, I hope. So Charles Crawford and I had a meeting with Alexei Chekhov, the
Jared,
inventor.
I'm sorry, sir. It's not showing. It's not
showing.
There we go. Now it's showing.
Okay. I had to give it some time. All right, so we got my partner Charles and I had a meeting with Alexei Chekhov, the inventor of the Graviflyer, just within the last week or two. And he built a whole nother device for us just so he could do a live demonstration for us of his entire tuning process. And here is a little clip for everybody to see. This is 3.5 hours watching him go through 3 rounds of tuning because he hadn't actually tested this prior to our meeting. So it wasn't necessarily tuned perfectly to be able to lift off straight up. So instead, since the spacing of these rotors is a little bit off from what they should be to be perfectly tuned, the thing just tips over like it does in some of his other videos. But three tries, and he managed to make the thing actually do the thing. So I'll just do that a couple of times here. So he's pulsing the ultrasound here when he already has everything else already tuned up right. And it ends up creating some kind of standing wave, but because that standing wave is offset off to the side, it ends up tipping itself over. But it was the first and only live demonstration he's ever done for this device. And along with it, he gave us really good tuning instructions. So now Charles and I are quickly working through that to try to replicate his results that he showed us.
Wow, this is amazing, Jared. Really, this is like confirmation that everything you're working on is real.
Yes, absolutely. So up until this point, because no one had ever actually seen him do it, there'd always been kind of a question mark as to, how legit is this thing? How legit is this guy? But after Charles and I got to watch him go through the process 3 times over 3.5 hours, trying to get it tuned just right, because if he hits that button and he misses the moment where everything is in resonance, he has to turn it all off and start again. And it takes about 30 to 45 minutes each time you want to go through the process of getting it up to the point where it's in this perfect resonant state that you can pulse it on and catch that, and then it'll lift up. So the fact that it wasn't,
what's he flicking?
That button that he's pushing is turning off the ultrasound buzzer. So just a little quick rundown on this thing. You got 2 spinning discs. You got a center disc that doesn't spin. And then you got a ultrasound buzzer on top. So you got high voltage on the spinning discs from DC. You got an AC high voltage RF 1 megahertz-ish on the center plate. And then you got this piezoelectric buzzer on the top. And that button that he's pushing is what turns off the piezoelectric buzzer. So he's going through this tuning process, simultaneously tuning the ultrasound frequency and the RF frequency and amplitude of the center plate there. So as he's doing all of that for 20 minutes or so, finally he'll find this sweet spot where everything is resonating just right. And he lets it sit there for a few seconds, and then he turns off the ultrasound by holding down that button. It turns it off. I have observed with all of my equipment here that when you turn off the ultrasound, about 3 to 10 seconds later, there's an RF release. Like there's this huge pulse of RF energy that gets released all at once. Like it's storing up this energy in some kind of, I don't know, RF standing wave or something. And then when you turn off the ultrasound after a few seconds, that Q factor is low enough that dissipates. But it dissipates very rapidly, and so you get this pulse of RF energy. So I think what he's doing is he pushes the button, it turns off the ultrasound, he holds it down for a few seconds, he lets it off, it builds up the field again, he pushes it again, and then it collapses it, and he starts pushing it faster and faster and faster, and then usually within the 3rd to 5th push, it'll pop up off the ground. So it's a weird deal. Like it's a very complicated tuning process, and it's a very artistic rendition of trying to, find that sweet spot. Because as you saw in that video, he doesn't have any screens. He doesn't have any like test equipment or anything. He's doing it all just by sound of the sound of the beat frequency for the speed differences of the 2 spinning disks, as well as the physical, the vertical motion of those disks all create a bunch of different vibrational sounds that you can hear as well. I've picked them up at about 420 hertz, 610 hertz, 50 hertz. There's a lot of lower frequency mechanical vibration sounds. So you start listening for those too. And he's doing it all by ear. But yeah, so it's an ultrasound off button that he's holding and then pulsing faster and faster.
Wow.
Question: has this been done in a vacuum?
No. In fact, I don't necessarily know that it will work in a vacuum. I have this spreadsheet that I've made that takes all of the different materials into account to include the air, and it shows the correlations between the sizes of the discs he used, the thickness of the discs he used, the frequencies that he used for each of these different components. And it suggests also in that 3.5 hours we had with him, I asked him, how does temperature affect stuff? Because that'll tell you a lot. If cold air or hot air changes your frequencies or changes the spacing, that tells you a lot about what's going on. And he said that colder air made it so the discs had to be closer and the frequency had to be lower. Hotter air meant farther apart discs and higher frequencies. So there's an atmospheric component to it, which makes me think that it's creating some kind of standing wave beneath it. Just yesterday, I was observing those acoustics that I was talking about, those 600 hertz thing, and there's gaps. So you'll hear it at like 1.5 feet, 3 feet, 7 feet, 12 feet, and you won't hear it anywhere in between there, right? And this isn't like ultrasound that's super directional. This is a low frequency, so you should hear it everywhere. So it's creating some kind of acoustic standing wave.
Low frequencies. I actually had a customer who came here for the hybrid battery shop way back when, who worked at a top secret acoustic laboratory in Poland or was it in Russia or something like that? And he said he was working with infrasound, and they had the exact same effect, that there was sounds that you could only hear or feel at certain points in the room. There was peaks and troughs, and it was very noticeable because especially at those low frequencies, sound is, the wavelengths are pretty freaking long. But Jared, I just want to point out one thing, which a question actually. Do you think it's possible for it to work in a vacuum? Like if you changed all the parameters to account for no air?
I don't feel comfortable saying one way or another yet. I want it to be able to work in a vacuum, but the fact that we're dealing with acoustic sounds, right, that he's listening for these things, the fact that my spreadsheet suggests that it's using certain standing waves in air, like it's using an even number of standing waves on the top and an odd number on the bottom. Maybe it's vice versa, but either way, he's using an asymmetric number of standing wave nodes in air for the top and bottom. If you had all of that self-contained into, a disk, a flying saucer that would encapsulate this thing, I don't necessarily see yet how that could be propellantless propulsion if it's relying upon an air medium. So assuming Charles and I can get it going, which I have every confidence now at this point that we're going to get it going. The next step after that is to go back to Kepler and do more vacuum testing with it to see if it's still possible.
I would suggest smoke testing too, because that's
we've
going
done
to show you.
lots of smoke testing already. And the smoke testing doesn't really show much in the way of a Coanda effect or anything. And it doesn't really show much in the way of these pressure waves that I'm hearing. So,
well, in the videos, what's interesting. Oh, I'm sorry, Curtis.
Go ahead.
I was just thinking in the videos, you see he puts his body over the top and he puts his hands and stuff underneath, and you don't see airflow moving the cords. And so maybe there's a standing wave, but a lot of the things that would be indicators of airflow aren't there, which is kind of interesting.
So yesterday I was doing some mechanical resonance testing, and I noticed the extra low sound, the 50 hertz and the 400 hertz sounds coming directly underneath the center of this thing. So there's two places around this thing where you can hear the sound. It's directly beneath the center, and it's slightly angled upward above the horizontal plane of the center disk there. That's like the only two places where you can actually hear any of these low vibration sounds. It's quite odd.
So my experience was 2 years ago when I started full-time with working with Jim Woodward on the Mach effect drive. They had it at the time out in the air on a pendulum, and that it was moving, and I was very wary of that, and I expressed that. It took a few months to convince everybody to put some baffles or take a step back, and it turned out yes, that it was the air effect, and it's a very similar thing because that device is driven between 40 and 20 hertz, just depends on the mechanical resonance. And you got a piezo stack, you're putting in a voltages, pretty high volt, I don't know, not that high, 100 plus volts at that frequency. And so you have a very similar device, it sounds like, and you would expect, if it's working, to interact with the air. So you should get air effects. So anybody that does a Mach effect type experiment and doesn't see anything, they're doing it wrong. Because if you're doing it in air, you're going to get a push from the air. Now, once you put it in a vacuum, the thing is, what the Mach effect is trying to do is coax out the Mach effect, some kind of a way for propulsion, using pushing. You can call it pushing against the ether, whatever way you want to look at it. And ironically, that is kind of starting to come out now that we don't have the air in there. So it's almost like maybe it was it's dampening the effect or hiding the effect. But those kind of devices, because they're the Mach effect drive is dependent on the vibration. It needs the air to not be in there or to not work against its force.
There is one way in which that it can work in a vacuum, because there's multiple theories for how this thing works, right? One of the theories is that it is using that little ultrasound buzzer as an electromechanical coupling for some of these RF scanning waves. And so when he's finding the right frequency with that thing, it has very little to do with the air. I mean, you could still keep it encapsulated in air, but you might be able to use a better medium than air, just as long as there's some way to mechanically couple the vibration of that thing to the mechanical vibration of the rest of the disks, and then couple back the RF, right? So a medium that transfers the mechanical energy without impeding the RF reflection. But if that's the case, then that electromechanical coupling, I think, might work similar to the asymmetric damping of the Mega Drive, where it's the same thing in a different box.
Yeah. Yep. Yeah, it might be a combination of the Mega Drive and the MLT drive, right? The Max Lorentz, because you get in that drive have a spinning magnetic field, so there could be something there. But yeah, definitely try to do the testing in a vacuum, and it's kind of weird because like some of the same things that advanced doing it in air could work in the vacuum as well, but some things could work against you. Where you optimize in air, you might not get the effect that you really want, which is to work in the vacuum. One other thing that one of the collaborators in our group has mentioned is that what she's doing, Michelle, what she's doing is she has an air sled, basically with a rod and some air bearings, and she has the device encapsulated so that she's trying to block the air effects, but she doesn't have it in a vacuum. So what she's considering doing is putting things like helium or argon, because they'll have different effects in terms of like how they move. But ideally, you would want a really good vacuum. That's the ultimate way to go.
Awesome. Well, guys, if it's okay, let me go to Drew now, and then actually, man, we're on the hour every hour today. But that's awesome. That's awesome. Yeah, and again, Jared, you guys are doing amazing work as well. This is the year, it's all happening. Drew, go for it, sir.
Yeah, I'm just trying to figure out which button to push to share my screen.
I'll take everybody out. I'm just admiring Mark's coat too in the background.
Is
He had that hood on a minute ago.
Present, yeah.
Is it present?
Present.
Oh, share screen. Okay.
Yeah, the present button and the share screen.
Share screen, screen sharing, looking, some screen sharing, to share screen. I don't know what the hell it is. Okay.
Present share screen. It'll make you pick your
truly
window.
hate computers. Okay, you're seeing something that looks like a graph? Maybe?
Not yet. Not yet. There it is. Okay,
Maybe?
perfect.
Okay. The only thing I can tell you about this experiment is, it sounds like we always have success. We don't. This was a particularly miserable day in my life. Things that should have worked didn't, and things that shouldn't have worked didn't, and things that have never failed did. And then I called Charlie and blamed him for everything. So this was an interesting step forward. Where I kind of went away from my core bread and butter work for the last six months and just chose a plate chemistry that I was happy with and stuck 3 of them in the chamber at some distance apart. And I apologize for the blurriness of the image, but I had to knock it down some because we have enemies in the world, apparently. So I don't want to share the magic with the whole world yet. But basically, these are 3 plates, and this test example is the center plate. And basically, it starts down here at 0. This is in millinewtons. And this is basically because I have a real system. It has mechanical drift. So this is the first, whatever that is, maybe the first 40 or 50 or 60 seconds of operation. It's got a little tiny drift to it, maybe probably 20 micronewtons per 100 seconds or something like that. Then hit the power button and drop the voltage, and it's dropped in steps so that it doesn't short the plates, because the plates don't like to be hit with high voltage all at once. And the thrust immediately comes up until it hits about 1.5 millinewtons. Again, this is only the center plate that's being energized of the 3 plates. Run it for a little while to see what it's going to do. Is it going to bleed off? Is it fake? Is it real? Does the machine get bored and spit out some garbage? In this case, it was very steady. Turn off the power. Thrust drops down to here. Takes about 100 seconds, give or take, to bleed these plates down because they're starting to act like big ass capacitors, which is what they are. So then sometime else, turn on the power again. And in this case, I just here's power off. This is 0 volts, and then hit power, drop it down, whatever, 7,500, and the thrust immediately comes up. Drop the power, here's the power on, and there's the off. And as you can see, as the voltage comes up, or I'm sorry, as the voltage goes to 0, the thrust drops off to 0 again for the most part. A little bit below. There's some interference between the plates or something. I don't really understand, because the drift of the system is positive, but they ended up about 100 micronewtons below 0. So that means I'm stealing charge from one of the other plates, or it's getting screwed up and put somewhere else. I don't know. I'll let Charlie figure it all out. But the one cool thing I wanted to show here is that somebody said that there's no way this thing can work at the power levels that we're talking about. This is real current over here. And this is measured off of the power supply. So this is what the power supply is putting into the system. And as you can see, these numbers are, here's it's kind of tough to see, but there's the little aqua colored stuff. So at maximum thrust, you can see the aqua colored line is buried down inside this purple line. Well, the purple line is the power supply. We burned out our $6,000 amperage detector a couple of months ago, so we took it offline, but I haven't gotten it out of the software yet. But the aqua colored line is buried underneath here. That's the actual power supply, and the power supply's output is still very accurate. So as you can see, the power consumption while it's on is in the noise. It's like less than 0.1 microamps, and it's 7,500 volts. That works out to something like, I don't know, 600 microwatts. And this is running 3 plates, or I'm sorry, it's powering 1 plate, but it's the same numbers when you run 3 plates or 300 plates. It doesn't really matter. So it's an electrostatic engine. It's an electrostatic propulsion device. So it's not like we're pumping energy in to make thrust come out. So some other fundamental physics is going on. Charlie and I differ on what we think is going on. I think we're stealing momentum from the universe. One little wink in, I think we're throwing up a wall in space. And someday, if somebody wants to come over and have a cup of coffee, I'll explain all the full details of it. But I think when the particle comes into existence, wink, it comes into existence with momentum and velocity and, I don't know, Higgs or whatever, all the crap that it comes into the universe with, and it slams into this wall that we throw up in space, and then it imparts a little of its momentum to the wall. Well, the wall's attached to the plastic plates, which is attached to the force meter. So wink in, slam into the wall, wink out, or whatever particles do that don't hang around long. And the net result is it pushes against the plate. That is what I believe is going on. So we're still tuning a couple of the problems. We got some issues with plates, and they're not acting quite right. But I'm very happy with 1,500 micronewtons for 10 square inches. It's about 50% of Earth unity, because that plate only weighs 360 milligrams, and it's making 150 milligrams right now of thrust. So I'm very happy with it overall. The things that are going wrong are very wrong, so I got to fix all that. But it's a typical Saturday here in the shop. 2 steps, 1 step forward and 22 steps backwards, and then we play catch up for the next couple of weeks, trying to figure out all the things that are wrong with this test. So that's what it's like in the real world. I really hope the rest of y'all have better success to failure ratios than I do, because this is maddening, the stuff that goes wrong on a regular basis. Anyhow, any questions?
Drew, that is awesome, man. That is truly, truly awesome.
I have a question.
I got a question too.
Have you considered? It sounds like you're measuring force with some kind of a cell. Have you considered putting it on bearings and letting it move, or putting it on a torsion arm or something?
Oh yeah, we've done that. We've built spinners. We've built the torsion things, and yes, this is definitely being measured by a force meter, but the digital force meter is accurate down to about 10 micronewtons, give or take, maybe plus or minus 10 micronewtons in any given test, because we sample 250 times a second, and the actual force meter is only accurate to 0.1 millinewtons. That's 100 micronewtons, but we sample 250 times a second. So when you take the average of that, it truly does give you a much higher resolution. So instead of 100 micronewtons, it's probably plus or minus 10 or 20 micronewtons. So you just can't beat that kind of reproduction of accuracy and data.
Right.
But we've done the whole thing. We've done the thing where it's hanging down and we turn it on and it moves a couple of millimeters. And I guess how much the thing weighs, and I guess the small angle theory, and we do the math, and we're accurate to within, I don't know, 20-30% usually. But it's all guessing because you don't really know where the center of gravity is. You don't know really how much drag you have in the system. You don't know what the bearings are eating up. You don't know what the inertia is doing. This is the answer. The answer is put it on a digital force meter and run the test hundreds of times and use the same setup. I mean, we use the same ITO box. We use the same exact pendulum thing that's hanging there. We use the same little piece of string that ties it to the force meter. Right before I run the test, I thump the chamber, not too hard because otherwise you throw the electromags off and then your turbo goes into scream mode. But there's mechanical stress that's stored up in the string. You wouldn't think that until you've run the test 100 times. But you do the same exact thing every time, and the only thing that's changing is the data. So this may not be a great, we'll call it. This isn't probably the greatest. Well, what do we call this? It's not like it's exactly 1,550 micronewtons. I mean, that's probably accurate to within 100 micronewtons or so. But that 1,550, I guarantee you that this crest and this crest are at the same. They're the same accuracy. So if this crest is 1,550 or 1,500, and this crest is 150, then I start looking for what the hell did this thing do wrong. I can get accuracy between tests. So I go for deltas. I go, hey, did this plate work well? Test after test after test after test, versus I throw the next plate in there. And since I know the accuracy of the system is relatively the same between major tests, I get a high degree of accuracy that I can say, hey, this chemistry is better than that chemistry. Let's move forward. Or this chemistry is worse than that chemistry. Let's go figure out some other, what we do wrong. Or this plate spacing is wrong, or this voltage is wrong, or the thing's shorted out. So that's probably bad. So you got to be real careful when you start just putting stuff and watching it wiggle or whatever. It's all about reproducibility of the accuracy. So did I answer any question? Did I answer your question?
Yeah, it sounds like you've done those tests. Thanks.
Yeah, got the videos. Hundreds of them.
Drew, what's the pressure? Oh, it's I see 6.
Let's see. I hate that I have to do it in log, but otherwise the thing don't record worth a squat. So I'm down around. This was early on. This was probably, I'm going to say maybe 9 or maybe 8.5 times 10 to the -6. So probably 8 point, probably somewhere between 8 and 9 times 10 to the -6 torr. So, I wanted to make sure I had fully shielded because I didn't want this thing shorting out because of how close the stuff was. So I threw an extra layer of Kapton on there, and what that did was it trapped a little pocket of air. So I ran the vacuum for, I don't know, 24 hours, and to get it all out of there. So it took a long time because there was air trapped. You know, molecules don't like to come out when they're trapped between two sheets of plastic, and there's just this little tiny slit where there's no tape. So it took a long time. And today when I reran this thing, I got it down to, because I ran this about 20 different times. But I had it down to 4.5 times 10 to the minus 6, and it was given the same results. This was an early on test. Went on, when's the 19th? That was yesterday. So this was 2100. So that was sometime last night. So yeah, it was good vacuum. It doesn't work in atmosphere. It shorts out. We're losing energy to the, I don't know what, probably the edge effects where the metallization just sends the atmosphere into corona. You know, it's only a couple of microns thick, the metal that we're laying down. It's real easy to send air into corona when you got a couple of micron thick metal edge at, you know, high voltage. Real easy for that to happen. So that's it. That's all I got.
Awesome. Well, I think we're about the top of the hour. Should we go to open discussion, guys?
We have Lou Elizondo and Jeremy Corbell in the live chat, but I'm not sure if they're real or if they're puppet accounts. Jeremy, you want to chime in on that? You got to unmute yourself.
No, I've seen these guys on a bunch of other. They go around on a lot of different live streams and troll, dude. They look hilarious. I've seen them on Steve Cambion's show, and they were on Thomas Fessler one night too. Anyways, yeah, no. If those guys do want to come on the show, the offer is always on the table if you guys are listening or watching.
Before we do open discussion, I think we should do at least one more hand for all of our lab experimenters today. I want to do that. You guys are kicking serious butt. This is one hell of a year. Brian says he suspects imposters. For them or for the lab guys? That's not really Mark. I've never seen Mark in a coat like that before.
It's cold.
Imposter.
I've never seen anybody in a coat like that before.
I think that's a cool coat.
It's hard to be an imposter in science.
It's 47 degrees in my shop. That's why I'm not out there. It's freezing out there.
Look at that. That's hardcore,
What do you say,
man.
27 degrees?
47. If it was 27, I'd have to shoot the weather guy.
Over here, it's 20 degrees outside.
Yeah, we're warming back up. Our area, we got 2 feet of slush, which is, in a weird way, even more disgusting than snow. You know, it's you can't really do anything with it. It's like snow that hasn't left yet. You're just waiting for it to leave.
Where are you at, Tim?
I'm in the Seattle area. I'm up in a little town called Blaine, right at the border. We're right next to the ocean, though, so it usually doesn't stay cold that long.
Every once in a while, they punish me and send me out to Kent.
Okay, yeah, this just south of Seattle.
Mm-hmm.
I've got a couple of vids that I could show that are a demonstration of some of the things I was talking about. If any point you guys want to check that out, I can share those. Just trying to, those things we want to discuss, etc.
Yeah, if you want to. And then actually, who else was? And Dan, you wanted to do a quick shout out for Maya's paper also.
Yeah, so if you guys haven't, I'm unmuted.
I can put it up. Let's do that real quick.
Yeah, this won't take long. I'm not going to go in too depth with it. Do you want me to screen share it or do?
Yeah, go for it. Yeah, so that's Maya Benowitz. Dan emailed me about her a few days ago, and she has some personal stuff that she is a little distracted with, but we hope to see her. And she's pretty cool. She has the TARDIS on her Twitter feed, all sorts of time travel stuff. And the math that she does is like, it just hurt looking at it.
Can you guys see this?
Here, I'll. There we go.
All right, is this up?
Yeah, it's up now.
Okay. So I just can't see it on my screen. So this came out on the beginning of the week. She put out this paper. I'm not going to go too in depth in it, other than she's basically beat me to what I've been doing with like the polar multiversal dimension and finding Einstein's equation from the wave function in an Everettian context. And it's really actually genius what she's doing here, because she's starting with the Wheeler-DeWitt equation instead of the regular non-relativistic Schrodinger equation, which is very interesting. And I'm not going to waste you guys' time going too in depth in this, other than say that you guys should really go and read this paper. And I'll kind of highlight here what she kind of comes to in her conclusion. The Everettian field theory does not prohibit a traversial multiverse. This begs the profound question: can we split time in two different directions, assuming the decoherence of timelines, with a fine-tuned antimatter reaction, which kind of speaks to the polarizable vacuums of matter-antimatter pairs that a lot of you guys are working with, to warping the quantum nature of space-time into shapes of our design, to explore the many worlds. Will humanity one day find a world out there? Or will we one day find our way to them? If quantum universality is true and the multiverse exists, then there exist worlds where future humans master the quantum nature of space-time to travel, quote-unquote, past adjacent light cones, and a form of time travel within the multiverse. So if this is possible, then where are they? So you can kind of see where she's starting to extend I think she's going to be extending the Fermi paradox to UAP in the multiversal context here, which is, if you guys saw my talk last month, is basically what I've been doing, is working out a way for warp drive navigation. If we're taking if we're taking superluminal travel seriously, how do you get around the different paradoxes that are assumed to that? And again, just go and read this paper. For those of you who are well enough versed to be able to keep up with the math, she's on the right track. I'll stop sharing it there. So yeah, then that's all I got. I'll go more into it when I have a better understanding of things.
Awesome. Thank you, Dan. Yeah, well, I guess it's open discussion now. So if anybody has anything, and if you guys don't have anything, we can close it down for the evening too. It's been one heck of a day.
I got an old video from a couple of years ago. If anybody want to watch early days of the Drew and Charlie show.
Yeah, I'd say go for it, man. And then Shiva, do you have some videos you wanted to show?
Yeah, I was just going to demonstrate a couple of the different things I had mentioned during my talk that are better, taken in when they're.
Yeah, I would say. Do you know how to share? Do you know how to do a screen share?
Yeah, I'm sharing one right now.
And then we'll do Drew's after that.
Sure.
Should be able to see it there anyway. I got about 4 different little videos here that are great for demonstrating the various things I was mentioning. Is it showing up there for you?
Not yet.
Okay. Well, I do have it in sharing. I can stop it and restart it. Let's do that. See if that
try that. Maybe it's a browser permissions thing. It should tell you.
Oh, no, it's showing it down there for me. Let's see. Let me just reshare it. Maybe it'll pop up for you.
There we go.
All right. Let's see. You're showing there? Okay, let me hit the play on that. So
Yeah,
this video put out by John Bush at MIT, and just kind of demonstrating some of the effects of the silicone walkers and some of the history behind it. This is the most like succinct video that he put out about the walkers. And he's going to show a little video here where he just takes out the frames, and so it looks like it's hovering. It's not actually hovering. It's just every other, every few frames, it's just showing the top of the bounce. But basically, this is showing how these walkers will infinitely bounce on top of a fluid, and as part of the fluid dynamics when there is a pool that's driven, and so it's pushed along by its guiding wave. So this is a demonstration of the way in which pilot wave works, where there's both an energy in the bath itself, and then the waves that are created by the walkers bouncing are part and parcel in the system, and the way in which they determine their own future. And so it's a really interesting way in which determinism kind of shows this implication of the unit in determining what the future outcome will be. Now here's the walker as it just explores the corral. Looks completely random whenever you're watching it over a short period of time. However, as you watch it over a long enough period of time, the result of a superposition of the waves is that you end up seeing, you start seeing a pattern, and you see the guiding wave field is the Faraday wave motor of the cavity. So yeah, just as it shows the velocity fluctuations, and here he's showing the probability distribution. So in other words, the probability of finding the droplet in any one of those locations is the same thing as finding the probability of finding an electron within its electron cloud that is part of the shapes of these wave equations. And so that's where he's drawing the analogy here. Now this is very early on, and there's a lot more that you can check out here, but he's just kind of showing the most succinct version of that. Now, if you allow me 3 more videos, if that's all right, I can show you some of these others real quick. Let me drop that one and pop in the next one. Oops, not that. It's the wrong button. Share screen, and let's show you. So once you can pop that back up there for me, I'll show you what I'm talking about here with standing waves inside of a single droplet. So let me hit play on that. There we go. Okay, what we're looking at here is just a single droplet of water that is being vibrated. And then when you reach the right combination of frequency and amplitude, the droplet will start to resonate within its own cavity that's created by the border that is defined by the droplet itself. So there's nothing really amazing about the effect that you're seeing. However, what the effects once you start to look at them, once you hit these appropriate resonances, are that there is, first of all, there's rotation. So you see the toroidal rotation. If you look at you can see a bubble in there that's moving along with it. But there's not just a simple toroid inside this. As you'll see in just a moment, it's going to transition to an image where there are particles flowing within it. And what you'll see as the particles flow inside this is that it creates a what looks like the d orbital of the electron in hydrogen, and that's going to transfer here in just a moment. As soon as it gets to that, it's very interesting. So you'll see there are two vortices like going like this, and then 2 vortices going like this. So there are multiple vortices within this toroidal figure that are embedded within it. And then as I'm going to go ahead and try to just move this along to a little bit later where you see some of the other frequencies. Now he talks about some instabilities and how when you hit certain frequencies that are not the appropriate combination of frequency and amplitude. But then some of the things that you'll see are, you can get any variety of regular figures will show up here. And of course, inside this regular figure, there are vortices which are going alongside those regular pulsations that you're seeing there. So this is the effect that I was talking about when it comes to wave vortex interaction and the creation of a cavity through these resonance effects. So that's that is called the Faraday wave mode. That is what you're seeing there occurring, is it's part of Faraday wave mode. But they, in cymatics, they just call it a cymatic figure or something to that effect. So that you get, I think you get the idea there. Then let's go ahead and switch to the next one, if you don't mind. And let me stop that and present another one. So
have you tried freezing water well under those vibrations? Have you tried like?
I'm not the experimenter that does that. There's a few of them. That guy is a German experimenter. I've forgotten his name, but he's fairly well known.
Flash freeze it with liquid nitrogen or something,
Yeah, there's some neat things that they've done with cymatics that they're not relating to the pilot wave hydrodynamics model, and so that's one of the parallels that I've been trying to make people see, is that this, you have in pilot wave hydrodynamics at MIT with John Bush and all that, these things that we're seeing as kind of a fringe science, that where it was kind of artistic, it's with cymatics. They didn't really necessarily understand what it was they were getting at here scientifically. Well, here you have a relationship between the two in the Faraday wave mode, and understanding what it is that that they're creating and how it can impact something that is meaningful when it comes to quantum mechanics, for instance. So here's the reversible laminar flow experiment.
There we go. Okay.
Yeah, sorry about that. And let me go ahead and hit the play button on it. So this is what I was talking about when conceiving of dimensions in other ways. And what you're going to see here is that they can put these droplets in this fluid. Let's see if I can speed it up. I hope it'll speed up for me if I hit these. Is it wanting to? Oh, I probably shouldn't have done that. Looks like sharing it and hitting these things messed me up. Oh, there we go. Okay. So he'll put in these 3 droplets, red and blue and green, probably. This is a bit of a slow one, unfortunately. So I'm going to jump ahead and get to where he's mixing it up. So you see him, he'll start spinning this thing. And there's a variety of these you can find out there in the reversible laminar flow experiments. So the idea here that I want you to see, and then he'll reverse it. I don't want to take too much longer here, so I'm going to keep going through it. And as he reverses it, you'll see that the droplets are completely recovered. And so what I'm talking about here is this is to demonstrate what David Bohm called implicate and explicate order, and that is a different way of seeing the idea of additional dimensions. As those droplets, when they appeared mixed, they still existed, just in a different dimension. And so that understanding of dimensions, that they are here and present and part of this reality, simply is just a different mixture of this reality, is a way of seeing the that whole effect. So let me change that over. Stop on that. And I got one more. And this is the talking about the structure of the vacuum. That a lot of people have never seen this. It's a really neat little effect. I discovered this fella who made these videos a while back, and I've never seen anybody else point this out. So what he's done here is he's taken and created what are called heel-shell plates, where he's taken a ferrofluid and pressed it between 2 plates, lit it from the side. And what he's done is he's created a novel visualization of magnetic fields. And what I contend is what he's showing here, that I've seen you can visualize it in a few other ways. And generally what you see are these figures that are like, I guess, golden spirals, etc. Is that there is a microstructure to space that was first talked about by Maxwell when he was describing Maxwell's equations. He talked about these that you have to have idle wheels, and what he's talking about there is whenever you have layers that are moving across each other in a fluid, and what will happen is the vertical motion, that is, in other words, what allows them to move against each other, is that there has to be some sort of vertical motion that occurs, and that can be tremendously smaller than the laminar flow layers. And so this is what big whirls lead to little whirls, sort of thing. If you've ever heard that little ditty for when it comes to hydrodynamics, it basically describes that vortices will break down to smaller and smaller levels. But then there's also a mechanism by which vortices can add back together and become larger ones. And so it's just an interesting method of visualizing what may be a microstructure to the vacuum that we might at some point be able to exploit in some way. So that was it.
Awesome. Okay. Oh, there we go. Yeah, perfect. Yeah, this is really exciting stuff. And this, I've actually heard, I mean, very rudimentary variations on what you're talking about, Shiva. So this whole vortex dynamics, and then Einstein's unified field theory was based on torsion, right, which is spin. So it all kind of comes back to spin. But okay, well, guys, I think if anybody doesn't have anything else, maybe we should consider shutting things down for this evening. This has been, yeah, I actually, you guys wore me out. I'm exhausted, but in an amazing way. This is so much been drinking from the fire hose. So,
Tim, let me throw something up. Just 30 seconds.
oh yeah, go for it, Drew. Go for it.
Okay, theoretically, it's happening.
Hold on. There we go.
Okay. This was back in 2019, and I sped it up tenfold because otherwise it would painfully slow to watch this 5 minutes. But this is about 100 micronewtons worth of thrust hanging from a wire, self-contained power supply that was actually working. This was super early on. Like again, those two thrusters are making a total of about 100 micronewtons of thrust. And when it's on, it would go against the torsion, and when you turned it off, it would go right back to where it was. Anyhow. That's what got us excited, was a couple of pieces of epoxy and some metal plates shoved against some styrofoam, and we were off to the races.
That's amazing. And the stuff you're working with now is so much more efficient, so much more powerful.
Oh yeah, we're in the 10 millinewton range now. So yeah, trip down memory lane.
Wonderful. Well, guys, why don't we close things down for today then? I think everybody's kind of slowed down. This has been amazing, an amazing APEC presentation. Thank you all. Thank you so much. And thank you to everyone in the audience and everyone who's contributing ideas. And again, I mean, what I've been seeing, kind of looking at it from a distance, is all of this is moving forward. And that's a tribute to your guys' hard work and perseverance and just dedication. So you're making this dream a reality, right? And it's like we're seeing it move forward every day. And that's so exciting. That is truly exciting. So thank you. Thank you to everyone.
Thank you.
Yeah, we definitely won't get there listening to Neil deGrasse Tyson or these celebrities.
No, I think we're
Sadly,
getting
you won't get there.
We are getting
You
there.
won't get there waiting for NASA either.
No, we got to do it on our own.
It will not happen.
We're on the path.
I'm gonna close things down now.
Night.
Good night.
All right, thanks.